Section 15 of a textbook of assaying for the use of those connected with mines, by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 9. Silver, Gold, Cyanides, Platinum, Mercury. Part 7. Cupellation. The cupellation of lead for gold differs very little from that of lead carrying silver. When the gold is accompanied by a larger proportion of silver, and both have to be determined, the cupellation must be conducted exactly as in a silver assay, the usual precautions being taken to moderate the temperature so as to lessen the cupellation loss and to promote a slow and undisturbed solidification in order to avoid spurting. If, however, the gold predominates, the finish should be effected at a higher heat, as the melting point of gold is 100 degrees higher than that of silver. The bad effect of a higher temperature in increasing the cupellation loss need hardly be considered in the case of such small buttons of gold as are obtained in assaying gold ores, as any loss there may be is hardly appreciable by the balance. With larger quantities of gold, however, as in assaying gold bullion, this loss becomes important, and it is therefore necessary to very carefully regulate the temperature of the muffle so as to minimize the loss. The cupels are made of well burnt bone ash of the fineness of coarse wheat flour, moistened with 1/12 of its weight of water and compressed into shape in suitable moulds. The moulds sold for this purpose are often of unsuitable shape. Since lead has a specific gravity of over 11, a cup to hold from 15 to 25 grams of molten lead need not have a capacity of more than about 2 cc. A hollow about 1 inch across and 1/4 of an inch deep is sufficient, and the body of the cupel to absorb this weight of lead should itself weigh from 20 to 25 grams. The button of lead in a gold assay may be twice as heavy as this. For these larger buttons, a hollow 1 1/3 inches across and 1/3 of an inch deep will be sufficient. If these larger cupels are not at hand, the larger buttons will have to be reduced in size by a scorification before cupelling. In some cases, this preliminary scorification is advantageous or even necessary. This may be because the lead is hard and impure, or it may be that a very small button of gold is expected. In the latter case, it is best to scorify the lead down to something less than 1 gram, and to perform the cupellation on a specially prepared small, fine cupel. These small cupels are best made by grinding the unsaturated portion of a used cupel to a fine powder, and compressing the dry powder in a small Berlin crucible or scorifier. The face should be made quite smooth by pressure from a pestle. On such cupels a small speck of gold, less than 0.01 of a milligram, will be left in a good shape and easily visible, but the cupel must be withdrawn from the muffle as soon as the cupellation is finished, to make sure of always getting the button in good condition. In places such as mints, where large numbers of bullion assays are regularly made, a special form of cupel is used, so that not less than 6 dozen assays may all be cupelled at the same time in a muffle of ordinary size. These cupels are square blocks a little less than 2 inches across and a little more than 3/4 of an inch deep. Each block carries 4 hollows of about 0.7 of an inch across and 0.3 of an inch deep. A muffle on a floor space of 6 inches by 12 would take 3 of these blocks abreast and 6 deep, and thus provide the means for 72 assays. Note from Percy, Metallurgy of Silver and Gold, page 258. End note. Cupels made with wet bone ash should be slowly dried, and if in the muffle they can be slowly brought to an orange-red heat, it is all the better. Under no circumstances must the lead be placed on the cupel before the latter has been so thoroughly heated that it can no longer give off steam or gas of any kind, for this gas bubbling through the molten metal spatters it, thus spoiling one assay and throwing doubt on all the rest. Again, the risk of freezing at the start is much greater with a cupel which has not been properly heated. The best plan is to do all the cupellations in batches. After the muffle has cooled down for the withdrawal of the last batch, and the old cupels have been taken out, the new cupels for the next batch should be put in their place. The furnace should then be stoked and made ready for the next cupellations. By the time the furnace is ready, the cupels will be ready also. There should be no unnecessary handling of the cupels once they have been placed in the muffle. The cupellation temperature for gold is an orange-red heat, or perhaps a little hotter. Beginners who are apt to overheat their furnaces should avoid a heat which can properly be called yellow. Dr. T.K. Rose, note, in Limits of Accuracy Attained in Gold Bullion Assay, Transactions of the Chemical Society 1893, end note, has determined the temperature of a muffle during the cupellation of gold-silver alloys at the Royal Mint. In one muffle the temperature ranged from 1065 degrees to 1095 degrees centigrade. The lower temperature was, of course, in the front of the muffle. In another it ranged from 1022 degrees to 1062 degrees, and here the muffle appeared to the eye decidedly cooler than usual. The alloy left after cupelling was made up of 1 part of gold to 2½ parts of silver, and was fused at 952 degrees. Hence the usual temperature of cupellation was, say, 120 degrees or 130 degrees above the melting point of the residual metals. To obtain some real knowledge as to the meaning of these figures, the student should prepare pointed pieces of the following metals: silver, which melts at 945 degrees, gold, which melts at 1035 degrees, and an alloy half silver half gold, which melts at 990 degrees. These should be placed on clean cupels in a muffle almost entirely closed. The temperature should be very slowly raised, and the appearance of the muffle when each metal begins to melt should be carefully noted. The cupelling temperature in Dr. Rose's experiment was as much above the melting point of gold as this is above that of the silver-gold alloy. The finish of the cupellation of gold or gold-silver alloys is practically the same as with pure silver. There is the same thinning out of the litharge into a luminous film which becomes iridescent before the brightening. But the danger of spurting decreases as the proportion of gold becomes greater, and disappears when the gold is much over 30%. Nevertheless, it is well to let such buttons become solid, undisturbed and protected from draughts, in the body of the muffle. This means closing the muffle and allowing the furnace to cool down somewhat before withdrawing the cupels. Buttons solidified in this way are more malleable than when they are withdrawn promptly on the finish of cupellation. This is important with large buttons, as in a bullion assay. On the other hand, very small buttons, especially such as have to be measured rather than weighed, should be withdrawn as soon as the luminous film has disappeared. For when this is done, the button can be loosened from the cupel by merely touching it with the point of a pin, and is then safely and easily transferred to a watch glass by touching it with the head of a pin which has been moistened. It adheres to this, and if the pin is not too wet, comes off at once on touching the glass, or in any case will do so on gentle warming. Molten gold with little or no silver has a peculiar colour which is easy to recognize. It is more globular than a button of silver of the same size would be, and it shows less adhesion to the cupel. Just after becoming solid it glows beautifully, and this is so marked that it is a valuable help in finding the position of a button when it is more than ordinarily minute. If the button left from cupellation is yellow, it is at least half gold, and a rough guess as to the proportion of gold may be made from its yellowness. The rest of the metal is generally silver. The presence of platinum, or one of the platinum group of metals, makes the surface of the button dull and crystalline. The native alloy of osmium and iridium does not alloy with gold, however, but falls to the bottom of the molten metal. It shows itself in the subsequent parting as a black spot or streak on the undersurface. The buttons are removed from the cupel with a pair of pliers, and then brushed to remove adherent litharge and bone ash. Some assayers advise cleaning by dipping in warm dilute hydrochloric acid, followed by washing in water and drying. The button is next weighed. When the quantity of silver obtained is not required to be known, the weighing may sometimes be omitted. The next operation in either case is parting, either with or without a previous inquartation. The loss of gold in cupellation is by no means always inconsiderable. In 3 cupellations of 1 gram of gold with 20 grams of lead, made purposely at a very high temperature, the cupel absorbed 6.04, 6.20 and 6.45 milligrams of gold. Hence, at a high temperature there may easily be a loss of more than 0.5% of the gold. In 10 cupellations with the same quantities of gold and lead, but at an ordinary temperature, the gold recovered from the cupels varied from 1.37 to 1.92 milligrams, and gave an average of 1.59 milligrams. In round numbers, the cupellation loss of pure gold is 0.15%. But if the gold be alloyed with silver, the loss is diminished, as is shown by the following experiments. Gold, 0.3 gram, was cupelled with 10 grams of lead and varying amounts of silver, and the cupels were assayed for gold with the following results. Silver in the alloy 0.3 gram, gold in the cupel 0.47 milligrams. Silver in the alloy 0.6 gram, gold in the cupel 0.32 milligram. Silver in the alloy 0.9 gram, gold in the cupel 0.17 milligram. These, calculated on the 0.3 gram of gold, give the loss as 0.157, 0.107 and 0.057% respectively. The effect of copper, on the other hand, is to increase the cupellation loss, which, silver being absent, may from this cause rise to 0.3%, even when the temperature is not excessive. In the ordinary assay of gold-copper alloys, a constant weight of the alloy is always taken. Hence, as the weight of copper in a cupel charge increases, the weight of gold decreases. The silver, on the other hand, is always very nearly 2.5 times as much as the gold, whatever its quantity may be. But the cupellation loss is smaller with less gold and greater with more copper. And it so happens in these assays that these two opposites nearly neutralise one another. Mr. W. F. Lowe, note in Assaying and Hallmarking at the Chester Assay Office, W. F. Lowe, Journal of the Society of Chemical Industry, September 1889, end note, found the gold recoverable from the cupels on which 20 grains of gold bullion had been treated varied only between 0.014 and 0.015 of a grain, i.e. from 0.07 to 0.075% of the bullion treated, although the quality of the bullion varied from 9 to 22 carat. Note, fine or pure gold is 24 carat. 9 carat gold therefore contains 9 parts of gold in 24 of the alloy. 18 carat gold contains 18 parts of gold in 24, and so on. End note. But in the poorest bullion there was only 7.5 grains of pure gold, while in the richest there were 18.3 grains, yet each lost on the cupel the same weight of gold, that is, 0.014 of a grain. When reckoned in percentages of the actual gold present, the losses are 0.187% and 0.076% respectively. The heavier percentage loss is mainly due to the increased quantity of copper. As with silver, so with gold, the predominant cause of the cupellation loss is the solution of the metal in the molten litharge which passes into the cupel. 3 lots of 1 gram of gold cupelled each with 20 grams of lead repeatedly, so as to make 13 cupellations in all, lost in actual weight 35.72 milligrams. The gold recovered from the cupels amounted altogether to 34.56 milligrams. This shows that, compared with the absorption by the cupel, the other causes of loss are inconsiderable. The loss of gold by volatilisation is, however, a real one. The dust from the flues of assay furnaces has been tested on several occasions, and found to contain gold, though in small quantity. Thus Mr. Lowe found 0.073% of silver and 0.00033% of gold in such a material. The lead volatilised from a gold bullion assay would need to be 10 times as rich as this to account for a loss of gold equal to the 100th part of a milligram. Dr. Rose, in the paper already quoted, believes that on a 0.5 gram charge of standard bullion, the loss from volatilisation is not less than 0.025 nor more than 0.05 of a milligram of gold. By way of conclusion, it may be said that the cupellation loss of gold is about 0.07%, and that it is largely met or even over-corrected by a compensating error due to silver retained in the gold after parting. Inquartation. The method of separating the gold from the silver in gold-silver alloys by boiling with nitric acid does not act equally well in all cases. An alloy half silver, half gold, rolled to thin sheet and boiled for half an hour with nitric acid, may still retain more than 2/3 of its silver. An alloy of 1 part gold and 1.7 parts of silver gives up practically the whole of its silver under similar treatment. The gold is left in a coherent though easily broken sheet, retaining the shape of the original alloy. The gold thus left is quite spongy and porous, so that the acid can penetrate into its innermost portions. But if the silver is in large excess in the alloy, the removal of the silver is less complete, and the residual gold, instead of holding together in a form easy to manipulate, falls to a powder which requires care and time in its treatment. The older assayers, therefore, added silver to their gold in such proportion that the alloy for parting should be 1/4 gold to 3/4 silver. This operation they called inquartation. The modern practice is to aim at getting an alloy with 2½ parts of silver and 1 part of gold. In gold bullion assays this proportion should be obtained with fair exactness, and in the parting of such gold buttons as are obtained in assaying ores it is well to aim at this proportion, though absolute precision is not a matter of importance. If the button left on cupelling the lead from an assay of an ore appears white, it is best to assume that it already contains at least a sufficiency of silver, in the absence of any knowledge to the contrary. This will be true in almost all cases. But if on parting it does not lose at least 2/3 of its weight, this indicates that the assumption was not justified, and also what quantity of silver must be added to the button before again attempting to part. Generally the fault will be in the other direction. The silver will be in excess, and the gold will break up and demand a very careful treatment. If, however, such a button is yellow, then from its weight and depth of colour a rough estimate can be made of how much gold is contained in it. Silver must be added to make the total weight 3½ times as much as that of the gold supposed to be present. Thus, if the button weighs 10 milligrams and is supposed to contain 8 milligrams of gold, then 8 multiplied by 3½ is 28. The button must in such case be made up to 28 milligrams by adding 18 milligrams of silver. In judging of the quality of the gold button, no ordinary error will very seriously affect the result. If, in the example just given, the quantity of gold present was really 7 or even 9 milligrams of gold, the resulting alloy would still have been suitable for such partings. In fact, in routine assays, where the quantity as well as the quality of the gold is known within fair limits, it is often the custom to add the silver for inquartation to the lead during the first cupellation. But in the assay of rich gold alloys, such approximate work will not do. If the composition is not already known with a fair degree of accuracy, preliminary assays must be made. Weigh up 2 lots of 100 milligrams of the alloy and wrap each in 3 grams of lead. To one, add 300 milligrams of silver. Cupel both. The button containing the added silver must be flattened and boiled with 15 cc of nitric acid, and the resulting gold must be washed, dried, ignited and weighed. This, in milligrams, gives directly the percentage of gold. The weight of the other button gives the percentage of gold and silver. The difference between the two gives the percentage of silver. The rest will perhaps be copper. The composition of the alloy being known, or having been determined as just described, the calculation of how much silver must be added is fairly simple. The following is an example. Suppose the bullion contained 92% of gold, 1% of silver and 7% of copper, and that 0.5 of a gram of it is to be taken for an assay. The 0.5 of a gram then will contain gold, 0.460 of a gram, silver, 0.005 of a gram, copper, 0.035 of a gram. But the total silver required is 0.46 of a gram times 2.5. This equals 1.15. Allowing for the 0.005 of a gram of silver already present, 1.145 grams of silver must be added. The silver is incorporated with the gold, and at the same time the copper is eliminated by cupelling with sheet lead. How much sheet lead must be used will depend partly on how much bullion is taken, partly on how much copper it contains. 4 grams of lead will do for a 0.5 gram charge, and for a 0.3 gram charge 3 grams may be used. But with 20% of copper, these amounts should be doubled. With 40% of copper, they should be trebled, and with over 60% of copper, 4 times as much lead should be used. For small buttons of gold, as little lead as may be relied on to start cupelling may be taken. The lead may conveniently be in the form of little cups, made by folding lead foil on a piece of glass rod. With a large number of bullion assays systematically worked and checked, a simple plan would be to always use the quantity of lead required by the alloy containing most copper which turns up for assay. This weight cut out of lead foil would be kept in stock, folded into little bags ready to receive the bullion and silver. The silver used for inquartation must, of course, be free from gold, and is best prepared by the assayer who is to use it. See page 66. Reader's note in section 6 of these recordings, on reagents, salts, etc. End reader's note. It should not be in long strips or angular pieces likely to perforate the lead in which it is folded. When wrapped in the lead, it should be in the middle and should make as compact a parcel as possible. Each little parcel, as completed, should be placed on a tray in its properly numbered compartment. Its position here should correspond to that it will occupy in the muffle and eventually in the cupel tray. The cupellation must be made with all the requisite precautions. A good, smooth, malleable button is needed for the next operation, which is known as flatting. Flatting. Small buttons, such as are got in assaying most gold ores, are placed on a polished steel anvil and flattened by 1 or 2 blows with a hammer. The flattened discs are heated to dull redness on a clean cupel and are then ready for parting. Somewhat larger buttons may be similarly treated, but they should be annealed, i.e. heated to redness and allowed to cool, during the flattening. The silver-gold alloy left from the cupellation is soft and bends like lead, but after hammering or rolling it becomes harder, gets a spring in it like a piece of mainspring, and cracks or splits somewhat easily. There should be no cracks or stripping or even roughness on the flattened metal, since such defects may cause the loss of small particles either during the flattening or in the subsequent treatment with acid. The softness of the metal is restored by heating. In bullion assays, the flatting of the buttons requires care and practice for its skillful working. The strips of alloy for parting should be of uniform thickness and condition, so that the action of the acid shall be equal in all cases. The button is taken from the cupel, cleaned, and placed on the anvil. It is then struck a heavy blow which widens it to about 3/4 of an inch in diameter. This blow is followed by 2 others, one a little in front, the other behind, which lengthen the disc and give a very blunt roof-like slope to its upper face. It should then be annealed. This may be done by putting it in a just red-hot scorifier heated in a muffle. It very soon attains the right heat, and may then be transferred to a cold scorifier. The hot scorifier should be put back into the muffle. The softened disc is then taken to the rolls. Figure 45. Reader's note: the rolls consist of two cylindrical polished steel rollers, one above the other. The rollers are about 1½ times as long as their diameter. They are supported horizontally in a heavy metal frame, with a handle at one side and a pair of cogs at the other side of the frame linking the movement of the two rollers. The exact position of the upper roller can be adjusted by screws at the top of the frame holding the two rollers. End reader's note. The rolls are loosened until the disc can be pressed between them. Looking through the interval between them, the rolls should appear exactly parallel. If they are not, one adjusting screw should be loosened and the other tightened until parallelism is obtained. The rolls are now turned, and the disc should be drawn through without any great effort. Beginners are apt to err by trying to do too much with one turn of the handle. It is easy to stop whilst the rolls are only just gripping the metal, and then to bring the disc back by reversing the action. If the disc was originally level and the rolls are parallel, the metal will appear as a strip which has been merely lengthened. If the rolls are tighter on one side, the strip will be bowed. The tighter side will correspond with the outer curve of the crescent. A mistake of this kind may be amended by passing the strip through the rolls the other way, so as to reverse the irregularity and so straighten the strip. The screw on the looser side should then be tightened until parallelism is obtained, after which more care should be taken to tighten the two screws equally. The rolling should be stopped when the strip is 3 or 4 inches long and of the thickness of an ordinary visiting card. The strip should be annealed during the rolling and again at the finish. The end of section 15. Section 16 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 9. Silver, Gold, Cyanides, Platinum, Mercury. Part 8. Parting. The thin sheet of metal is dropped into hot dilute nitric acid and boiled for 5 or 6 minutes after the brisk action of the acid on the metal has ceased. At this stage nearly all the silver has gone into solution as nitrate of silver, and the acid is charged with this salt. This acid is poured off, and the residual metal is again boiled for from 20 to 30 minutes with a second lot of stronger acid. This leaves the gold almost pure, though it may still retain from 0.05 to 0.1% of silver. Treatment with the first acid only would probably leave 3 or 4 times as much. The nitric acid used should be free from hydrochloric, sulfuric, iodic and telluric acids. In testing it for the first of these, add nitrate of silver and dilute with distilled water. There should be no turbidity. In testing for the others, evaporate 3 lots in dishes over a water bath. Test one for sulfates by adding water and barium chloride. Test another for iodates by taking up with a little water, adding a few drops of starch paste, and then dilute sulfurous acid solution, a little at a time. There should be no blue colour. Test the third for tellurium by heating with 1 cc of strong sulfuric acid until dense fumes come off. Allow to cool considerably. A piece of tin foil added to the warm acid develops a fine purple colour if only a trace of tellurium is present. The presence of lower oxides of nitrogen, which impart a brown colour to the acid, is objectionable. They, however, are removed by boiling the diluted acid before using it for parting. It is usual to keep a stock of the acid suitably diluted to the 2 strengths required for the parting. These are known as the parting acids. The first parting acid is the weaker and is used in the first attack on the metal. The specific gravity generally recommended for it is about 1.2. It may be prepared either by diluting the strong acid with about its own volume of distilled water, or by suitably diluting the second parting acid, which has been already used in an assay. The small proportion of silver this contains is not harmful for this purpose. The second parting acid has a specific gravity of about 1.3 and may be made by diluting the strong acid with half its volume of distilled water. Parting in flasks. Flasks are most convenient for the larger partings, as in bullion assays, and should always be used for this purpose unless some of the special parting apparatus, like that used in mints, is available. Many assayers use flasks, though of a smaller size, for the ordinary partings in assaying gold ores. The flasks are either bulbs with long necks, which ought to be heated on rose burners of special construction, or they are small flat-bottomed conical flasks which may be conveniently heated on a hot plate and are in this respect much easier to deal with in general work. The following instructions apply to the parting of an alloy containing a few decigrams of gold, together with the proper proportion of silver. The strip from the rolls, after being softened by annealing, is folded on itself on a glass rod into a roll or cornet. It should be so plastic that it will retain the shape thus given it, and not spring open on removing the pressure of the fingers. About 50 cc of the first parting acid are placed in a 6-ounce conical flask and heated to boiling. The flask is then withdrawn and tilted a little to one side, whilst the cornet is cautiously dropped into it. There will be a sudden issue of hot vapours, and a prompt withdrawal of the hand is advisable. The flask is replaced on the hot plate and the acid is kept boiling for 10 or 15 minutes. The flask is then withdrawn and the acid diluted with about an equal volume of distilled water. If the flask has a thick glass band around its neck a little way down, note, the mouth of the flask must not have a rim around it, end note. Care must be taken to use hot water, for any sudden chill will certainly crack the flask where it is thus thickened. The liquor is carefully decanted into a clean beaker and is then thrown into a jar marked waste silver. About 40 cc of the second parting acid, heated to boiling, is then poured into the flask, which is then replaced on the hot plate. The boiling is continued for 15 or 20 minutes, or even longer. At this stage, bumping has to be specially guarded against. After a little experience, it is easy to see when this is imminent, and the flask should be withdrawn to a cooler part of the plate. It is better to prolong the heating at a temperature below boiling than to run the risk of disaster. Some of the older writers, however, are rather insistent on vigorous boiling with large bubbles. The addition of a small ball of well-burnt clay of about the size of a pea has been recommended, as it lessens the tendency to irregular and dangerous boiling. At the end of the treatment with the second acid, the flask is withdrawn from the plate and the acid is diluted with an equal volume of distilled water. The liquor is carefully decanted into a beaker and then poured into a jar or Winchester marked acid waste. It serves for making the first parting acid. The flask is then washed twice with hot distilled water. The washings must be carefully decanted from the gold. The flask is then filled with water. A parting cup, size B, is then placed over its mouth, like a thimble on the tip of a finger. This cup is of unglazed porous earthenware, of such texture that it absorbs the last few drops of water left on drying, and with a surface to which the gold does not adhere even on ignition. The gold should fall out cleanly and completely on merely inverting the cup over the pan of the balance. The flask and cup are then inverted so that the flask stands mouth down in the cup. A little of the water from the flask flows into the cup, but only a little. The gold falls steadily through the water into the cup. When time has been allowed for even the finest of the gold to have settled into the cup, the flask is removed. This is easiest done under water. The cup with the flask still resting in it is dipped under water in a basin. As soon as the neck of the flask is immersed, the crucible can safely be drawn away from under it and then lifted out of the water. The flask should not be taken away first, for the rush of water from it may easily sweep the gold out of the cup. The water in the cup is then drained off and the cup is dried at not too high a temperature, for if the last drop or two of water should boil, there is danger of spattering the gold out of the crucible. When it is dry, the cup is heated on a pipe clay triangle over a Bunsen burner, or on a slab of asbestos in a muffle to a dull red heat. This brings the gold to colour. That is, the loose, tender, dark-coloured gold becomes bright yellow and coherent, and is in a state fit to be transferred to the balance and weighed. All unnecessary transferences must be avoided. As soon as the cup is cool, it may be inverted over the pan of the balance, when the gold will fall out cleanly, or, at the worst, a gentle tap with the finger will be sufficient to detach it. Parting in test tubes, or in the smaller conical flasks, is used in the assay of gold ores of ordinary richness. The work is exactly like that just described in all its main features. Generally speaking, much less acid will be used. For example, in test tubes and for small buttons, 3 or 4 cc of each acid is quite enough. Again, the action need not be so prolonged. 10 or 15 minutes in each acid is sufficient. So too, the heating may be less. It is very convenient to support the test tubes in a water bath, or merely to rest them in a beaker of boiling water, and there is no serious objection to doing this. A smaller parting cup should be used. The A size is suitable. The button, on the other hand, should be beaten thinner than is needed for the larger partings. If the silver should be in excess and the gold becomes much broken up, ample time should be given for subsidence from the test tube or flask into the parting cup. Parting in glazed crucibles or dishes. This method of working has the advantage that there is no transference of the gold until it is placed on the pan of the balance. On the other hand, in the boiling, more care is required in adjusting the temperature. The following instructions apply to the treatment of very small buttons, to which the method is more particularly applicable, but very little modification is needed for the treatment of larger buttons. The smallest sized Berlin crucibles answer admirably. They should be cleaned by treatment with hot and strong sulphuric acid, followed by washing in distilled water. The comfort and ease of working mainly depends on the thoroughness of this cleaning. The crucible, 1/3 full with the first parting acid, is heated on the hot plate until the acid is almost boiling. The flattened and annealed button is dropped into it, and the heating continued with, at most, gentle boiling for a few minutes. The crucible is then filled with distilled water, which cools it enough for easy handling, and when the gold has settled, the liquor is poured off along a glass rod into a clean beaker. Any greasiness of the crucible makes itself felt here and is very objectionable. The crucible is then 1/3 filled with the second parting acid, and the heating resumed, care being taken not to raise the temperature too high. This should be continued much longer than before, say for 5 or 10 minutes, or even longer according to the size of the button. Distilled water is again added, and when it is drained off, the washing with distilled water is twice repeated. It will not be possible to drain off the last drop of water, but if the gold is coherent, the crucible can be so inclined that this drop drains away from the gold, in which case the drying can be done rapidly. The boiling of the water will do no harm, but when the gold is much broken up, it will collect in the middle of this drop, and the drying must be done gently, best by putting the crucible in a warm place. When dry, the crucible is heated till the gold changes colour, but the heat must be kept well below redness. When cold, the gold is transferred directly to the pan of the balance. With minute specks of gold, which will require measuring, it is best to put a small piece of lead foil, say 0.1 gram, in the crucible over the gold, and then heat the crucible to above redness over a blowpipe. Whilst the lead is oxidizing, it is easily swept round in a bath of molten litharge by merely tilting the crucible. In this way, any separated specks of gold can be taken up with certainty. When the worker is satisfied that the lead has had ample opportunity for taking up the gold, the lead must be kept in one place and the heat slowly lowered. By this means the button becomes supported in comparatively pure litharge, and when solid can be picked out quite easily with a pair of pliers, and in a very clean condition. The lead button is then cupelled on a very fine cupel, as already described. The method of working last described destroys the crucible. If the gold is not quite so small, this may be avoided. A small piece of lead foil should be hammered out until it is perfectly flexible. It is then shaped into a tray and the gold is transferred to it. The lead is then folded over with the help of 2 pins and cupelled. If the crucible shows a black stain on heating, it is because some silver remains through bad washing. It shows poor work and the assay should be repeated. The silver retained in the gold after parting is, in bullion assays, an important matter. It is roughly equal to the loss of gold due to absorption by the cupel. Mr. Lowe, working on 0.5 of an ounce of gold, obtained by parting in assaying bullion, found it to contain 0.123% of silver. Dr. Rose, in some special assay pieces, found by a less direct method of assaying from 0.06 to 0.09% of silver. The proportion of silver retained varies in a marked way with the proportion of gold to silver in the alloy before parting. It is generally stated that the retained silver is least when this proportion is 1 to 2.5, and more or less silver than this leads to a less pure gold after parting. Platinum in an alloy being parted is dissolved along with the silver, either altogether or in part. It imparts a straw yellow colour to the parting acid. Palladium gives an orange colour to the acid. The loss of gold by solution in the acid during parting is small, but easily demonstrable. On a 500 mg charge of bullion, it may amount to from 0.05 to 0.15 of a milligram, i.e. from 0.01 to 0.03%. It is due to gold actually dissolved and not merely held in suspension. Assaying with checks. Surcharge. It will be seen from what has been stated that the errors in gold parting are of 2 kinds. That is, 1. A loss of gold on the cupel, and to a less extent by solution in the acid, and 2. An apparent gain of gold due to the retention of silver in the parted material. Both errors are small, and as they are of an opposite character, they tend to neutralise each other. Hence they are altogether without effect on the accuracy of the assays of ores when the total gold is reckoned in milligrams. And even with the larger amounts present in bullion assays, their influence is so small that an uncorrected result is still fairly accurate. The resultant error would not be more than 1 part in 2 or 3,000. It is customary to report the purity of bullion, or its fineness as it is called, in parts per 1,000 of bullion. The sum of the errors of an assay, which is called the surcharge, is reported in the same way. Thus, a surcharge of plus 0.3 means that the gold, as weighed, was 0.3 of a part per 1,000 more than the gold actually present. But a surcharge of minus 0.3 means that on the whole there was a loss of 0.3 of a part per 1,000 in the assay. Speaking roughly, the retained silver will vary with the weight of gold present. If one alloy contains twice as much gold as another, the retained silver will be about twice as much also. On the other hand, as already explained, the cupellation loss on the poorer alloy is as much as, or even more than, with the richer one, because of the copper, etc. present. With rich gold alloys, the silver more than compensates for the loss, and the surcharge is positive, but with poorer alloys the loss is greater, and the surcharge is negative. In mints, and places where bullion assays must be made with the highest attainable accuracy, the surcharge is determined by experiment, and the proper correction is made in the reports on the bullion. This is done by making assays of gold of the highest degree of purity, alongside of those of the bullion whose quality has to be determined. These checks are so made that they do not differ from the actual assays in any material point. Thus, being of the same quality and weight, and undergoing exactly the same treatment, they may reasonably be expected to have the same surcharge as the assays they imitate. Suppose the bullion being assayed varies only a little up or down from 900 gold and 100 copper in the 1,000, and that 0.5 of a gram of it is used in each assay. A quantity of gold differing only a little from 0.450 of a gram would be very exactly weighed and placed with 0.050 of a gram of copper in the same weight of lead as is being used in the other assays. It would be cupelled, parted, etc., as nearly as possible under the same conditions as the actual assays. Suppose the pure gold weighed 0.45016 of a gram, and the parted gold weighed 0.45025 of a gram. The gain in weight, 0.00009 of a gram, would be deducted from the actual assays. A surcharge correction is never applied except to bullion of the same quality as that represented by the check assay it was calculated from. It is evident that unless the gold is of the highest degree of purity, these check assays will introduce an error almost equal to that which it is designed to remedy. Moreover, to work the checks to the greatest advantage, a very systematic and uniform method of working must be adopted. Parting in special apparatus. One plan for obtaining greater uniformity is to stamp each cornet with a number for purposes of identification, and to treat several, including one or more check assays, in the same acid contained in a beaker. All the assays under these conditions evidently receive precisely the same acid treatment. Such a plan can, of course, only be adopted where there is no risk of the gold breaking up during the parting. An improvement on this is to have a porcelain basin about 8½ inches in diameter and with a capacity of about 1½ litres. Note: see Assaying and Hallmarking at the Chester Assay Office by W. F. Lowe, Journal of the Society of Chemical Industry, September 1889. End note. It is provided with a porcelain cover with 30 numbered holes, through which tubes dip into the acid. The cover is removable. The tubes are like test tubes and are supported by the cover. Their bottoms are perforated with holes or slits. The acid is placed in the basin and boiled over a flat burner. It enters the tubes through the slits. The cornets are placed each in its proper tube. When the boiling is finished, the cover with the tubes is lifted, and at the same time the acid drains back into the basin. A dip into a basin of distilled water washes at one operation all 30 assays. The cover is then put on a basin containing the stronger parting acid, which is already boiling. This boiling is continued for half an hour. The cover with the 30 cornets is then lifted out from the acid and dipped 2 or 3 times in distilled water to wash off the last traces of acid. To transfer the cornets from the tubes to the porous cups, the whole of the tube must be dipped under the water. Otherwise, the operation is exactly as when working with test tubes. A still simpler method of working is to use small platinum cups provided with fine slits which admit the acid but retain the gold. Note: Percy, Metallurgy of Silver and Gold, page 263. End note. A number of these, say 60, are supported on a platinum tray. The parting acids are boiled in platinum dishes under a hood, and the 60 cornets, each in its proper cup, are placed in the acid all at once. The tray carrying the cups is provided with a handle suitable for this purpose. After a proper boiling, the tray is lifted out of the weaker acid into the stronger one, where it undergoes the second boiling. It is next dipped several times in distilled water, and lastly, after a gentle drying, it is raised to an annealing temperature, which must not be too high for fear of the gold sticking to the platinum. After cooling, the cornets are transferred from the platinum cups directly to the pan of the balance. Here all 60 cornets have exactly the same treatment, and the checks may be compared with great exactness with the other assays accompanying them. There is, too, a great saving of labour. Note: see also The Assaying of Gold Bullion by C. Whitehead and T. Ulke, Engineering and Mining Journal, New York, February 12th, 1898. End note. Silver, etc. in gold bullion. The base metals are generally determined by cupelling 0.5 of a gram of the alloy with 5 grams of lead, the loss in cupellation having been allowed for by any of the usual methods. Note: see page 104. End note. Reader's note: in section 10 of this recording. End reader's note. The gold and silver contents are given. By deducting the gold, the proportion of silver is obtained. The silver is generally determined by difference in this way. If it is desired to dissolve out the copper, silver, etc., and to determine them in the wet way, the gold must first be alloyed with a sufficiency of some other metal to render it amenable to the attack by acid. Cadmium is the metal generally recommended, and the alloy is made by melting together a weighed portion of the gold with 5 or 6 times its weight of cadmium in a Berlin crucible and under a thin layer of potassium cyanide. Lead with gold or silver. Large quantities of lead carrying gold and silver are sold to refiners in bars weighing about 100 pounds each. The assay of these alloys presents no special difficulties, but the sampling of them is a question which may be profitably discussed. Note: consult Percy's Metallurgy of Silver and Gold, page 172. A.C. Corday, Transaction of the Institute of Mining and Metallurgy, volume 6, page 29. G.M. Roberts, Transactions of the American Institute of Mining Engineers, Buffalo Meeting, 1898. J. and H. S. Pattinson, Journal of the Society of Chemical Industry, volume 11, page 321. End note. A molten metal may be conceived to have all the physical states observed in ordinary liquids, although these cannot be actually seen owing to its opaqueness. There is no doubt that pure lead at a temperature only a little above its melting point can contain a large proportion of gold in such a manner that it may, in a figurative way, be spoken of as a clear solution. Any small portion withdrawn from the molten metal would afford a perfect sample. The same would be true of any pure alloy of lead and silver in which the silver does not exceed the proportion of 2.5%. Note: Haycock and Neville, Journal of the Chemical Society, 1892, page 907. End note. On the other hand, if the molten metal contains much more than 0.5% of zinc, more than 0.1% of copper, or a larger quantity of silver, it may be likened to a turbid liquor. The resemblance holds good so far that if the molten lead be further heated, whereby its solvent power on the added metal is increased, the turbidity will disappear, or at least be considerably diminished. A portion taken at random from such a molten metal may or may not give a good sample. The suspended insoluble matter will tend to concentrate itself in the upper or lower parts of the liquid according to whether it is heavier or lighter than it, and this separation may occur with extreme slowness or with fair rapidity. However, it is generally agreed that in the case of such alloys as occur in practice, samples taken in this way are quite satisfactory, and are the best obtainable. The precautions insisted on are that the lead shall be made as hot as practicable, that it shall be stirred up at the time of taking the sample, and that the portion withdrawn shall be taken out with a ladle at least as hot as the molten metal. The further precaution that if any dross be on the surface of the metal, it shall be skimmed off and separately sampled and assayed is almost too obvious to require mention. An alternative and perhaps better way of taking the sample is to withdraw portions at equal intervals from the stream of metal while the pot is being emptied. Equal weights taken from these portions and mixed, by melting or in some other way, give a fair sample of the whole. In addition, separate assays of each portion will show to what extent the metal lacks uniformity in composition. For example, samples taken at the beginning, middle, and end of a run gave the following results in ounces of silver per ton: 475, 472, 466, showing an average result of 471 ounces. 15 fractions taken at regular intervals during the same pouring ranged from 475 ounces to 464 ounces. The average result was 469.8 ounces. The same lead cast into bars and sampled by sawing gave an average of 470 ounces. Note: G.M. Roberts. End note. In another case, samples drawn at the beginning, middle, and end of a run gave 1,345 ounces, 1,335 ounces, and 1,331 ounces. Note: A.C. Clodet. End note. The mean result in such cases is always a reasonably safe one, but evidently where the metal varies a good deal, it is safer to take more than 3 dips. Imagine such lead run into moulds and allowed to become solid as bars. The difference between bar and bar would not be greater than that between corresponding dip samples, but in each bar the distribution of the silver and gold is very seriously affected during solidification. Chips taken from the same bar of auriferous lead may show in one place 23 ounces of gold to the ton, in another 39 ounces. Similarly with silver, they may vary as much as from 900 ounces to 1,500 ounces to the ton. This rearrangement of the constituents of a bar takes place while the lead is partly solid, partly liquid. The most useful conception of such half-solidified metal is that of a felted, spongy mass of skeleton crystals of comparatively pure lead, saturated with a still fluid, enriched alloy. If the solidification of an ingot of impure tin be watched, it will be evident that the frosted appearance of the surface is due to the withdrawal of the fluid portion from a mat of crystals of purer tin which have been for some time solid, and a contraction of the mass. The shrinking of the last part to become solid is further shown by the collapse of the surface of the ingot where weakest, that is, a furrow is formed on the flat surface. In other cases of fused metal there is expansion instead of contraction in this final stage of the solidification, and the enriched alloy then causes the upper face of the ingot to bulge outwards. There are other causes affecting the redistribution of metals throughout the ingot. There can be no general rule of wide application showing which part of a bar is richest and which poorest in the precious metals. This will depend on the quantities of gold or silver, on the quantities and kinds of other metals present, and on the manner of casting. The student is advised to consult Mr. Claudet's paper, which has been already referred to. The best method of sampling such bars is to melt them all down, and to take a dip sample of the molten metal in one or other of the methods already described. According to Mr. Claudet, this should be done in all cases where the gold exceeds 1 or 2 ounces, or where the silver exceeds 200 ounces to the ton. If during the melting down some dross has formed, this must be skimmed off, weighed, and separately sampled and assayed. The clean lead also must be weighed, sampled, and assayed. The mean results must be calculated. Thus, 14 tons 500 weights of clean lead, assaying 32 ounces to the ton, will contain 456 ounces of silver. 1500 weight of dross, assaying 20 ounces to the ton, will contain 15 ounces of silver. The 15 tons of lead and dross will contain 471 ounces of silver, or 31.4 ounces per ton. Of the methods of sampling which avoid melting the bars, that known as sawing is the only one which is thoroughly satisfactory. In it the bars are brought to a circular saw having fine teeth, and are sawn across either completely or halfway through. In this way a quantity of lead sawdust is obtained, say 1 pound or so from a bar, which represents exactly the average of the bar along the particular cross-section taken, and approximately that of the whole bar. A bar of lead which by dip assay gave 334 ounces to the ton gave on 3 transverse sections 333 ounces, 335 ounces, and 331 ounces. The variation may be greater than this, but with a large number of bars, where each bar is cut across in as far as possible a different place, these variations tend to neutralize each other, and a good sample is obtained. 200 or 300 weight of sawdust may be obtained in this way. This is thoroughly mixed and reduced by quartering in the usual way, or by a mechanical sampler. A sample of 2 or 3 pounds is sent to the assayer. This, being contaminated with the oil used in lubricating the saw, is freed from it by washing with carbon bisulfide, ether, or benzene, and dried. Then, after mixing, 100 to 200 grams of it are carefully weighed and placed in a hot crucible, the heat of which should be sufficient to melt all the lead. The molten lead should not be overheated, and should show no loss due to the melting. The removal of the oil may have decreased the weight by perhaps 0.5%. If the lead gives dross on heating, it may be melted under 10 or 20 grams of potassium cyanide, which prevents the formation of dross. Samples are sometimes taken with a drill, gouge or chisel, though no method of this kind is quite satisfactory. One plan adopted is to use a punch, which when driven into the bar gives a core or rod of metal about half as long as the bar is thick, and about 1/8 of an inch across. With 5 bars side by side, it is customary to drive in the punch at one end on the first bar, and at the opposite end on the last one, and on the others in intermediate positions, in such a manner that all the holes will be along a diagonal of the rectangle enclosing the bars. The bars are then turned over, and similar portions punched out through the bottoms of the bars and along the other diagonal. Or one set of 5 may be sampled along the top, and the next set along the bottom of the bars. Silver and gold present in bars of copper are subject to the same irregularity of distribution as in lead. The sampling of such bars is guided by the same principles. Note: the sampling of argentiferous and auriferous copper by A. R. Ledoux, Journal of the Canadian Mining Institute, 1899. End note. End of section 16. Section 17 of A Textbook of Assaying for the Use of Those Connected with Mines, by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 9. Silver, Gold, Cyanides, Platinum, Mercury. Part 9. Cyanides. The cyanides ought, perhaps, to be considered along with the chlorides, bromides, and iodides in Chapter 15. But they are treated here because they owe their importance to their use in the extraction of gold, and because their determination has become a part of the ordinary work of an assayer of gold ores. Formerly the cyanide most easily obtained in commerce was potassium cyanide, and it was generally sold in cakes which might contain as little as 40% or as much as 95% of the pure salt. It became customary to express the quality of a sample of commercial cyanide by saying it contained so much % of potassium cyanide. The commercial product now made by improved methods of manufacture is actually sodium cyanide, but is called potassium cyanide, probably with the words double salt on the label. It contains cyanide equivalent to something over 100% of potassium cyanide, in addition to a large proportion of sodium carbonate and other impurities. What is wanted in most cases is merely a soluble cyanide, and it is a matter of indifference whether the base be sodium or potassium. But since 49 parts of sodium cyanide, note NaCN molecular weight equals 49, end note, are equivalent to 65 parts of potassium cyanide, note KCN molecular weight 65, end note, it is evident that a pure sample of sodium cyanide would contain cyanide equivalent to little less than 133% of potassium cyanide. Therefore, a sample of cyanide reported on in this way may be rich in cyanide and yet have much impurity. The commonest impurity in commercial cyanide is carbonate of sodium or potassium. This may be tested for by dissolving, say, 2 grams in a little water and adding barium chloride. There may be formed a white precipitate of barium carbonate which, if filtered off, washed and treated with acid, will dissolve with effervescence. Cyanate may be tested for in the solution from which the barium carbonate has been filtered, by adding a little soda and boiling. If cyanates are present, they decompose, giving off ammonia, which may be tested for in the steam, and yielding a further precipitate of barium carbonate. Note: NaCnO plus BaCl2 plus NaHO plus H2O yields NH3 plus BaCO3 plus 2 NaCl. End note. If the soda alone gave a further precipitate of barium carbonate, this may perhaps be due to the presence of bicarbonates. Alkaline sulfides may be present in small quantity in commercial cyanide. Their presence is shown at once when the sample is being tested for its strength in cyanide, inasmuch as the first few drops of silver nitrate solution produce at once a darkening of the liquor. A special test for sulfide may be made by adding a drop or two of solution of acetate of lead to 4 or 5 cc of soda solution, and adding this to a clear solution of the suspected cyanide. This will cause a black precipitate or colour if any sulfide is present. The cyanides of the heavier metals combine with the alkaline cyanides to form double cyanides. Some of these, ferrocyanide and ferricyanide of potassium, for example, have such characteristic properties that the fact that they are cyanides may be overlooked. Others, such as potassium zinc cyanide, K2ZnCy4, have much less distinctiveness. They behave more or less as a mixture of two cyanides, and are, moreover, so easily decomposed that it may be doubted if they can exist in dilute alkaline solutions. In reporting the cyanide strength of a cyanide liquor as equivalent to so much % of potassium cyanide, there is a question as to whether the cyanide present in the form of any of these double cyanides should be taken into account. It must be remembered that the object of the assay is not to learn how much of the cyanide exists in the solution as actual potassium cyanide. Reporting the strength in terms of this salt is a mere matter of convenience. What is really desired is to know how much of the cyanide present in the liquor is free or available for the purposes of dissolving gold. Everyone is agreed as to the exclusion of such cyanides as the following: potassium ferrocyanide, K4FeCy6, potassium ferricyanide, K3FeCy6, potassium silver cyanide, KAgCy2, and potassium aurocyanide, KAuCy2, and the double cyanides with copper or nickel. But with cyanide liquors containing zinc, the position is less satisfactory. One method of assay gives a lower proportion of cyanide when this metal is present, and the loss of available cyanide thus reported depends, though in a fitful and uncertain way, upon the quantity of zinc present. The other method of assay reports as full a strength in cyanide as if no zinc were present. Unfortunately, using both methods and accepting the difference in the results as a measure of the quantity of zinc present, or at any rate of the zinc present as cyanide, is not satisfactory. It appears best to use the method which ignores the zinc, and to determine the amount of zinc by a special assay of the liquor for this metal. The cyanide present as hydrogen cyanide or prussic acid, HCy, is practically useless as a gold solvent. Hence any report on the strength of a cyanide liquor which assigned to this the same value as its equivalent of alkaline cyanide would be misleading. On the other hand, it is available cyanide, inasmuch as a proper addition of sodium hydrate would restore its value. Note: HCy plus NaHO yields NaCy plus H2O. End note. The question of the presence or absence of free prussic acid is involved in the larger one as to whether the cyanide solution has the right degree of alkalinity. The assay for cyanide should include the hydrogen cyanide with the rest. A rough test of the power of a cyanide liquor for dissolving gold may be made by floating a gold leaf on its surface and noting the time required for its solution. This test might perhaps be improved by taking, say, 20 cc of the liquor and adding 3 or 4 gold leaves, so that the gold shall always be in considerable excess. The liquor should not be diluted, as this will affect the result. It should be allowed to stand for a definite time, say at least 2 or 3 hours, or better, that corresponding to the time the liquor is left in contact with the ore in actual practice. The liquor should then be filtered off, and with the washings be evaporated in a lead dish, as in the assay of cyanide liquors for gold. Note: page 141. End note. Reader's note in section 14 of these recordings. End reader's note. The gold obtained on cupelling less any gold and silver originally present in the liquor, would be the measure of the gold dissolving power. The assay for cyanide by titration with silver nitrate. The determination of the quantity of a cyanide is made by finding how much silver nitrate is required to convert the whole of the cyanide into potassium silver cyanide, or one of the allied compounds. Note: 2KCN plus AgNO3 yields KAgCN twice plus KNO3. End note. It will be seen from the equation that 170 parts by weight of silver nitrate are required for 130 parts by weight of potassium cyanide. As already explained, it is customary to report the cyanide strength in terms of potassium cyanide, even when only the sodium salt is present. 1 gram of potassium cyanide will require 1.3076 of a gram of silver nitrate. The standard solution of silver nitrate is made by dissolving 13.076 grams of silver nitrate in distilled water and diluting to 1 litre. 100 c.c. of such a solution are equivalent to 1 gram of potassium cyanide. Note: if it be desired to make a solution so that 100 c.c. shall be equivalent to 1 gram of sodium cyanide, then 18.085 grams of silver nitrate should be taken for each litre. End note. The titration is performed in the usual way, running the standard solution of silver nitrate into a solution containing a known weight or volume of the material containing the cyanide. The finishing point is determined in one of two ways, both of which are largely used. In the first place, as long as there remains any free cyanide in the solution, the silver nitrate will combine with it, forming the double cyanide and yielding a clear solution. But as soon as all the free cyanide is used up, the silver nitrate will react with the double cyanide, forming silver cyanide, which separates as a white precipitate and renders the solution turbid. Note: AgNO3 plus KAgCy2 yields 2AgCy plus KNO3. End note. But in the second place, if potassium iodide is present in the solution, the excess of silver nitrate will react with it rather than with the double cyanide, and silver iodide will separate as a yellowish turbidity, which is easily recognized. Note: AgNO3 plus Ki yields AgI plus KNO3. End note. In working with pure solutions, the two finishing points give the same results, and this is true even when there is much difference in the degree of dilution. The finishing point with the iodide, however, has an advantage in precision. Moreover, it is but little affected by variations in alkalinity, which render the other finishing point quite useless. The great difference between the two is shown when zinc is present in the solution. In this case, when working without the iodide, the first appearance of a turbidity is less distinct. The turbidity increases on standing and, as a finishing point, is unsatisfactory. It can be determined with precision only by very systematic working and after some experience. The turbidity is due to the separation of an insoluble zinc compound. A most important point, to which reference has already been made, is that less silver nitrate is required to give this turbidity, and consequently a lower strength in cyanide is reported. On the other hand, as much silver nitrate is required to give the yellow turbidity due to silver iodide as would be required if no zinc were present. Unfortunately, the difference in the two titrations does not depend merely on the quantity of zinc present, as it is also influenced by the extent of dilution, the degree of alkalinity of the solution, and the quantity of cyanide present. In an experiment with 0.055 of a gram of zinc sulfate and 0.1 of a gram of potassium cyanide, the difference in the two finishing points was only 0.1 of a cc, whereas with 0.4 of a gram of potassium cyanide, the other conditions being the same, the difference was 1.5 cc of standard silver nitrate. On the assumption that all the zinc was present as potassium zinc cyanide, K2ZnCy4, the difference should have been 5 cc in each case. Again, repeating the experiment with 0.4 gram of potassium cyanide, but with 0.11 gram of crystallized zinc sulfate, the difference was 6.5 cc. That is, merely doubling the quantity of zinc increased the difference by more than 4 times. Hence it would appear better to use the method with the iodide and make a separate assay for the zinc. But since the student may be called on to use the other method, he is advised to practice it also. The assay without iodide. The standard solution of silver nitrate is placed in a small burette divided into tenths of a cc. 10 cc of the cyanide solution to be assayed is transferred to a small flask and diluted with water to about 70 cc. The silver solution is then run in from the burette with constant shaking of the flask, a little at a time, but somewhat rapidly, until a permanent turbidity appears. Since 1 cc of the silver nitrate solution corresponds to 0.01 gram of potassium cyanide, it also corresponds to 0.1% of this salt counted on the 10 cc of cyanide solution taken. The titration should be performed in a fairly good uniform light. The learner should practice on a fairly pure solution of potassium cyanide at first, and this may conveniently have a strength of about 1%. For practice with solutions containing zinc, make a solution containing 1.1 gram of crystallized zinc sulfate in 100 cc, and slowly add measured quantities of from 1 to 5 cc of this to the 10 cc of cyanide liquor before diluting for the titration. If a cyanide solution blackens on the addition of the silver nitrate, it contains sulfide. In this case, shake up a considerable bulk of the liquor with a few grams of lead carbonate, allow to settle, and make the assay on 10 cc of the clear liquor. If the cyanide liquor be suspected to contain free prussic acid, take 10 cc for the assay as usual, but before titrating add 0.1 or 0.2 gram of sodium carbonate. On no condition must caustic soda or ammonia be added. The difference between the results with and without the addition of carbonate of soda is supposed to measure the quantity of free prussic acid. If this has to be reported, it is best done as prussic acid equivalent to blank% of potassium cyanide. Suppose, for example, the difference in the two titrations equals 1 cc of standard silver nitrate. The prussic acid found would be equivalent to 0.1% of potassium cyanide. The assay with iodide. The standard solution of silver nitrate is placed in a burette divided into tenths of a cc. Take 10 cc of the cyanide liquor, which should previously have been treated with white lead for the removal of sulfides if these happen to be present. Transfer to a small flask. Add 3 or 4 drops of a solution of potassium iodide and 2 or 3 cc of a solution of sodium hydrate. Dilute to 60 or 70 cc with water. If much zinc is present, the soda may be increased to 20 or 30 cc with advantage. The standard solution should be run in somewhat rapidly, but a little at a time, so that the precipitate at first formed shall be small and have only a momentary existence. The titration is continued until there is a permanent yellowish turbidity. The most satisfactory and exact finish is got by ignoring any faint suspicion of a turbidity and accepting the unmistakable turbidity which the next drop of silver nitrate is sure to produce. This finishing point gives results which are exactly proportional to the quantity of cyanide present, and it can be recognized with more than ordinary precision, even in solutions which are not otherwise perfectly clear. Each cc of the standard silver nitrate solution corresponds to 0.01 gram of potassium cyanide, and if 10 cc of the liquor are taken for assay, this corresponds to 0.1%, or 2 pounds to the short ton, or 2.24 pounds to the long ton. As already explained, the result should be reported as cyanide equivalent to so much % of potassium cyanide. The following experimental results were obtained with a solution of potassium cyanide made up to contain about 1.2% of the salt. Effect of varying cyanide. The bulk before titration was in each case 60 cc. 2 cc of soda and 3 drops of potassium iodide were used in each case. Cyanide added 40 cc, silver required 47.0 cc. Cyanide 30 cc, silver 35.25 cc. Cyanide 20 cc, silver 23.5 cc. Cyanide 10 cc, silver 11.7 cc. Cyanide 5 cc, silver 5.8 cc. Cyanide 1 cc, silver 1.15 cc. Accepting the result for 40 cc as correct, the others are in very satisfactory agreement. Effect of varying dilution. The conditions were those of the 40 cc experiment in the last series, but varying amounts of water were used in diluting. Water added, none. Silver required, 47.0 cc. Water, 100 cc. Silver, 47.0 cc. Water, 200 cc. Silver, 47.0 cc. Water, 400 cc. Silver, 47.05 cc. Very considerable dilution, therefore, has no effect. Effect of varying soda. The conditions were those of the 40 cc experiment in the first series, except that varying amounts of soda solution were used. Soda added, none. Silver required, 46.95 cc. Soda, 10 cc. Silver, 47.0 cc. Soda, 30 cc. Silver, 47.0 cc. This alkali therefore has no prejudicial effect. Effect of ammonia. Soda causes turbidity in some cyanide liquors. With these it should be replaced by 2 or 3 cc of dilute ammonia with a gram or so of ammonium chloride. The following experiments with dilute ammonia show that larger amounts of this reagent must be avoided. Ammonia added, none. Silver required, 46.95 cc. Ammonia, 10 cc. Silver, 47.15 cc. Ammonia 30 cc. Silver 47.7 cc. Ammonia 60 cc. Silver 49.5 cc. Effect of sodium bicarbonate. In this experiment, 1 gram of bicarbonate of soda was used instead of the soda or ammonia of the other experiments. The silver nitrate required was only 46.45 cc instead of the 47.0 cc, which is the normal result. This is probably due to the liberation of prussic acid and shows the importance of having the solution alkaline. Effect of zinc. In each experiment, 40 cc of the cyanide solution and 0.5 of a gram of zinc sulfate crystals were used, and the bulk was made up to 100 cc before titrating. Soda added, 1 cc. Silver required, 47.1 cc. Soda, 5 cc. Silver, 47.0 cc. Soda, 10 cc. Silver, 46.9 cc. Soda, 25 cc. Silver, 46.9 cc. The work was easier with the more alkaline solutions. The titration in the presence of zinc is comparatively easy, but in learning it, it is well to have a burette with cyanide, so that if a titration be overdone, it can be brought back by the addition of 1 or 2 cc more cyanide, and the finish repeated. A quarter of an hour's work in this way will ensure confidence in the method. Effect of other substances. It was found that an alkaline cyanate, sulfocyanate, ferrocyanide, nitrite, borate, silicate, or carbonate has no effect. The ferricyanide had a small influence, and, as might be expected, hyposulfite is fatal to the assay. The addition of salts of lead and cadmium was without effect. On the other hand, nickel produces its full effect, and the quantity of nickel added can be calculated with accuracy from the extent of its interference with the titration. Assay of commercial cyanide of potassium. Break off 20 or 30 grams of the cyanide in clean fresh pieces. Weigh accurately to the nearest centigram. Dissolve in water containing a little sodium hydroxide. Transfer to a 2-litre flask. Dilute to 2 litres. Add a few grams of white lead, shake up and allow to settle. Run 50 cc of the clear liquor from a burette into an 8-ounce flask. Add 2 or 3 cc of soda solution and 3 drops of potassium iodide. Titrate with the standard solution of silver nitrate. The percentage may be calculated by multiplying the number of cc's used by 40. Note: 50 cc's is 1/40th of the 2 litres. End note. And dividing by the weight of commercial cyanide originally taken. Alkalinity of commercial potassium cyanide and of cyanide solutions. Hydrocyanic acid, like carbonic acid, has no action on methyl orange. Hence the alkaline cyanides may be titrated with normal acid as easily as the carbonates or hydrates. Note: see pages 322, 323 and 324 for a description of the methods for measuring the quantity of acid or alkali. End note. Reader's note: see volumetric methods for lime under alkaline earths. End note. 100 cc of normal acid will neutralise 6.5 grams of pure potassium cyanide. Note: KCN plus HCl yields KCl plus HCN. End note. A solution of commercial cyanide, prepared as for the assay last described, but best without the addition of white lead, may be used for the test. Take 50 cc of it. Tint faintly yellow with methyl orange and titrate with normal acid till the liquor acquires a permanent reddish tint. In the case of the purer samples of cyanide, the quantity of acid used will correspond exactly with that required to neutralise the actual quantity of cyanide present, as determined by the assay with nitrate of silver. The less pure samples will show an excess of alkalinity because of the presence of sodium carbonate or of potassium carbonate. In comparing the alkalinity and cyanide strength of a solution, the simplest plan is to take 65 cc of the solution and titrate with normal acid, for in this case each cc of normal acid corresponds to 0.1% of potassium cyanide. In systematic assays of this kind, the alkalinity would no doubt be generally in excess of that required by the cyanide present. There would be no inconvenience in recording such excess in terms of potassium cyanide. Determination of the acidity of an ore. Most ores have the power of destroying more or less of the alkalinity of a cyanide solution, and in a proportionate degree of damaging its efficiency. An assay is needed to determine how much lime or soda must be added for each ton of ore in order to counteract this. Whether this acidity should be reported in terms of the lime or of the soda required to neutralise it will depend on which of these reagents is to be used in the actual practice. Again, if the ore is washed with water before being treated with cyanide on the large scale, then the assay should be made of the acidity of the ore after a similar washing. The standard solutions of acid and alkali used for this determination may be 1/5 normal. 200 cc of the normal solution should be diluted to 1 litre in each case. 1 cc of the resulting solutions would be equivalent to 8 mg of soda, NaHO, or 5.6 mg of lime, CaO. It must be remembered this refers to the pure bases in each case. Suppose it is desired to report as so many pounds of lime to the short ton, 2000 pounds, of ore. Since 1 cc of the standard solution is equivalent to 5.6 mg of lime, if we take 2000 times this weight of ore, i.e. 11,200 mg or 11.2 grams, for the assay, each cc of standard solution will be equivalent to 1 pound of lime to the short ton. Note: taking 16.0 grams of ore, each cc is equivalent to 1 pound of soda to the short ton. The corresponding figures for the long ton are 12.544 grams for lime and 17.92 grams for soda. End note. Total acidity. Weigh out 11.2 grams of the ore, place them in a 4-inch evaporating dish, and measure onto it from a burette 10 or 20 cc of the standard solution of soda. Stir the soda solution into the ore and allow to stand for 15 or 20 minutes, with occasional stirring. Stir up with 30 or 40 cc of water. Float a piece of litmus paper on the liquid and titrate with the standard solution of acid. If the ore is strictly neutral, the quantity of acid required to redden the litmus will be the same as the quantity of soda originally used. If the ore is acid, less acid will be used. For example, if 10 cc's of soda were used and only 7 cc's of acid were required, the ore will have done the work of the remaining 3 cc's of acid, and the ton of ore will require 3 pounds of lime to neutralise its acidity. Acidity after washing. Take 11.2 grams of the ore. Wash thoroughly with water and immediately treat the residue, without drying, exactly as just described. Examination of cyanide solutions for metals, etc. Take a measured quantity of the solution, say 20 cc's, and evaporate in a small dish with, say, half a cc of strong sulphuric acid. Note: in which case each 0.01 of a gram of metal found equals 1 pound to the short ton of solution. End note. Evaporate at first on a water bath in a well ventilated place, but finish off with a naked Bunsen flame, using a high temperature at the end in order to completely decompose the more refractory double cyanides. Allow to cool. Moisten with strong hydrochloric acid, warm with a little water, and test for the metals in the solution by the ordinary methods. Since the quantities of the metals likely to be present may be given in milligrams, the work must be carefully performed. It may be worthwhile to determine the proportions of lime and magnesia as well as those of the metals proper. Or the 20 cc's of cyanide liquor may be evaporated with 5 cc's of strong nitric acid to dryness and gently ignited, and the residue taken up with 2 or 3 cc's of strong hydrochloric acid. Copper, iron and zinc can be rapidly determined in such a solution as follows. Dilute with water to 10 or 15 cc's, add an excess of ammonia and filter. The precipitate will contain the iron as ferric hydrate. Dissolve it in a little hot dilute sulphuric acid. Reduce with sulphuretted hydrogen. Boil off the excess of gas, cool, and titrate with standard potassium permanganate. Note page 236. End note. Reader's note in chapter 11, Iron. End reader's note. Determine the copper in the filtrate colorimetrically. Note page 203. End note. Reader's note in chapter 10 on copper. End reader's note. But avoid further dilution. Then add dilute hydrochloric acid so as to have an excess of 4 or 5 cc's after neutralizing the ammonia. Add some clean strips of lead foil and boil until the solution has for some time become colourless. Titrate with standard potassium ferrocyanide. Note page 263. End note. Reader's note, chapter 11 on zinc. End reader's note. Without further dilution, and bearing in mind that at most only 1 or 2 cc's will be required. Examination of an ore for cyanides. Place 100 grams of the ore with 200 cc's of a cyanide solution of known strength, say 0.1 or 0.2%, in a bottle, and agitate for a definite time, such as 1 or 2 days. Filter off some of the liquor and assay for cyanide, using, say, 20 cc's. Calculate how much cyanide has been destroyed in the operation. Evaporate 20 cc's with sulphuric or nitric acid and examine for metal. Test another portion for sulfides, etc. The student who has mastered the methods of assaying can greatly improve himself by working out such problems as the above. End of section 17. Section 18 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 9. Silver, Gold, Cyanides, Platinum, Mercury. Part 10. Platinum, Iridium, Mercury. Platinum. Platinum occurs in nature in alluvial deposits associated with gold and some rare metals, generally in fine metallic grains and occasionally in nuggets. It is a grey metal with a high specific gravity, 21.5 when pure and about 18.0 in native specimens. It is fusible only at the highest temperature and is not acted on by acids. It is dissolved by warm aqua regia, forming a solution of platinic chloride, H2PtCl6. This substance on evaporation remains as a brownish red deliquescent mass. On drying at 300 degrees centigrade, it is converted into platinous chloride, PtCl2, and becomes insoluble, and at a higher temperature it is converted into platinum. All platinum compounds yield the metal in this way. Platinic chloride combines with other chlorides to form double salts, of which the ammonic and potassic platinochlorides are the most important. Platinum alone is not soluble in nitric acid, but when alloyed with other metals which dissolve in this acid, it too is dissolved, so that in gold parting, for example, if platinum was present, some, or perhaps the whole of it, would go into solution with the silver. Such alloys, however, when treated with hot sulfuric acid, leave the platinum in the residue with the gold. Platinum is detected when in the metallic state by its physical characters and insolubility in acids. In alloys it may be found by dissolving them in nitric acid or in aqua regia, evaporating with hydrochloric acid, and treating the filtrate with ammonic chloride and alcohol. A heavy yellow precipitate marks its presence. The assay of bullion, or of an alloy containing platinum, may be made as follows. Take 0.2 gram of the alloy and an equal weight of fine silver, cupel with sheet lead, and weigh. The loss in weight after deducting that of the silver added gives the weight of the base metals, copper, lead, etc. Flatten the button and part by boiling with strong sulfuric acid for several minutes. When cold, wash, anneal, and weigh. The weight is that of the platinum and gold. The silver may be got by difference. Recupel the metal thus got with 12 or 15 times its weight of silver. Flatten and part the gold with nitric acid in the usual way, see under gold, and the platinum will dissolve. The gold may contain an alloy of osmium and iridium. If so, it should be weighed and treated with aqua regia. The osmiridium will remain as an insoluble residue, which can be separated and weighed. Its weight, deducted from that previously ascertained, will give the weight of the gold. When the platinum only is required, the alloy must be dissolved by prolonged treatment with aqua regia, the solution evaporated to dryness, and the residue extracted with water. The solution thus obtained is treated with ammonic chloride in large excess and with some alcohol. A sparingly soluble yellow ammonic platinum chloride is thrown down, mixed perhaps with the corresponding salts of other metals of the platinum group. Note: 100 c.c. of water dissolves 0.66 gram of the salt. It is almost insoluble in alcohol or in solutions of ammonic chloride. End note. Gold will be in solution. The solution is allowed to stand for some time, and then the precipitate is filtered off, washed with alcohol, dried, and transferred, wrapped in the filter paper, to a weighed crucible. It is ignited, gently at first, as there is danger of volatilizing some of the platinum chloride, and afterwards intensely. With large quantities of platinum, the ignition should be performed in an atmosphere of hydrogen. Cool, and weigh as metallic platinum. Iridium occurs in nature, alloyed with osmium as osmiridium or iridosmine, which is rather abundant in the auriferous beach sands of northern California. Note author Dana. End note. It occurs in bright metallic scales, which do not alloy with lead, and are insoluble in aqua regia. Iridium also occurs in most platinum ores, and forms as much as 2% of some commercial platinum. In chemical properties it resembles platinum, but the ammonic iridochloride has a dark red colour, and on ignition leaves metallic iridium, which does not dissolve in aqua regia diluted with 4 or 5 times its volume of water and heated to a temperature of 40 degrees or 50 degrees centigrade. The other metals of the platinum group are palladium, rhodium, osmium, and ruthenium. They differ from gold, platinum and iridium by the insolubility of their sulfides in a solution of sodium sulfide. Palladium is distinguished by the insolubility of its iodide, and osmium by the volatility of its oxide on boiling with nitric acid. Mercury. Mercury occurs native, and occasionally alloyed with gold or silver in natural amalgams, but its chief ore is the sulfide, cinnabar. It is comparatively rare, being mined only in a few districts. It is chiefly used in the extraction of gold and silver from their ores, amalgamation, for silvering mirrors, etc. Mercury forms two series of salts, mercurous and mercuric, but for the purposes of the assayer, the most important property is the ease with which it can be reduced to the metallic state from either of these. Mercury itself is soluble in nitric acid, forming, when the acid is hot and strong, mercuric nitrate. Cinnabar is soluble only in aqua regia. Mercurous salts are generally insoluble and may be converted into mercuric salts by prolonged boiling with oxidizing agents, nitric acid or aqua regia. The salts of mercury are volatile, and if heated with a reducing agent or some body capable of fixing the acid, metallic mercury is given off, which may be condensed and collected. Mercury is separated from its solutions by zinc or copper, or it may be thrown down by stannous chloride, which, when in excess, gives a grey powder of metallic mercury, or if dilute, a white crystalline precipitate of mercurous chloride. Nitric acid solutions of mercury yield the metal on electrolysis, and if the pole on which the metal comes down be made of gold or copper, or is coated with these, the separated mercury will adhere thereto. It may then be washed and weighed. The best tests for mercury, next to obtaining globules of the metal, are 1. A black precipitate with sulphuretted hydrogen from acid solutions, which is insoluble in nitric acid, and 2. A white precipitate with stannous chloride. Dry method. Weigh up 5 grams if the ore is rich, or 10 grams if a poorer mineral. Take a piece of combustion tube from 18 inches to 2 feet long, closed at one end, and place in it some powdered magnesite, so as to fill it to a depth of 2 or 3 inches, and on that a layer of an equal quantity of powdered lime, not slaked. Mix the weighed sample of ore in a mortar with 10 grams of finely powdered lime and transfer to the tube. Rinse out the mortar with a little more lime and add the rinsings. Cover with a layer of 6 or 7 inches more lime and a loosely fitting plug of asbestos. Draw out the tube before the blowpipe to the shape shown in figure 47, avoiding the formation of a ridge or hollow at the bend which might collect the mercury. Reader's note: Figure 47 shows a long narrow tube bent sharply at one end to a point which touches the surface of water in a small beaker. End reader's note. Tap gently, holding the tube nearly horizontal so as to allow sufficient space above the mixture for the passage of the gases and vapours which are formed. Place the tube in a tube furnace, and when in position place a small beaker of water so that it shall just close the opening of the tube. The point of the tube should not more than touch the surface of the water. Bring the tube gradually to a red heat, commencing by heating the lime just behind the asbestos plug and travelling slowly backwards. When the portion of the tube containing the ore has been heated to redness for some time, the heat is carried back to the end of the tube. The magnesite readily gives up carbonic acid, which fills the tube and sweeps the mercury vapour before it. Some of the mercury will have dropped into the beaker, and some will remain as drops adhering to the upper part of the neck. While the tube is still hot, cut off the neck of the tube just in front of the asbestos plug. A drop of water from the wash bottle will do this, and wash the mercury from the neck into the beaker. The mercury easily collects into a globule, which must be transferred after decanting off the bulk of the water to a weighed Berlin crucible. The water is removed from the crucible, first by the help of filter paper, and then by exposing in a desiccator over sulphuric acid, where it should be left until its weight remains constant. It should not be warmed. Example: 5 grams of an ore treated in this way gave 4.265 grams of mercury, equivalent to 85.3%. Pure cinnabar contains 86.2%. Wet methods. Solution. Since solutions of chloride of mercury cannot be boiled without risk of loss, nitric acid solutions should be used wherever possible. Note: according to Persson, mercuric chloride is not volatilized from boiling solutions when alkaline chlorides are present. End note. No mercury-containing minerals are insoluble in acids, but cinnabar requires aqua regia for solution. In dissolving this mineral, nitric acid should be used with just as much hydrochloric acid as will suffice to take it up. To separate the mercury, pass sulphuretted hydrogen in considerable excess through the somewhat dilute solution. The precipitate should be black, although it comes down at first very light coloured. It is filtered, washed, and transferred back to the beaker, and then digested with warm ammonic sulphide. The residue, filtered, washed, and boiled with dilute nitric acid, will, in the absence of much lead, be pure mercuric sulphide. If much lead is present, a portion may be precipitated as sulphate, but can be removed by washing with ammonic acetate. To get the mercury into solution, cover with nitric acid and a few drops of hydrochloric, and warm till solution is effected. Dilute with water to 50 or 100 cc. Gravimetric determination. This may be made by electrolysis. The same apparatus as is used for the electrolytic copper assay may be employed, but instead of a cylinder of platinum, one cut out of sheet copper should be taken, or the platinum one may be coated with an evenly deposited layer of copper. Fix the spiral and weighed copper cylinder in position, couple up the battery, and, when this has been done, put the nitric acid solution of the mercury in its place. Note: the solution should contain about 0.25 of a gram of mercury, and a large excess of nitric acid must be avoided. End note. The student had better refer to the description of the electrolytic copper assay. The mercury comes down readily, and the precipitation is complete in a few hours. It is better to leave it overnight to make sure of complete reduction. Disconnect the apparatus and wash the cylinder, first with cold water, then with alcohol. Dry by placing in the water oven for 2 or 3 minutes. Cool and weigh. The increase in weight gives the amount of metallic mercury. It must be remembered that copper will precipitate mercury without the aid of the battery, but in this case copper will go into solution, with a consequent loss in the weight of the cylinder. This must be avoided by connecting the battery before immersing the electrodes in the assay solution. The electrolyzed solution should be treated with an excess of ammonia, when a blue coloration will indicate copper, in which case the electrolysis is unsatisfactory. With a little care, this need not happen. Gold cylinders may preferably be used instead of copper, but on platinum the deposit of mercury is grey and non-adherent, so that it cannot be washed and weighed. Volumetric methods. Several methods have been devised. For the details of these, the student is referred to Sutton's Handbook of Volumetric Analysis. Questions. 1. The specific gravity of mercury is 13.596. What volume would 8 grams occupy? 2. If 3.169 grams of cinnabar gave 2.718 grams of mercury, what would be the percentage of the metal in the ore? 3. Pour solution of mercuric chloride on mercury and explain what happens. 4. On dissolving 0.3 of a gram of mercury in hot nitric acid and passing sulphuretted hydrogen in excess through the diluted solution, what weight of precipitate will be got? End of section 18. Section 19 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 10. Copper, Lead, Thallium, Bismuth, Antimony. Copper. Copper occurs native in large quantities, especially in the Lake Superior district. In this state it is generally pure. More frequently it is found in combination. The ores of copper may be classed as oxides and sulfides. The most abundant oxidized ores are the carbonates, malachite and chessylite. The silicates, as also the red and black oxides, occur less abundantly. All these yield their copper in solution on boiling with hydrochloric acid. The sulfides are more abundant. Copper pyrites, or yellow ore, erubicite, or purple ore, and chalcocite, or grey ore, are the most important. Iron pyrites generally carries copper and is frequently associated with the above-mentioned minerals. These are all attacked by nitric acid. They nearly all contain a small quantity of organic matter and frequently considerable quantities of lead, zinc, silver, gold, arsenic, bismuth, etc. The copper ores are often concentrated on the mine before being sent into the market, either by smelting, when the product is a regulus or matte, or by a wet method of extraction, yielding cement copper or precipitate. A regulus is a sulfide of copper and iron carrying from 30 to 40% of copper. A precipitate, which is generally in the form of powder, consists mainly of metallic copper. Either regulus or precipitate may be readily dissolved in nitric acid. Copper forms two classes of salts, cuprous and cupric. The former are pale-coloured and of little importance to the assayer. They are easily and completely converted into cupric by oxidizing agents. Cupric compounds are generally green or blue and are soluble in ammonia, forming deep blue solutions. Dry assay. That for copper, next after those for gold and silver, holds a more important position than any other dry assay. The sale of copper ores has been regulated almost solely in the past by assays made on the Cornish method. It is not pretended that this method gives the actual content of copper, but it gives the purchaser an idea of the quantity and quality of the metal that can be got by smelting. The process is itself one of smelting on a small scale. As might be expected, however, the assay produce and the smelting produce are not the same, there being a smaller loss of copper in the smelting. The method has worked very well, but when applied to the purchase of low-class ores, from which the whole of the copper is extracted by wet methods, it is unsatisfactory. The following table, which embodies the results of several years' experience with copper assays, shows the loss of copper on ores of varying produce. The figures in the fourth column show how rapidly the proportion of copper lost increases as the percentage of copper in the ore falls below 30%. For material with more than 30%, the proportion lost is in inverse proportion to the copper present. Reader's note. The table is headed Loss of Copper. There are 4 columns: copper present, dry assay, margin, loss on 100 parts of copper. A selection from over 30 entries in the table is given. From 100% down to 20%, there is an entry every 5% of copper present. For example, 100% copper present, dry assay 98%, margin 2%, loss on 100 parts of copper 2.0. 30% copper present, dry assay 28.5%, margin 1.50, loss on 100 parts of copper 5.0. 20% of copper present, dry assay 18.5%, margin 1.56%, loss on 100 parts of copper 7.8. From 20 down to 6% copper present is given in steps of 2%. Example, 10% copper present, dry assay 8.75%, margin 1.28%, loss on 100 parts of copper 12.8. 6% copper present, dry assay 5%, margin 1.05%, loss on 100 parts of copper 17.5. From 3.75% to 2% copper present is given in steps of 0.25%. 3.75% copper present, dry assay 2.75%, margin 0.97, loss on 100 parts of copper 26.0. and the last entry in the table, copper present 2.00%, dry assay 1 5/16%, margin 0.66%, loss on 100 parts of copper 33.0. To summarise, between 100% and 30% copper present, the loss on 100 parts of copper varies from 2.0 to 5.0. From 25% to 14%, the loss on 100 parts of copper varies from 6.0 to 10.0. And from 12% copper present down to 2% copper present, the loss on 100 parts of copper varies from 11.4 to 33.0. End reader's note. The wet assay being known, the dry assay can be calculated with the help of the above table by deducting the amount in the column headed margin opposite the corresponding percentage. For example, if the wet assay gives a produce of 17.12%, there should be deducted 1.5. The dry assay would then be 15.62, or, since the fractions are always expressed in eighths, 15 5/8. With impure ores containing from 25 to 50% of copper, the differences may be perhaps a quarter greater. Wet methods are gradually replacing the dry assay, and it is probable that in the future they will supersede it. For stock taking and the various determinations required in smelting works and on mines, they are generally adopted because they give the actual copper contents, and since it is obvious that a knowledge of this is more valuable to the miner and smelter. Moreover, the working of the dry method has been monopolised by a small ring of assayers, with the double result of exciting outside jealousy and, worse still, of retarding the development and improvement of the process. The principal stages of the dry assay are: 1. The concentration of the copper in a regulus; 2. The separation of the sulphur by calcining; 3. The reduction of the copper by fusion; and 4. The refining of the metal obtained. The whole of these operations are not necessary with all copper material. Ores are worked through all the stages. With mattes, the preliminary fusion for regulus is omitted. Precipitates are simply fused for coarse copper and refined, and blister or bar coppers are refined or, if very pure, subjected merely to washing. The quantity of ore generally taken is 400 grains, and is known as a full trial. But for rich material containing more than 50% of copper, a half trial or 200 grains is used. Fusion for regulus. The ore, either with or without a previous imperfect roasting to get rid of any excess of sulphur, is mixed with borax, glass, lime, and fluorspar, and in some cases with nitre or iron pyrites, according to the quality of the ore. The mixture is placed in a large Cornish crucible and heated, as uniformly as possible, in the wind furnace, gradually raising the temperature so as to melt down the charge in from 15 to 20 minutes. The crucible is removed and its contents poured into an iron mould. When the slag is solid, it is taken up with tweezers and quenched in water. The regulus is easily detached from the slag. It should be convex above and easily broken, have a reddish brown colour, and contain from 40 to 60% of copper. A regulus with more than this is too fine, and with less too coarse. A regulus which is too fine is round, compact, hard, and of a dark bluish grey on the freshly broken surface. A coarse regulus is flat and coarse-grained, and more nearly resembles sulphide of iron in fracture and colour. If an assay yields a regulus too coarse, a fresh determination is made with more nitre added, or the roasting is carried further. With low-class ores, a somewhat coarse regulus is an advantage. If, on the other hand, the regulus is too fine, less nitre or less roasting is the remedy. With grey copper ores and the oxidised ores, iron pyrites is added. Calcining the regulus. It is powdered in an iron mortar and transferred to a small Cornish crucible, or, if the roasting is to be done in the muffle, to a roasting dish or scorifier. The calcining is carried out at a dull red heat, which is gradually increased. The charge requires constant stirring at first to prevent clotting, but towards the end it becomes sandy and requires less attention. If the temperature during calcination has been too low, sulfates are formed, which are again reduced to sulfides in the subsequent fusion. To prevent this, the roasted regulus is recalcined at a higher temperature after being rubbed up with a little anthracite. The roasted substance must not smell of burning sulphur when hot. It is practically a mixture of the oxides of copper and iron. Fusion for coarse copper. The calcined regulus is mixed with a flux consisting of borax and carbonate of soda, with more or less tartar according to its weight. Some assayers use both tartar and nitre, the former of course being in excess. The charge is returned to the crucible in which it was calcined and is melted down at a high temperature, and as soon as tranquil, poured. When solid, it is quenched and the button of metal separated. The slag is black and glassy. The small quantity of copper which it retains is recovered by a subsequent cleaning, together with the slags from the next operation. The button of coarse copper obtained must be free from a coating of regulus. It will vary somewhat in appearance according to the nature and quantity of the impurities. Refining the coarse copper. The same crucible is put back in the furnace, deep down and under the crevice between the two bricks. When it has attained the temperature of the furnace, the coarse copper is dropped into it and the furnace closed. The copper will melt almost at once with a dull surface, which after a time clears, showing an eye. Some refining flux is then shot in from the scoop. Figure 48. Reader's note. Figure 48 shows a very shallow-rimmed, flat-bottomed, shuffle-like scoop. It is shaped roughly like an isosceles triangle, about 3 times as long as its base. The narrow tip is cut off and is the open end of the scoop. The base is rounded, with an offset handle attached to it. End reader's note. And when the assay is again fluid, it is poured. When cold, the button of metal is separated. The button of fine copper is flat or pitted on its upper surface and is coated with a thin orange film. It must have the appearance of good copper. If it is covered with a red or purple film, it is overdone or burnt. If, on the other hand, it has a rough, dull appearance, it is not sufficiently refined. Assays that have been burnt are rejected. Those not sufficiently fine are treated as coarse copper and again put through the refining operation. Cleaning the slags. These are roughly powdered and refused with tartar, etc., as in the fusion for coarse copper. The button of metal got is separated, if big enough, refined, and weighed. The details of the process are slightly varied by different assayers. The following will be good practice for the student. Determination of copper in copper pyrites. Powder, dry, and weigh up 20 grams of the ore. Mix with 20 grams each of powdered lime and fluor, 15 grams each of powdered glass and borax, and 5 or 10 grams of nitre. Transfer to a large Cornish crucible and fuse under a loose cover at a high temperature for from 15 to 20 minutes. When fluid and tranquil, pour into a mould. When the slag has solidified, but whilst still hot, quench by dipping 2 or 3 times in cold water. Avoid leaving it in the water so long that it does not dry after removal. When cold, separate the button, or perhaps buttons, of regulus by crumbling the slag between the fingers. See that the slag is free from regulus. It should be light coloured when cold and very fluid when hot. Reject the slag. Powder the regulus in a mortar and transfer to a small crucible. Calcine with occasional stirring until no odour of sulphurous oxide can be detected. Shake back into the mortar, rub up with about 1 gram of powdered anthracite, and recalcine for 10 minutes longer. Mix the calcined regulus with 10 grams of tartar, 20 grams of soda, and 3 grams of borax, and replace in the crucible used for calcining. Fuse at a bright red heat for 10 or 15 minutes. Pour when tranquil. As soon as solid, quench in water, separate the button of copper, and save the slag. To refine the copper, a very hot fire is wanted, and the fuel should not be too low down in the furnace. Place the crucible well down in the fire and in the middle of the furnace. The same crucible is used, or if a new one is taken it must be glazed with a little borax. When the crucible is at a good red heat, above the fusing point of copper, drop the button of copper into it and close the furnace. Watch through the crevice, and as soon as the button has melted and appears clear, showing an eye, shoot in 10 grams of refining flux, close the furnace, and in a few minutes pour. Then separate the button of copper. Add the slag to that from the coarse copper fusion and powder. Mix with 5 grams of tartar, 0.5 of a gram of powdered charcoal, and 2 grams of soda. Fuse in the same crucible, and when tranquil, pour. Quench and pick out the prills of metal. If the copper thus got from the slags is coarse looking and large in amount, it must be refined, but if small in quantity it may be taken as 4/5 copper. The combined results multiplied by 5 give the percentage of copper. The refining flux is made by mixing 3 parts by measure of powdered nitre, 2½ of tartar, and 1 of salt. Put in a large crucible and stir with a red-hot iron until action has ceased. This operation should be carried out in a well-ventilated spot. For pure ores in which the copper is present either as metal or oxide, and free from sulphur, arsenic, etc., the concentration of the copper in a regulus may be omitted, and the metal obtained in a pure state by a single fusion. Note: Modern American Methods of Copper Smelting, Dr. Peters. End note. It is necessary to get a fluid neutral slag with the addition of as small an amount of flux as possible. The fusion should be made at a high temperature, so as not to occupy more than from 20 to 25 minutes. 30 grams of ore is taken for a charge, mixed with 20 grams of cream of tartar and 10 grams each of dried borax and soda. If the gangue of the ore is basic, carrying much oxide of iron or lime, silica is added in quantity not exceeding 10 grams. If, on the other hand, the gangue is mainly quartz, oxide of iron, up to 7 grams, must be added. Example: 20 grams of copper pyrites, known to contain 27.6% of copper, gave by the method first described 5.22 grams of copper, equalling 26 1/8%. Another sample of 20 grams of the same ore, calcined, fused with 40 grams of nitre, and washed to ensure the removal of arsenic and sulphur, and treated according to the second method, gave a button weighing 5.27 grams, equalling 26 3/8%. The ore contained a considerable quantity of lead. Lead renders the assay more difficult, since after calcination it remains as lead sulphate, and in the fusion for coarse copper reappears as a regulus on the button. The estimation of moisture. The Cornish dry assayer very seldom makes a moisture determination. He dries the samples by placing the papers containing them on the iron plate of the furnace. It is well known that by buying the copper contents of pyrites by Cornish assay, burning off the sulphur, and converting the copper into precipitate, a large excess is obtained. Notes on the valuation of copper ores. Closely bound up with the practice of dry copper assaying is that of valuing a parcel of copper ore. The methods by which the valuation is made have been described by Mr. Westmoreland. Note: Journal of the Society of Chemical Industry, Volume 5, No. 2. End note. And are briefly as follows. The produce of the parcel is settled by 2 assayers, one acting for the buyer, the other for the seller, with the help, in case of non-agreement, of a third, or referee, whose decision is final. The dry assayers who do this are in most cases helped and sometimes, perhaps, controlled by wet assays made for one or both of the parties in the transaction. In the case of ticketing, the parcels are purchased by the smelters by tender, and the value of any particular parcel is calculated from the average price paid, as follows: The standard or absolute value of each ton of fine copper in the ore is the price the smelters have paid for it, plus the returning charges, or cost of smelting the quantity of ore in which it is contained. The value of any particular parcel of ore is that of the quantity of fine copper it contains, calculated on this standard, minus the returning charges. The ton consists of 21 hundredweights, and it is assumed that the settled produce is the actual yield of the ore. If at a ticketing in Cornwall 985 tons of ore containing 63.3 tons of fine copper by dry assay brought £2,591 12 shillings, the standard would be £83 15 shillings. This is calculated as follows. The returning charge is fixed at 55 shillings per ton of ore. This, on 985 tons, will amount to £2,708 15 shillings. Add this to the actual price paid, and there is got £5,300 as the value of the fine copper present. The weight of copper in these 985 tons being 63.3 tons, the standard is 5,300 divided by 63.3, or £83 15 shillings, nearly. The value of a parcel of 150 tons of a 6% ore on the same standard would be arrived at as follows. The 150 tons at 6% would contain 9 tons, 150 times 6 divided by 100, of fine copper. This, at £83 15 shillings per ton, would give £753 15 shillings. From this must be deducted the returning charges on 150 tons of ore at 55 shillings per ton, or £412 10 shillings. This leaves £341 5 shillings as the value of the parcel. At Swansea, the returning charge is less than in Cornwall, and varies with the quality of the ore. This appears equitable, since in smelting there are some costs which are dependent simply on the number of tons treated, and others which increase with the richness. The returning charge, then, is made up of two parts, one fixed at so much, 12 shillings and twopence, per ton of ore treated, and the other so much, 3 shillings and ninepence, per unit of metal in the ore. In this way the returning charges on a ton of ore of 8 3/4 produce would be 12 shillings and twopence plus 8 3/4 times 3 shillings and ninepence, or £2 5 shillings. If, for example, Chile bars containing 96% of copper bring £50 per ton, the standard is £71 9 shillings and fourpence. It is got at in this way. The returning charge on a 96% ore is 12 shillings and twopence plus 96 times 3 shillings and ninepence, or £18 12 shillings and twopence. This added to £50 gives £68 12 shillings and twopence, and this multiplied by 100 and divided by 96. Note, 100 tons of the bars will contain 96 tons of fine copper. End note. Will give £71 9 shillings and fourpence. The price of 100 tons of pyrites containing 2¼ % of copper by dry assay would be got on this standard as follows. The parcel of ore would contain 2¼ tons of copper. This, multiplied by the standard, gives £160 16 shillings no pence. From this must be deducted the returning charge, which for 1 ton of ore of this produce would be 12 shillings and twopence plus 2¼ times 3 shillings and ninepence, or £1 no shillings and 7 pence, and on the 100 tons is £102 18 shillings and fourpence. This would leave £57 17 shillings and tenpence as the price of the parcel, or 11 shillings and sevenpence per ton. This would be on the standard returning charge of 45 shillings. Note, for 8 3/4% ore. End note. If a smaller returning charge was agreed on, say 38 shillings, the difference in this case, 7 shillings, would be added to the price per ton. Wet methods. The solubility of the ores of copper in acid has already been described, but certain furnace products, such as slags, are best opened up by fusion with fusion mixture and a little niter. The method of dissolving varies with the nature of the ore. With 5 grams of pyrites, a single evaporation with 20 c.c. of nitric acid will give a residue completely soluble in 30 c.c. of hydrochloric acid. If the ore carries oxide of iron or similar bodies, these are first dissolved up by boiling with 20 c.c. of hydrochloric acid, and the residue attacked by an addition of 5 c.c. of nitric. When silicates decomposable by acid are present, the solution is evaporated to dryness to render the silica insoluble. The residue extracted with 30 c.c. of hydrochloric acid and diluted with water to 150 c.c. It is advisable to have the copper in solution as chloride. To separate the copper, heat the solution nearly to boiling, best in a pint flask, and pass a rapid current of sulphuretted hydrogen for 4 or 5 minutes, until the precipitate settles readily and the liquid smells of the gas. When iron is present, it will be reduced to the ferrous state before the copper sulphide begins to separate. The copper appears as a brown coloration, or black precipitate, according to the quantity present. Filter through a coarse filter, wash with hot water containing sulphuretted hydrogen, if necessary. Wash the precipitate back into the flask, boil with 10 c.c. of nitric acid, add soda till alkaline, and pass sulphuretted hydrogen again. Warm and filter, wash and redissolve in nitric acid, neutralize with ammonia, add ammonic carbonate, boil and filter. The copper, freed from impurities, will be in the solution. Acidulate and reprecipitate with sulphuretted hydrogen. When the nature of the impurities will allow it, this process may be shortened to first filtering off the gangue, then precipitating with sulphuretted hydrogen and washing the precipitate on the filter, first with water and then with ammonium sulphide. Having separated the copper as sulphide, its weight is determined as follows. Dry and transfer to a weighed porcelain crucible, mix with a little pure sulphur, and ignite at a red heat for 5 or 10 minutes in a current of hydrogen. Allow to cool while the hydrogen is still passing. Weigh. The sub-sulphide of copper thus obtained contains 79.85% of copper. It is a greyish-black crystalline mass which loses no weight on ignition if air is excluded. Copper may be separated from its solutions by means of sodium hyposulphite. The solution is freed from hydrochloric and nitric acids by evaporation with sulphuric acid, diluted to about 1/4 litre, heated nearly to boiling, and treated with a hot solution of sodium hyposulphite, added a little at a time, until the precipitate settles and leaves the solution free from colour. The solution contains suspended sulphur. The precipitate is easily washed, and under the proper conditions the separation is complete. But the separation with sulphuretted hydrogen is more satisfactory, since the conditions as to acidity, etc., need not be so exact. Zinc or iron is sometimes used for separating copper from its solutions, but they are not to be recommended. End of section 19. Section 20 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 10. Copper, Lead, Thallium, Bismuth, Antimony. Part 2. Copper. Electrolytic Assay. The separation of copper by means of a current of electricity is largely made use of, and forms the basis of the most satisfactory method for the determination of this metal. If the wire closing an electric circuit be broken, and the two ends immersed in a beaker of acidulated water, or solution of any salt, the electricity will pass through the liquid, bringing about some remarkable changes. Hydrogen and the metals will be liberated around that part of the wire connected with the zinc end of the battery, and oxygen, chlorine, and the acid radicals will be set free around the other. Different metals are deposited in this way with varying degrees of ease, and whether or not any particular metal will be deposited depends 1. on the conditions of the solution as regards acid and other substances present, and 2. on the intensity of the current of electricity used. For analytical purposes, the metal should be deposited not only free from the other metals present, but also as a firm coherent film, which may afterwards be manipulated without fear of loss. This is, in the case of copper and many other metals, effected by a simple control of the conditions. It is necessary that the electrodes, or wires which bring the electricity into the solution, should be made of a material to which the deposited metal will adhere, and which will not be attacked by substances originally present or set free in the solution. They are generally made of platinum. There are various arrangements of apparatus used for this purpose, but the following plan and method of working is simple and effective, and has been in daily use with very satisfactory results for the last 5 or 6 years. The battery used is made up of 2 Daniell cells, coupled up for intensity as shown in figure 49, that is, with the copper of one connected with the zinc of the other. Reader's note: each Daniell cell consists of a cylindrical outer container with a cylindrical inner, and within that a cylindrical rod. Wires are connected to the cylindrical rod and to the outer container. Figure 49 shows 2 such cells, where the wire from the outer container of one cell is connected to the inner rod of the other. End reader's note. For 8 or 10 assays daily, the quart size should be used, but for 4 or 5, 2 pint cells will be sufficient. The outer pot of each cell is made of sheet copper, and must be clean and free from solder on the inside. It is provided near the top with a perforated copper shelf in the shape of a ring, into which the inner or porous cell loosely fits. It is charged with a saturated solution of copper sulphate, and crystals of this salt must be added and always kept in excess. When the battery is at work, copper is being deposited on the inner surface of this pot. The inner or porous pot contains the zinc rod, and is charged with a dilute acid, made by diluting 1 volume of sulphuric acid up to 10 with water. The object of the porous pot is to prevent the mixing of the acid and copper sulphate solutions without interrupting the flow of electricity. The copper sulphate solutions will last for months, but the acid must be emptied out and recharged daily. The zinc rods must be well amalgamated by rubbing with mercury under dilute acid until they show a uniformly bright surface. They should not produce a brisk effervescence when placed in the acid in the porous pot before coupling up. The battery, when working, is apt to become dirty from the creeping of the copper and zinc sulphate solution. It must be kept away from the working bench, and is best kept in a box on the floor. The connection of the battery with, and the fixing of, the electrodes may be made by any suitable arrangement, but the following is a very convenient plan. The wire from the zinc is connected by means of a binding screw with a piece of stout copper wire, which, at a distance sufficiently great to allow of easy coupling with the battery, is led along the back of a piece of hardwood. This is fixed horizontally about 1 foot above the working bench. The general arrangement is shown in figure 50, in which, however, for the sake of economy of space, the battery is placed on the working bench instead of on the floor. Reader's note: figure 50 shows 2 batteries at the left connected in series, with wires from cathode and anode passing along the horizontal wooden bar. A small beaker rests on each wooden block. Each beaker holds 2 electrodes, one inside the other. The outer one is a cylinder. The pairs of electrodes in the beakers are connected in series to the wires running along the wooden bar from the batteries. End reader's note. The piece of wood is 1 inch square and 3 or 4 feet long. It is perforated from front to back at distances of 6 inches by a number of small holes, in which are inserted screws like that shown in figure 51. Reader's note: figure 51 shows a long threaded bolt with a wide circular knurled nut turning on it. End reader's note. These are known as terminals, and may be obtained of any electrician. The head of each screw is soldered to the wire mentioned above as running along the back, and as being connected with the zinc end of the battery. These terminals serve to fix the electrodes on which the copper is to be deposited. The wire from the copper end of the battery is similarly connected by a connecting screw. Figure 52. Reader's note. Figure 52 shows a short piece of thick-walled metal tubing. At each end, a small threaded screw with a knurled head passes across the tube. The screws are in place to tighten on wires inserted in the tubing at each end. End reader's note. With another wire, H in figure 53, which runs along the top of the rod and has soldered to it at distances of 6 inches cylindrical spirals of copper wire. These should project from the rod at points about halfway between the terminals already described. They may be made by wrapping copper wire around a black lead pencil for a length of about 3 inches. The rod is perforated from top to bottom with a series of small holes, one in advance of each terminal, but as near it as possible. Into these, short pieces of glass tube are inserted to ensure insulation. These receive the other electrodes, which are connected with the wire leading to the copper end of the battery through the spirals with the help of a binding screw. The figure will make this clear. Figure 53. Reader's note. Figure 53 is a close-up of one of the beakers resting on the top of its wooden block, with the wooden bar just above it. One wire from the battery runs along the top of the bar, and one behind the bar. At point H, mentioned in the text, a short loop of coiled wire is soldered onto the wire on top of the bar and is attached, by the connector described in figure 52, to the central electrode in the beaker. This central electrode passes from the beaker to the connector via a short length of glass tubing inserted vertically through the wooden bar. The other electrode in the beaker, which in the figure appears to be a cylinder surrounding the central electrode, is fixed to the face of the wooden bar by a terminal bolt, which runs through the wooden bar to connect the electrode to the battery wire running along the back of the wooden bar. End reader's note. The electrodes consist of a platinum spiral and cylinder. The spiral should have the shape shown in A, figure 54. Reader's note. Figure 54A shows a vertical wire attached to a tightly wound spiral of about 2 revolutions of metal sheet, making a near cylinder. End reader's note. When in work, it is passed through one of the holes fitted with glass tubes and connected with the copper end of the battery. The thickness of the wire of which it is made is unimportant, provided it is stout enough to keep its form and does not easily bend. The spiral will weigh about 8 grams. The cylinder, note C, figure 54, end note, will weigh about 12 grams. It should have the shape shown in the figure. Reader's note. Figure 54B and C show a small square of metal sheet attached to a vertical wire. This sheet is then formed into a cylinder. In working, it is clamped to one of the terminals, and on it the copper is deposited. A cylinder will serve for the deposition of from 1 to 1.5 grams of copper. It is made by riveting a square piece of foil onto a stiff piece of wire, and then bending into shape over a glass tube or piece of rounded wood. Each cylinder carries a distinctive number, and is marked by impressing Roman numerals on the foil with the blade of a knife. The weight of each is carefully taken and recorded. They lose slightly in weight when in use, but the loss is uniform and averages half a milligram per month when in daily use. The cylinders are cleaned from deposited copper by dissolving off with nitric acid and washing with water, and from grease by igniting. The beakers to contain the solution of copper to be electrolysed are ordinary tall beakers of about 200 cc capacity, and are marked off at 100 cc and 150 cc. They are supported on movable stands consisting of wooden blocks about 6 inches high and 3 inches across. The bar of wood which carries the connecting wires and electrodes is permanently fixed over the working bench at such a height that, with the beakers resting on these blocks, the electrodes shall be in position for working. To fix the electrodes to the rod, Remove the stand and beaker and pass the long limb of the spiral up through one of the glass tubes. Connect it with the free end of the copper spiral by means of a connecting screw, figure 52, and then draw out and bend the copper spiral so that the platinum one may hang freely. Screw the wire of the cylinder to the terminal, and, if necessary, bend it, so that the cylinder itself may be brought to encircle the rod of the spiral in the manner shown in figure 53. The general method of working is as follows. The quantity of ore to be taken for an assay varies with the richness of the ore, as is shown in the following table. 1 to 5% of copper in the ore, 5 grams of ore to be taken. 5 to 10% of copper in the ore, 3 grams to be taken. 10 to 30% of copper in the ore, 2 grams to be taken. 30 to 50% of copper in the ore, 1.5 grams to be taken. 50 to 100% of copper in the ore, 1 gram to be taken. The weighed quantity of ore is dissolved by evaporating with nitric acid and taking up with hydrochloric, as already described. Any coloured residue which may be left is generally organic matter. It is filtered off, calcined, and any copper it contains is estimated colorimetrically. Nearly always, however, the residue is white and sandy. The copper is separated from the solution as sulphide by means of a rapid current of sulphuretted hydrogen. The liquid is decanted off through a filter, the precipitate washed once with hot water, and then rinsed back into the flask, the filter paper being opened out, with a jet of water from a wash bottle. 15 cc of nitric acid are added to the contents of the flask, which are then briskly boiled until the bulk is reduced to less than 10 cc. The boiling down is carried out in a cupboard free from cold draughts, so as to prevent the condensation of acid and steam in the neck of the flask. 20 cc of water are next added, and the solution is warmed and filtered into one of the beakers for electrolysis. The filtrate and washings are diluted with water to the 100 cc mark, and the solution is then ready for the battery. It must not contain more than 10% by volume of nitric acid. The number and weight of the platinum cylinder having been recorded, both electrodes are fixed in position and the wooden block removed from under them. The beaker containing the copper solution is then brought up into its place with one hand and the block replaced with the other so as to support it. All the assays having been got into position, the connecting wires are joined to the battery. If everything is right, bubbles of oxygen at once stream off from the spiral, and the cylinder becomes tarnished by a deposit of copper. If the oxygen comes off but no copper is deposited, it is because the assay solution contains too much nitric acid. If no action whatever takes place, it is because the current is not passing. In this case, examine the connections to see that they are clean and secure, and the connecting wires to see that they are not touching each other. The action is allowed to go on for 16 or 17 hours, so that it is best to let the current act overnight. In the morning the solutions will appear colourless, and a slow stream of oxygen will still be coming off from the spiral. A wash bottle with cold distilled water and 2 beakers, one with distilled water and the other with alcohol, are got ready. The block is then removed, the spiral loosened and lowered with the beaker. The cylinder is next detached and washed with a stream of water from the wash bottle, the washings being added to the original solution. The current from the battery is not stopped until all the cylinders are washed. After being dipped in the beaker of water and once or twice in that with the alcohol, it is dried in the water oven for about 3 minutes and then weighed. The increase in weight is due to deposited copper. This should be salmon red in colour, satin-like or crystalline in appearance, and in an even, coherent deposit, not removed by rubbing. It is permanent in air when dry, but sulphuretted hydrogen quickly tarnishes it, producing coloured films. With ores containing even very small proportions of bismuth, the deposited copper has a dark grey colour, and when much of this metal is present, the copper is coated with a grey, shaggy deposit. It still remains to determine any copper left undeposited in the solution. This does not generally exceed 4 or 5 milligrams, and is estimated colorimetrically. 30 cc's of dilute ammonia, note 1 of strong ammonia mixed with 1 of water, end note, are added to the electrolyzed solution, which is then diluted up to the 150 cc mark with water. It is mixed using the spiral as stirrer, and after standing a few minutes to allow the precipitate to settle, 100 cc's of it are filtered off through a dry filter for the colorimetric determination. Since only 2/3 of the solution are taken for this, the quantity of copper found must be increased by 1/2 to get the quantity actually present. The colorimetric determination may be made in the manner described under that head, but where a number of assays are being carried out, it is more convenient to have a series of standard phials containing known amounts of copper in ammoniacal solution. By comparing the measured volume of the assay solution with these, the amount of copper present is determined at a glance. These standard bottles, however, can only be economically used where a large number of assays are being made daily. A convenient plan is to get a quantity of white glass 4-ounce phials, like that in figure 55. Reader's note, which shows a thin-walled stoppered glass phial, at least 6 times as tall as it is wide, with the 100 mm mark near the neck. End reader's note. And to label them so that they shall contain 100 cc's when filled up to the bottom of the labels. The labels should be rendered permanent by coating with wax, and be marked with numbers indicating the milligrams of copper present. The bottles are stopped with new, clean corks, and contain, in addition to the specified quantity of copper, 6 cc's of nitric acid and 10 cc's of strong ammonia, with sufficient water to make up the bulk to 100 cc's. The copper is best added by running in the requisite amount of a standard solution of copper, each cc of which contains 0.001 of a gram of the metal. The standard bottles should be refilled once every 3 or 4 months, since their colorimetric value becomes slowly less on keeping. The following determination of a set which had been in use for 3 months will illustrate this. The figures indicate milligrams of copper in 100 cc's. The first row gives the nominal and the second row the actual colorimetric value of the standards. The difference between the two shows the deterioration. 1 and 1, 2 and 2, 3 and 3, 4 and 3.7, 6 and 5.5, 8 and 7.5, 10 and 9, 12 and 11, 14 and 13. The amount of copper in the assay is got by increasing that found colorimetrically by 1/2 and adding to that found on the platinum cylinder. The percentage is calculated in the usual way. The following examples will illustrate this, as well as the method of recording the work in the laboratory book. First sample. Cylinder 1 plus copper 9.5410 grams, cylinder 1 9.5170 grams. By subtraction, copper 0.0240 of a gram. By colour, 100 cc's gives 0.0015 plus 0.0007, 1/2, total 0.0022. Total of copper 0.0262 of a gram. 9 sample took 5 grams. Copper equals 0.52%. Second sample, cylinder 6 plus copper 10.5705 grams. Cylinder 6 10.0437 grams. Copper by subtraction 0.5268 of a gram. By colour, 100 cc's yields 0.0070 and 0.0035, half that. Total 0.0105 of a gram. Total 0.5373 of a gram of copper. Matte number 1070 took 1.5 grams. Copper equals 35.82%. Third sample. Cylinder 13 plus copper 12.0352 grams, cylinder 13 11.0405 grams, copper by subtraction 0.9947 of a gram, By colour, 100 cc's yields 0.0005 plus 0.0002, half that, total 0.0007 of a gram, total 0.9954 of a gram of copper. 10 sample. Cake copper took 1.0053 of a gram. Copper equals 99.00%. In the electrolytic assay of metals, alloys, precipitates and other bodies rich in copper, the preliminary separation of the copper by sulphuretted hydrogen is unnecessary. It is sufficient to dissolve the weighed sample in 10 cc of nitric acid, boil off nitrous fumes, dilute to 100 cc with water, and then electrolyse. General considerations. In the preliminary work with the copper sulphide, there is a small loss owing to its imperfect removal in washing the filter paper, and another small loss in dissolving in nitric acid owing to the retention of particles in the fused globules of sulphur. To determine its amount, the filter papers and sulphur were collected from 40 assays, and the copper in them determined. The average amount of copper in each assay was 0.175 of a gram. That left on the filter paper was 0.00067 of a gram, and that retained by the sulphur 0.00003 of a gram, thus showing an average loss from both sources of 0.00070 of a gram. The determination from another lot of 42 similar assays gave, on an average, copper left on filter paper 0.00070 of a gram, copper retained by sulphur 0.00004 of a gram. The loss from these sources is trifling, and need only be considered when great accuracy is required. The deposition of the copper under the conditions given is satisfactory, but, as already stated, if the solution contains more than 10% of nitric acid, it is not thrown down at all. Or if a stronger current is used, say that from 3 Bunsen cells, it will be precipitated in an arborescent, brittle form, ill adapted for weighing. It may be noted here that increasing the size of the cells does not necessarily increase the intensity of the current. In 2 determinations on pure electrotype copper, the following results are obtained. Copper taken, 0.8988 of a gram. Copper found, 0.8985 of a gram. Copper taken, 0.8305 of a gram. Copper found, 0.8303 of a gram. The presence of salts of ammonia, etc., somewhat retards the deposition, but has no other ill effect. The organic matter generally present in copper ores interferes more especially in the colorimetric determination of the residual copper. It can be detected on dissolving the ore as a light black residue insoluble in nitric acid. It is filtered off at once, or, if only present in small amount, it is carried on in the ordinary process of the assay and separated in the last filtration before electrolysis. The following experiments were made to test the effect of the presence of salts of foreign metals in the solution during the precipitation of copper by electrolysis. Reader's note: this table is omitted as it is summarized in the text. End reader's note. It will be seen from these that mercury, silver and bismuth are the only metals which are precipitable, along with the copper, under the conditions of the assay. Note: lead, when present, is precipitated on the spiral in the form of a dark powder of dioxide, PbO2. Manganese is also thrown down on the spiral as dioxide, MnO2. The solution at the same time becomes violet from the formation of permanganic acid. End note. Mercury, which, if present, would interfere, is separated because of the insolubility of its sulphide in nitric acid. Bismuth is precipitated only after the main portion of the copper is thrown down. It renders the copper obviously unsuitable for weighing. It darkens or forms a greyish coating on the copper, and this darkening is a delicate test for bismuth. In assaying ores containing about 3.5% of copper, and known to contain bismuth in quantities scarcely detectable in ordinary analysis, the metal deposited was distinctly greyish in colour, and would not be mistaken for pure copper. 10 grams of this impure copper were collected and analysed with the following results: copper 99.46%, bismuth 0.30%, iron 0.14%, arsenic 0.10%, total 100%. The quantity of copper got in each assay was 0.175 of a gram, and consequently the bismuth averaged 0.00053 of a gram. To separate the bismuth in such a case, the deposit is dissolved off by warming it in the original solution. The bismuth is precipitated by the addition of ammonic carbonate, and the solution, after filtering and acidifying with nitric acid, is re-electrolysed. End of section 20. A textbook of assaying for the use of those connected with mines, by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Determination of copper in commercial copper. Take from 1 to 1.5 grams, weigh carefully and transfer to a beaker. Add 20 cc of water and 10 cc of nitric acid. Cover with a clock glass and allow to dissolve with moderate action. Boil off nitrous fumes, dilute to 100 cc and electrolyse. The cylinder must be carefully weighed and the electrolysis allowed to proceed for 24 hours. The weight found will be that of the copper and silver. The silver in it must be determined and deducted. Note: see the method given under Examination of Commercial Copper. End note. Determination of copper in brass, German silver, or bronze. Treat in the same manner as commercial copper. If nickel is present, the few milligrams of copper remaining in the electrolysed solution should be separated with sulphuretted hydrogen, the precipitated sulphide dissolved in nitric acid and determined colorimetrically. Volumetric processes. There are 2 of these in use, one based on the decolorizing effect of potassic cyanide upon an ammoniacal copper solution, and the other upon the measurement of the quantity of iodine liberated from potassic iodide by the copper salt. The cyanide process is the more generally used, and when carefully worked on certain understood and orthodox conditions, yields good results. But probably there is no method of assaying where a slight deviation from these conditions so surely leads to error. An operator has no difficulty in getting concordant results with duplicate assays, yet different assayers, working without bias on the same material, get results uniformly higher or lower, a difference evidently due to variations in the mode of working. Where a large number of results are wanted quickly, it is a very convenient method. The iodide process is very satisfactory when worked under the proper conditions. Cyanide method. The process is based upon the facts: 1. That when ammonia is added in excess to a solution containing cupric salts, ammoniacal copper compounds are formed which give to the solution a deep blue colour, and 2. That when potassic cyanide is added in sufficient quantity to such a solution, the colour is removed, double cyanides of copper and potassium or ammonium being formed. Note: CuSO4 plus 4KCy yields 2KCy CuCy2 plus K2SO4. End note. In the explanation generally given, the formation of cuprous cyanide is supposed. Note: 2CuSO4 plus 3KCy plus Am2O yields Cu2 Cy2 plus Am2SO4 plus K2SO4 plus KCyO. End note. But in practice it is found that 1 part of copper requires rather more than 4 parts of cyanide, which agrees with the former rather than the latter explanation. Reliance on the accuracy of the process cannot rest upon the supposition that the cyanide required for decoloration is proportional to the copper present, for varying quantities of ammonia salt, ammonia and water, and differences of temperature have an important effect. The results are concordant and exact only when the cyanide is standardized under the same conditions as it is used. It is best to have the assay solutions and that used for standardizing as nearly as possible alike, and to titrate the 2 solutions side by side. This demands an approximate knowledge of the quantity of copper contained in the ore and a separation of the bulk of the impurities. For the titration, there is required a standard solution of potassium cyanide made by dissolving 42 grams of the salt, known to dealers as potassium cyanide (gold), in water, and diluting to 1 litre. 100 cc of this will be about equivalent to 1 gram of copper. For poor ores, the solution may conveniently be made half this strength. The solution of the ore and the separation of the copper as sulphide are effected in the same ways as have been already described for electrolysis. Similarly, too, the sulphide is attacked with 15 cc of nitric acid and the assay boiled down to 10 cc. Add 20 cc of water and warm. Filter into a pint flask, wash well with water and dilute to about 150 cc. Add 30 cc of dilute ammonia and cool. Prepare a standard by dissolving a quantity of electrotype copper, note judged to be about the same as that contained in the assay, end note, in 20 cc of water and 10 cc of nitric acid. Boil off the nitrous fumes and dilute to 150 cc. Add 30 cc of dilute ammonia and cool. Fill a burette with the standard cyanide solution. The burette with siphon arrangement figured on page 52 is used. Reader's note: this consists of a standard burette with a side arm attached to a reservoir higher up and connected with a clip, so the burette can be refilled from the reservoir. End reader's note. A number of titrations can be carried on at the same time, provided the quantity of copper present in each is about the same. This is regulated in weighing up the ore. The flasks must, of course, be marked, and should be arranged in series on a bench in front of a good light, and at such a height that the liquid can be looked through without stooping. Supposing about 50 cc of cyanide will be required, 30 cc should be run into each, and each addition be recorded as soon as made. Then run 15 cc into each. The solutions will now probably show marked differences of tint. Add 1 cc of cyanide to the lighter ones, and more to the darker, so as to bring the colours to about the same depth of tint. They should all be of nearly equal tint just before finishing. At the end, add half a cc at a time until the colours are completely discharged. A piece of damp filter paper held between the light and the flask assists in judging the colour when nearly finished. Overdone assays show a straw yellow colour which deepens on standing. The following will illustrate the notes recorded of 5 such assays and 1 standard. 1. 30 cc, 15 cc, 5 cc, 2 cc, 1 cc, half a cc. Total 53.5 cc. 2. 30 cc, 15 cc, 1 cc, 1 cc, 1 cc, half a cc. Total 48.5 cc. 3. 30 cc, 15 cc, 3 cc, 1 cc, 1 cc, half a cc. Total 50.5 cc. 4. 30 cc, 15 cc, 5 cc, 2 cc, 1 cc, half a cc, and half a cc. Total 54 cc. 5. 30 cc's, 15 cc's, 2 cc's, 1 cc, 1 cc, half a cc, total 49.5 cc's. 6 30 cc's, 15 cc's, 2 cc's, 1 cc, 1 cc, half a cc, half a cc, total 50 cc's, standard. 3 grams of ore were taken, and the standard contained 0.480 of a gram of copper. In this series, the difference of half a cc means about 0.15% on the ore. With a little practice, it is easy to estimate whether the whole or half of the last addition should be counted. To get satisfactory results, the manner of finishing, once adopted, must be adhered to. The following experiments show the effect of variation in the conditions of the assay. Use a solution of copper nitrate made by dissolving 10 grams of copper in 50 cc's of water and 35 cc's of nitric acid, and diluting to a litre. 100 cc's is equivalent to 1 gram of copper. Effect of varying temperature. In these experiments, 20 cc's of copper nitrate were used with 10 cc's of nitric acid, 30 cc's of dilute ammonia, and water to 200 cc's. The results were temperature 15 degrees centigrade, cyanide required 21.5 cc's, 30 degrees centigrade 20.8 cc's cyanide, 70 degrees centigrade 19.7 cc's cyanide, 100 degrees centigrade 18.8 cc's of cyanide. The temperature is that of the solution before titrating. These show the importance of always cooling before titrating, and of titrating the assay and standard at the same temperature. Effect of varying bulk. The quantities of copper, acid, and ammonia were the same as in the last mentioned experiments. The results were bulk 100.0 cc's, cyanide required 23.3 cc's, bulk 200.0 cc's, cyanide required 21.7 cc's, bulk 300.0 cc's, cyanide required 21.4 cc's, bulk 400.0 cc's, cyanide required 21.4 cc's. These show that large variations in bulk must be avoided. Effect of varying ammonia. The quantities of copper and acid were the same as in the series of experiments last noticed. The bulk was 200 cc's. The results were dilute ammonia 20.0 cc's, cyanide required 20.9 cc's, dilute ammonia 30.0 cc's, cyanide required 21.7 cc's, dilute ammonia 50.0 cc's, cyanide required 22.3 cc's, dilute ammonia 100.0 cc's, cyanide required 24.6 cc's. Effect of varying acid. The quantities of copper and water were the same as in the last noticed set of experiments. 30 cc's of dilute ammonia were used. Nitric acid 5.0 cc's, cyanide required 21.6 cc's, nitric acid 10.0 cc's, cyanide required 21.7 cc's, nitric acid 15.0 cc's, cyanide required 21.5 cc's. On adding nitric acid to the solution, it combines with a portion of the ammonia to form ammonic nitrate. It will be seen from the last series of experiments that the lessening of the amount of free ammonia will decrease the quantity of cyanide required. But on the other hand, the ammonic nitrate, which is at the same time formed, will increase the amount required. Under the conditions of the assay, these two effects neutralize each other, and such differences in the quantity of acid as are likely to occur are unimportant. Effect of varying ammonic salts. The quantities of copper, water, and ammonia were the same as in the last mentioned set of experiments, but no nitric acid was used. Ammonic nitrate added 1 gram, cyanide required 21.2 cc's, ammonic nitrate 5 grams, cyanide required 21.1 cc's, ammonic nitrate 10 grams, cyanide required 23.1 cc's, ammonic nitrate 20 grams, Cyanide required 24.1 cc. These show that combined ammonia seriously affects the titration, and that the principle sometimes recommended of neutralizing the acid with ammonia and then adding a constant quantity of ammonia is not a good one, because there is then an interference both by the ammonia and by the variable quantity of ammonic salts. The same quantity of combined ammonia has the same effect, whether it is present as sulphate, nitrate, chloride, or acetate, as the following experiments show. 4 lots of 20 cc of copper nitrate were taken, and 20 cc of dilute ammonia added to each. These were carefully neutralized with the respective acids, rendered alkaline with 30 cc more of ammonia, cooled, diluted to bulk, and titrated. The results were with sulfuric acid 22.5 cc of cyanide, with nitric acid 22.6 cc of cyanide, with hydrochloric acid 22.6 cc of cyanide, with acetic acid 22.5 cc of cyanide. Effect of foreign salts. Sulfates, nitrates, and chlorides of sodium or potassium have no action, whilst the hydrates, carbonates, bicarbonates, sulfites, and nitrites have an important effect. The interference of ammonic salts has already been shown. Salts of silver, zinc, and nickel react with cyanide just as copper does, and consequently interfere. Ferrous salts are sure to be absent, and ferric salts yield ferric hydrate with the ammonia, which is not acted on by the cyanide, but, owing to its bulkiness, it settles slowly. This lengthens the time required for titration, and so modifies the manner of working. An assay should not be worked with ferric hydrate present, unless the standard contains about the same amount of it. On mines it is often inconvenient to separate the copper by means of sulphuretted hydrogen. Hence it is customary to titrate without previous separation. In this case, instead of standardizing the cyanide with electrotype copper, a standard ore should be used. This should be an ore, of the same kind as those being assayed, in which the copper has been carefully determined. Effect of varying copper. In these experiments, 10 cc of nitric acid, 30 cc of ammonia, and water to 200 cc were used. Copper nitrate present, 1.0 cc, cyanide required, 0.7 cc. Copper nitrate present, 10.0 cc, cyanide required 11.2 cc. Copper nitrate present, 20.0 cc, cyanide required 21.7 cc. Copper nitrate present, 50.0 cc, cyanide required 54.5 cc. Copper nitrate present, 100.0 cc, cyanide required 108.1 cc. These results show that under the conditions laid down, the various causes of disturbance nearly neutralize one another, and the results within a fair range are practically proportional. Determination of copper in copper pyrites. Weigh up 2 grams of the dried and powdered ore and place in an evaporating dish about 4 inches in diameter. Cover with 20 cc of nitric acid and put on a hot plate. Evaporate to dryness without further handling. Allow to cool and take up with 30 cc of hydrochloric acid. Boil, dilute, and transfer to a pint flask, filtering if necessary. Make up the bulk with the washings to about 150 cc. Precipitate with sulphuretted hydrogen, filter, and wash back the precipitate into the flask. Add 15 cc of nitric acid and boil down rapidly to 10 cc. Dilute, add 30 cc of dilute ammonia, make up to 150 cc and cool. For the standard, weigh up 0.5 gram of copper, more or less, according to the quantity judged to be present in the assay. Dissolve in 20 cc of dilute nitric acid, boil off nitrous fumes, add 30 cc of dilute ammonia, make up to the same bulk as that of the assay, and cool. Titrate the two solutions side by side and as nearly as possible in the same manner. Since the assay solution is often turbid from the presence of small quantities of lead and of iron from incomplete washing, and since the slight precipitate is very slow in settling, the standard can hardly be compared strictly with the assay. This can be counteracted by precipitating in both solutions a mixture of ferric and aluminic hydrates, which settles readily and leaves the supernatant liquor clear. To effect this, boil the nitric acid solutions with 30 c.c. of a solution containing 15 grams each of alum and ferrous sulfate to the litre. In an actual determination, 2 grams of the ore were taken and compared with 0.5 of a gram of copper. The assay required 57.7 c.c. of cyanide and the standard 52.5 c.c. 52.5 to 0.5 is equivalent to 57.7 to 0.5495. This on 2 grams of ore equaling 27.47%. The same sample by electrolysis gave 27.60% of copper. Determination without previous separation. Dissolve up 2 grams as before, but instead of passing sulphuretted hydrogen, add 30 c.c. of dilute ammonia. Shake well and cool. Prepare a standard by dissolving 0.5 of a gram of copper in 1 c.c. of nitric acid. Add 0.6 of a gram of iron in the form of ferric chloride and 20 c.c. of hydrochloric acid. Dilute to about 150 c.c. Add 30 c.c. of dilute ammonia and cool. Titrate the two solutions side by side. In a determination on the sample last used, 58 c.c. were required for the assay and 53 c.c. for the standard, which indicates 27.3% of copper. This method of working is somewhat rough. Iodide method. This is based upon the fact that when potassic iodide in excess is added to a strong solution of a cupric salt in a faintly acid solution, cuprous iodide is formed and an equivalent of iodine liberated. Note: 2CuSO4 plus 4Ki yield Cu2I2 plus 2I plus 2K2SO4. End note. The iodine is measured by titrating with a solution of sodium hyposulfite, using starch paste as indicator. Note: 2Na2SO3 plus 2I yields 2NaI plus Na2S4O6. End note. The iodine is soluble in the excess of potassium iodide, forming a deep brown solution. The hyposulfite is added until this brown colour is almost removed. Starch paste is then added and strikes with the remaining iodine a dirty blue colour. The addition of the hypo is continued until the blue colour is discharged. The end reaction is sharp. A drop is sufficient to complete it. As regards the titration, the process leaves little to be desired. The quantity of hypo required is strictly proportional to the copper present, and ordinary variations in the conditions of working are without effect. The presence of salts of bismuth masks the end reaction because of the strong colour imparted to the solution by the iodide of bismuth. Under certain conditions there is a return of the blue colour in the assay solution after the finishing point has apparently been reached, which is a heavy tax on the patience and confidence of the operator. This is specially apt to occur when sodium acetate is present, although it may also be due to excessive dilution. The standard hypo solution is made by dissolving 39.18 grams of the crystallized salt Na2S2O3.5H2O in water and diluting to 1 litre. 100 c.c. will equal 1 gram of copper. The starch solution is made by mixing 1 gram of starch into a thin paste with cold water, pouring it into 200 c.c. of boiling water, and continuing the boiling for a minute or so. The solution must be cold before use, and about 2 c.c. is used for each assay. It should not be added until the bulk of the iodine has been reduced. To standardise the hypo, weigh up 0.3 or 0.4 of a gram of pure copper, dissolve in 5 c.c. of dilute nitric acid, boil off nitrous fumes and dilute with an equal bulk of cold water. Add soda solution until a permanent precipitate is obtained, and then 1 c.c. of acetic acid. This should yield a clear solution. Fill an ordinary burette with the hypo, add 3 grams of potassium iodide crystals to the copper solution, and when these are dissolved, dilute to 100 c.c. with water. Run in the hypo solution rather quickly until the brown colour is nearly discharged, i.e. to within 3 or 4 c.c. of the finish. Add 2 c.c. of the starch solution and continue the addition of the hypo a few drops at a time until the tint suddenly changes to a cream colour. The blue colour must not return on standing 3 or 4 minutes. Calculate the standard in the usual way. In assaying ores, the copper is dissolved and separated with sulphuretted hydrogen, as in the other processes, but the sulphide should be washed more completely to ensure the absence of iron salts. The following experiments show the effects of variation in the conditions of the assay. Use a solution of copper sulphate containing 39.38 grams of copper sulphate crystals, CuSO4.5H2O, in the litre. 100 cc's equal 1.00 gram of copper. Effect of varying temperature. The assay after the addition of the potassic iodide must be kept cold, else iodine may be volatilized. Effect of varying potassium iodide. In various descriptions of the process, the amount of iodide required is variously stated at from a few crystals to as much as 10 grams. The proportion required by theory for 1 gram of copper is a little over 5 grams. An excess, however, is required to keep the liberated iodine in solution. On economic grounds, this excess should not be extravagant. If the student uses 10 parts of the iodide for each part of copper in the assay, he will have sufficient. In the experiments, there were used 20 cc's of the copper sulphate with varying amounts of potassic iodide, and the following results were got. Potassic iodide added 1.5 grams, hypo required 20.0 cc's, potassic iodide 3 grams, hypo required 20.0 cc's, potassic iodide 5 grams, hypo required 20.0 cc's. In these, the iodide was added direct to the solution containing the copper, which was afterwards diluted to 100 cc's and titrated. In another series, the iodide was added after the dilution to 100 cc's, and the results were potassic iodide added 1.5 grams, hypo required 20.0 cc's, potassic iodide 3 grams, hypo required 20.1 cc's, potassic iodide added 5 grams, hypo required 20.0 cc's, potassic iodide added 10 grams, hypo required 20.0 cc's. Effect of varying bulk. In these experiments, 20 cc's of copper sulphate were taken, 3 grams of potassic iodide added, and also water to the required bulk. Bulk 20.0 cc's, hypo required 20.0 cc's. Bulk 100.0 cc's, hypo required 20.0 cc's. Bulk 200.0 cc's, hypo required 20.0 cc's. Bulk 500.0 cc's, hypo required 19.9 cc's. In the last of these experiments, the colour was discharged at 18 cc's, but gradually returned until 19.9 cc's had been run in. It will be seen that considerable variation in bulk does not interfere. Effect of acetic acid. These experiments were like the last series mentioned, but the bulk was 100 cc's and varying amounts of acetic acid were added. Acetic acid added 0 cc's, hypo required 20.0 cc's. Acetic acid 1.0 cc's, hypo required 20.1 cc. Acetic acid 5.0 cc's, hypo required 20.1 cc's. Acetic acid 10.0 cc's, hypo required 20.0 cc's. Acetic acid 20.0 cc's, hypo required 20.2 cc's. Acetic acid then does not interfere to any serious extent. Effect of varying sodium acetate. These experiments were like those last mentioned, but without acetic acid, and with varying amounts of sodium acetate. Sodium acetate added 0 gram, hypo required 20.0 cc's. Sodium acetate 1 gram, hypo required 20.0 cc's. Sodium acetate 2 grams, hypo required 20.2 cc's. Sodium acetate 5 grams, hypo required 19.3 cc's. Sodium acetate 10 grams, hypo required 18.2 cc's. In the 5 grams experiment, when the finishing point had been apparently reached, the colour slowly returned. But as the results generally on titrating were not satisfactory, a repetition of the experiment was made with the addition of 5 cc's of acetic acid, which gave an equally bad result. Effect of foreign salts. The conditions of these experiments were the same as before. The salts were added and dissolved before the addition of the potassium iodide. Using 5 grams, or in the case of the acids 5 cc's, the results were as follows. Salt added, none. Hypo required 20.0 cc's. Salt added, dilute H2SO4, hypo required 20.0 cc's. Salt added, acetic acid, hypo required 20.1 cc's. Salt added, NaAC, note sodium acetate, end note, hypo required 19.3 cc's. Salt added, NaCl, hypo required 20.1 cc's. Salt added, KNO3, hypo required 20.2 cc's. Salt added, Na2SO4, hypo required 18.7 cc's. Salt added, AmCl, note ammonium chloride, end note, hypo required 20.0 cc's. Salt added, Am2SO4, note ammonium sulfate, end note, hypo required 19.9 cc's. The low result with the sulfate of soda was evidently due to the formation of a sparingly soluble double salt, which removed copper from the solution. On adding a little acetic acid, the full amount of hypo was required. The effect of the presence of certain metals is important. The method of determining it was to add the substance to the solution containing the copper and partly precipitate with soda solution, then treating with 1 cc of acetic acid, adding the iodide and proceeding as before. Substance added, none. Hypo required 20.0 cc's. Substance added 0.050 gram arsenic, As2O5. Hypo required 20.0 cc's. Substance added 0.050 gram antimony as SbCl5. Hypo required 19.8 cc's. Substance added 0.050 gram lead as Pb(NO3) twice. Hypo required 20.1 cc. A similar experiment with 0.050 gram of bismuth nitrate could not be determined, the end reaction being masked. Bismuth iodide is soluble in potassic iodide, forming a brown solution, the colour of which is very similar to that produced by iodine, and although it does not strike a blue colour with starch, hypo has an action on it. A similar experiment with 0.050 gram of iodine as ferric chloride required 22.3 cc's of hypo, and the colour returned on standing. This shows that ferric acetate liberates iodine under the conditions of the assay. Trying to counteract this by adding to a similar solution 0.5 of a gram of phosphate of soda dissolved in a little water, 19.7 cc's of hypo were required instead of 20.0, but the assay showed signs of returning colour. In standardising, the same result was obtained, whether the copper was present as nitrate or sulfate, before neutralising. Effect of varying copper. With the same conditions as before, but with varying amounts of copper and a proportionally increasing quantity of iodide, the results were copper present 1.0 cc, hypo required 1.0 cc, copper present 10.0 cc, hypo required 10.0 cc, copper present 20.0 cc, hypo required 20.0 cc, Copper present 50.0 cc, hypo required 50.0 cc. Copper present 100.0 cc, hypo required 100.0 cc, showing the results to be exactly proportional. Note: for further information see Appendix B and a paper by J. W. Westmoreland, Journal of the Society of Chemical Industry, Volume 5, page 48. End note. Determination of copper in copper pyrites. Take 2 grams of the dried and powdered ore and treat in a porcelain dish with 20 cc of nitric acid and evaporate to dryness. Take up with 30 cc of hydrochloric acid, dilute and transfer to a pint flask. Make up with water to 200 cc, warm, and pass sulphuretted hydrogen to excess. Filter and wash the precipitate with water acidified with sulphuric acid. Wash the precipitate back into the flask and dissolve with 15 cc of nitric acid. Evaporate almost to dryness. Add 20 cc of water and boil till free from nitrous fumes. Filter off the sulphur and gangue. Neutralize with soda, avoiding excess. Add 1 or 2 cc of acetic acid and shake till clear. Add 5 grams of potassium iodide, dilute to 100 cc and titrate. The following is an example. 0.5 gram of copper required, 50.5 cc hypo. The assay required 55.6 cc hypo, which is equal to 27.5% of copper. End of section 21. Section 22 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 10. Copper, Lead, Thallium, Bismuth, Antimony. Part 4. Colorimetric process. This is based on the blue coloration of ammoniacal copper solutions. The quantity of copper in 100 cc of the assay solution should not be more than 15 milligrams or less than half a milligram. It is not so delicate as most other colorimetric methods, but nevertheless is a very useful one. The manner of working is the same as that described under iron. Standard copper solution. Weigh up 0.5 gram of electrotype copper. Dissolve in 10 cc of nitric acid. Boil off nitrous fumes and dilute to 1 litre. 1 cc equals 0.5 milligram. In nearly all cases it will be necessary to separate the copper with sulphuretted hydrogen from a solution of about 5 grams of the material to be assayed. The filter paper containing the sulphide, and probably much sulphur, is dried and burnt. The ashes are dissolved in 5 cc of dilute nitric acid. 10 cc of dilute ammonia added, and the solution filtered through a coarse filter into a Nessler tube, washing the paper with a little dilute ammonia. The estimation of the colour and calculation of the result are made in the way described on page 44. Reader's note in the section on volumetric assays. End reader's note. The effect of varying conditions on the assay may be seen from the following experiments. Effect of varying temperature. The effect of increased temperature is to slightly decrease the colour, but this can only be observed when a fair quantity of copper is present. 1 cc at 15 degrees showed the colour of 1 cc at 70 degrees. 2.5 cc at 15 degrees showed the colour of 2.7 cc at 70 degrees. 5.0 cc at 15 degrees showed the colour of 5.0 cc at 70 degrees. 10.0 cc at 15 degrees showed the colour of 9.0 cc at 70 degrees. Effect of varying ammonia. The solution must, of course, contain free ammonia. About 5 cc of dilute ammonia in 50 cc bulk is the quantity to be used in the experiments. A larger quantity affects the results, giving lower readings and altering the tint. With small quantities of ammonia, the colour approaches a violet, with larger a sky blue. 2.5 cc with 25 cc of strong ammonia read 2.2 cc, 5.0 cc with 25 cc of strong ammonia, red 4.0 cc. 10.0 cc with 25 cc of strong ammonia, red 8.0 cc. Effect of ammonic salts. The following table shows the results after addition of ammonic salts. 2.5 cc is present. With 10 grams ammonic nitrate, 2.5. With 10 grams ammonic chloride, 2.5. With 10 grams ammonic sulfate, 2.0. 5.0 cc is present. With 10 grams ammonic nitrate, 5.0. With 10 grams ammonic chloride, 5.3. With 10 grams ammonic sulfate, 4.3. 10.0 cc is present. With 10 grams ammonic nitrate, 10.0. With 10 grams ammonic chloride, 10.0. With 10 grams ammonic sulfate, 8.5. These show that sulfates should be avoided, and either nitrate or chloride solutions be used in the standard, as well as in the assay. Determination of copper in a manganese ore. Treat 3 grams of the ore with 20 cc of hydrochloric acid and evaporate to dryness. Take up with 10 cc of hydrochloric acid, dilute to about 200 cc and pass sulphuretted hydrogen until the solution smells of the gas. Filter, burn, take up with 5 cc of dilute nitric acid, add 10 cc of dilute ammonia and filter into the Nestler tube, and make up with the washings to 50 cc. Into the standard tube, put 5 cc of dilute nitric acid and 10 cc of dilute ammonia. Make up to nearly 50 cc with water and run in the standard copper until the colours are equal. In a determination, 4 cc, equaling 2.0 mg of copper, were required. This, in 3 grams of ore, equals 0.07%. Determination of copper in black tin. Weigh up 3 grams of the dried ore, boil with 10 cc of hydrochloric acid, and afterwards add 1 cc of nitric. Boil off nitrous fumes, evaporate to about 5 cc, dilute to 50 cc, add 20 cc of dilute ammonia, stir and filter. If much iron is present, dissolve the precipitate of ferric hydrate in acid and reprecipitate with ammonia. Mix the 2 filtrates and dilute to 100 cc. Take 50 cc for the test. A sample of 3 grams of an ore treated in this way required 5.2 cc of standard copper to produce equality of tint. This gives 0.35%. Determination of copper in tin. Weigh up 1 gram of the sample, transfer to an evaporating dish and cover with 30 cc of aqua regia. Warm until the metal has dissolved, then evaporate almost to dryness. Take up with a few cc of hydrochloric acid and again evaporate. Dissolve the residue in 10 cc of dilute hydrochloric acid and transfer to a 100 cc flask. Add 10 cc of dilute ammonia and make up with water to the containing mark. Filter off 50 cc of the solution into a Nestler glass and determine the copper in it colorimetrically. Examination of commercial copper. Very pure copper can be obtained in commerce owing to the demand for metal of high conductivity for electrical purposes, which practically means for metal free from impurities. Much of the metal sold contains as much as 1% of foreign substances, of which arsenic is the most important. The other elements to be looked for are bismuth, lead, antimony, silver, gold, iron, nickel, cobalt, sulfur and oxygen. In blister copper, which is the unrefined metal, aluminium, silicon and phosphorus may be met with. Oxygen. All commercial copper carries oxygen. Most of it is present as cuprous oxide, which is dissolved by molten copper. The estimation of oxygen is often made by difference. The copper and the other impurities being determined, the rest is assumed to be oxygen. Probably this is nearly correct, but the whole of the oxygen should not be ascribed to cuprous oxide, for any arsenic the metal contained would be present as cuprous arsenite, since arsenide of copper and cuprous oxide could not exist together at the temperature of fusion without interacting. In the report of the analysis, it is best to state the proportion of oxygen, thus oxygen % by difference. There is a method of determination by fusing 5 or 10 grams in a brasked crucible and counting the loss as oxygen, and another method for the determination of cuprous oxide based on the reaction of this substance with nitrate of silver. Note: 3Cu2O plus 6AgNO3 plus 3H2O yields 2Cu2H3O3NO3 insoluble basic salt plus 2Cu brackets NO3 close brackets twice plus 6Ag. End note. About 2 grams of silver nitrate dissolved in 100 c.c. of water is allowed to act upon 1 gram of the copper in the cold. The precipitate is filtered off, washed thoroughly with water, and the basic salt dissolved and determined colorimetrically. 1 part of copper found represents 1.68 part of cuprous oxide, or 0.19 part of oxygen. Copper generally carries from 0.1 to 0.2% of oxygen. Silver is found in most samples, but occurs in variable proportions. When it amounts to 30 ounces per ton, it has a commercial value. To determine its amount, dissolve 10 grams of the copper in 35 c.c. of nitric acid and 50 c.c. of water. Boil off nitrous fumes and dilute to about 100 c.c. 1 or 2 c.c. of dilute hydrochloric acid, 1 to 100 of water, are added, stirred in, and the precipitate allowed to settle for 24 hours. Filter through a double Swedish paper, dry, burn, and cupel the ashes with 1 gram of sheet lead. 10 grams of a sample of copper gave in this way 4.7 milligrams of silver. 10 grams of the same copper, to which 24 milligrams of silver had been added, gave 28.2 milligrams. Gold. To determine it, dissolve 10, 20 or 50 grams of the sample in 35, 70 or 175 c.c. of nitric acid and an equal volume of water. Boil till free from nitrous fumes and dilute to double its volume. Allow to stand for some time. Decant onto a filter, dry, burn, and cupel the ashes with 1 gram of sheet lead. If silver is present, owing to traces of chlorides in the reagents used, parting will be necessary. Note: see gold. End note. Working in this way on 20 grams of copper, to which 1.8 milligrams of gold had been added, a button weighing 2.0 milligrams was obtained. Antimony is not a frequent impurity of copper. It can be detected in quantities over 0.1% by a white residue of Sb2O4, insoluble in nitric acid. With material containing only small quantities of antimony, the white oxide does not show itself for some time, but on long continued boiling it separates as a fine powder. It is best, when looking for it, to evaporate the nitric acid solution to the crystallizing point, to add a little fresh nitric acid and water, and then to filter off the precipitate. After weighing, it should be examined for arsenic and bismuth. Lead. Refined coppers are often free from lead, anything more than traces being seldom found. In coarse coppers it is sometimes present in considerable quantities. Its presence may be detected in the estimation of the copper electrolytically, the platinum spiral becoming coated with a brown or black deposit of lead dioxide. The depth of colour varies with the lead present, and obviously could be made the basis of an approximate estimation. The colour shows itself within an hour or so, but is best observed when all the copper has been deposited. Electrolysing a solution of 1 gram of pure copper to which 0.5 of a milligram of lead had been added, the deposit was dark brown. In a similar solution with 1 milligram of lead it was much darker, and with 2 milligrams it was black. Under the conditions of the assay, the dioxide cannot be weighed, as it partly dissolves on breaking the current. When lead has been found, its quantity may be estimated by evaporating to dryness the nitric acid solution, to which an excess of sulphuric acid has been added, taking up with water and filtering off and weighing the lead sulphate. The separation of traces of lead as chromate is a fairly good one. Dissolve 5 grams of the copper in 17 cc of nitric acid and an equal volume of water. Boil off nitrous fumes, neutralise with soda, and afterwards acidulate with acetic acid and dilute to a litre. Add 20 grams of sodium acetate, warm, and precipitate the lead with a dilute solution of potassium chromate. Copper chromate, yellow, may be at the same time thrown down, but it is readily soluble on diluting. Filter off the precipitate, wash it into a beaker, and pass sulphuretted hydrogen. Oxidise the sulphide and weigh as lead sulphate. Treated in this way, 5 grams of copper yielded sulphate of lead equal to 2.0 milligrams of lead. 5 grams of the same sample, to which 10 milligrams of lead were added, gave 11.4 milligrams. Nickel and cobalt. Nickel is always present in larger or smaller quantities in commercial copper, and perhaps has an influence on the properties of the metal. It is determined as follows. Dissolve 10 grams of the copper in 35 cc of nitric acid and an equal bulk of water. Boil off nitrous fumes and neutralise with soda. Add 2 grams of carbonate of soda dissolved in water, boil and filter. Acidify the filtrate with 2 or 3 cc of dilute nitric acid and dilute to 1 or 1.5 litres. Pass sulphuretted hydrogen through the cold solution till the copper is all down and the liquid smells of the gas. Filter and evaporate the filtrate to a small bulk, and determine the nickel by electrolysing the solution rendered ammoniacal, or by precipitating as sulphide and weighing as sulphate. Note C under nickel. End note. The precipitate after weighing should be tested for cobalt. If present, it is separated with potassium nitrite, as described under cobalt. 10 grams of copper gave 6.0 milligrams of nickel, and another lot of 10 grams of the same copper, to which 10.0 milligrams of nickel had been added, gave 17.2 milligrams. Sulphur. The amount of sulphur in refined copper is very small, seldom exceeding 0.005%. In coarse copper, as might be expected, it is found in larger quantities. In determining it, it is first converted into sulphuric acid, and then precipitated and weighed as barium sulphate. The precipitation cannot be effected from a nitric acid solution. 10 grams of copper are dissolved in nitric acid, as for the other determinations, and then boiled with excess of hydrochloric acid till the nitric acid is completely removed. There is then added a few drops of a dilute solution of baric chloride, and the solution is allowed to stand for some hours. The baric sulphate is filtered off and weighed. The necessity for precipitating from a hydrochloric acid solution is seen from the following determinations. In each experiment 10 grams of copper was used, and a known weight of sulphur in the form of copper sulphate added. Sulphur added 5 milligrams. Sulphur found in hydrochloric acid solution 8 milligrams. Sulphur found in nitric acid solution 0.03 milligrams. Sulphur added 10 milligrams. Sulphur found in hydrochloric acid solution 11 milligrams. Sulphur found in nitric acid solution 0.03 milligrams. Sulphur added 15 milligrams. Sulphur found in hydrochloric acid solution 17 milligrams. Sulphur found in nitric acid solution 12.00 milligrams. Bismuth. Nearly all samples of copper contain bismuth, but only in small quantities. It is best determined colorimetrically, as described under bismuth. The method of concentrating and preparing the solution for colorimetric assay is as follows. Dissolve 10 grams of copper in nitric acid, as in the other determinations. Neutralise with soda, add 1 or 1.5 grams of bicarbonate of soda and boil for 10 minutes. Filter, dissolve the precipitate in hot dilute sulphuric acid, add sulphurous acid and potassium iodide in excess, and boil till free from iodine. Filter and dilute to 500 c.c. Take 50 c.c. of the yellow solution for the determination. A few c.c. of a dilute solution of sulphurous acid, 1 in 100, will prevent the liberation of iodine. The following experiments test the method of separation. 10 grams of copper were treated as above and precipitated with 1.5 gram of soda. The precipitate contained 0.6 milligrams of bismuth. Note equals 0.006%. End note. The filtrate, treated with another 1.5 gram of soda, gave a precipitate which was free from bismuth. To the filtrate from this was added 1.0 milligrams of bismuth, and another fraction was precipitated with 1.5 grams of soda. In this precipitate was found 1.0 milligrams of bismuth. To the filtrate, another milligram of bismuth was added, and the separation with soda repeated. The bismuth was separated from this precipitate with ammonic carbonate before determination, and 0.9 milligram was found. Arsenic. The proportion of arsenic in copper varies from 0.01 to 0.75%, while in coarse copper it may amount to 2 or even 3%. To determine it, dissolve 5, 10 or 20 grams of the copper, according to the amount of arsenic present, in 18 c.c., 35 c.c. or 70 c.c. of nitric acid, and an equal volume of water. Boil off the nitrous fumes, dilute to 100 c.c. and neutralize with soda. Add 1.5 or 2 grams of carbonate of soda dissolved in a little water, and boil. Filter, note washing is unnecessary, end note, and dissolve back into the flask with a little dilute hydrochloric acid. Add 30 c.c. of dilute ammonia and 25 c.c. of magnesia mixture, and allow to stand overnight. The whole of the arsenic is precipitated as ammonic magnesic arsenate in 1 hour, but it is advisable to leave it longer. The precipitate may be dried and weighed, or, better, titrated with uranium acetate. Note see arsenic. End note. To test this method of separation, 10 grams of pure copper were taken, and 0.200 of a gram of arsenic dissolved with it. The arsenic was determined by titration with uranium acetate, and 0.200 of a gram was found. 2 other similar experiments with 0.080 and 0.010 of a gram of arsenic added gave 0.079 and 0.012 of a gram, respectively. Antimony or bismuth may be present without interfering with the titration. With 0.100 of a gram of antimony and 0.100 of a gram of arsenic, 0.100 of a gram of arsenic was found. And in another case, with 0.100 of a gram of bismuth and 0.060 of a gram of arsenic, 0.060 of a gram was found. In these experiments, the antimony and bismuth were present in the assay solution when titrated. For a gravimetric determination, they would require to be removed before precipitating with magnesia mixture. Phosphorus, if present, counts as arsenic in the proportion of 1 to 2.4, but except in the case of coarse coppers it is always absent. Iron, if present, interferes by forming a white flocculent precipitate of ferric arsenate after the addition of the sodium acetate and preliminary to the titration. Each milligram of iron abstracts in this way 1.3 milligrams of arsenic. Iron. Refined coppers carry traces of iron varying from 0.001 to 0.01%. It is best determined during the arsenic estimation. The precipitate of the ammonic magnesic arsenate will contain the whole of the iron as ferric hydrate. On dissolving in hydrochloric acid, neutralizing with ammonia, adding 5 c.c. of sodic acetate, diluting and boiling, it reappears as a white precipitate of ferric arsenate. It is filtered off, the arsenic being estimated in the filtrate, dissolved in warm hydrochloric acid, and determined colorimetrically, as described under iron. A series of experiments testing the separation is there given. Phosphorus. Refined coppers do not carry phosphorus, although it may be present in coarse copper, up to 1% or more. In such samples, the following method is adopted for the estimation of both phosphorus and arsenic. Dissolve 10 grams of copper and 0.1, 0.2 or 0.3 grams of iron wire, according to the amount of arsenic and phosphorus present, in 35 cc of nitric acid and an equal volume of water. Add soda till the free acid is nearly neutralized. Next, add a strong solution of sodium acetate until the solution ceases to darken on further addition. Then dilute with water to half a litre. The solution is best contained in a large beaker. It is next heated to the boiling point and at once removed and allowed to settle. If the precipitate is light coloured, it is evidence that sufficient iron has not been added, or if it is green, from basic copper salts, it shows that the solution was not sufficiently acid. In either case, start afresh. Filter off the precipitate and wash with hot water containing a little sodium acetate. Dissolve it off the filter with hot dilute hydrochloric acid. Add ammonia in excess and pass sulphuretted hydrogen for 5 minutes. Warm at about 70 degrees centigrade for a quarter of an hour. Filter. The clear yellow filtrate contains the arsenic and phosphorus. Add dilute sulphuric acid in excess. Filter off the yellow precipitate of sulphide of arsenic. Dissolve it in nitric acid and titrate with uranium acetate, as described under arsenic. The filtrate from the sulphide of arsenic is rendered alkaline with ammonia, and magnesium mixture added. The solution is stirred and allowed to stand overnight. The precipitate of ammonic magnesic phosphate is filtered off, dissolved, and titrated with uranium acetate, using the same standard solution as is used in the arsenic assay. 0.5 of a gram of arsenic equals 0.207 of a gram of phosphorus. Copper. The method of determining this has been described under electrolytic assay. In the method of concentration by fractional precipitation with sodic carbonate, which is adopted in most of these determinations, the precipitate will contain all the bismuth, iron, and alumina. The arsenic and phosphorus, as cupric arsenate and phosphate, and the greater part of the lead, antimony, and silver. The nickel and cobalt and the sulphur as sulphuric acid will remain in solution with the greater part of the copper. Practical exercises. 1. According to a wet assay, 2 grams of a certain ore contained 0.3650 of a gram of copper. What would you expect the dry assay produce to be? 2. A standard solution is made by dissolving 25 grams of potassic cyanide and diluting to a litre. Assuming the salt to be 98% real cyanide, what would 100 cc of the solution be equivalent to in grams of copper? 3. How would you make a solution of hypo of such strength that 100 cc shall equal 0.633 of a gram of copper? 4. What weight of ore containing 17.0% of copper would you take in order to get about 0.5 of a gram of copper in solution for electrolysis? 5. The solution of copper in nitric acid is affected by the following reaction. 3Cu plus 8HNO3 yields 3Cu bracket NO3 close bracket twice plus 4H2O plus 2NO. What volume of nitric acid will be required to dissolve 1 gram of copper? End of section 22. Section 23 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 10, Copper, Lead, Thallium, Bismuth, Antimony. Part 5. Lead. The chief ore of lead is galena, a sulphide of lead, common in most mining districts, and frequently associated with blende and copper pyrites. It always carries more or less silver, so that in the assay of the ore a silver determination is always necessary. Carbonate, cerasite, sulfate, anglesite, and phosphate, pyromorphite, of lead also occur as ores, but in much smaller quantities. Lead ores are easily concentrated, owing to their high specific gravity, etc., by mechanical operations, so that the mineral matter sent to the smelter is comparatively pure. Lead is readily soluble in dilute nitric acid. The addition of sulfuric acid to this solution throws down heavy, white, and insoluble lead sulfate. Galena is soluble in hot hydrochloric acid, sulphuretted hydrogen being evolved, but the action is retarded by the separation of the sparingly soluble lead chloride. If a rod of zinc is placed in this solution, metallic lead is precipitated on it as a spongy mass, the lead chloride being decomposed as fast as it is formed. The opening up of the ore is thus easily effected, the sulphur going off as sulphuretted hydrogen, and the lead remaining in a form easily soluble in dilute nitric acid. Galena itself is readily attacked by nitric acid, part of the lead going into solution and the rest remaining as insoluble lead sulfate. The sulfate is due to the oxidation of the sulphur by nitric acid. Its amount will vary with the quantity and concentration of the acid used. Sulfate of lead is soluble in solutions of ammonium or sodium acetate, or it may be converted into carbonate by boiling with carbonate of soda. The carbonate, after washing off the sulfate of soda, dissolves easily in nitric acid. The precipitation of lead from acid solutions with sulfuric acid and the solubility of the precipitate in ammonium acetate distinguishes it from all other metals. The addition of potassium chromate to the acetate solution reprecipitates the lead as a yellow chromate. Dry assay. The dry assay of lead is largely used, but it is only applicable to rich or concentrated ores, and even with these only gives approximate results. Both lead and lead sulfide are sensibly volatile at a moderately high temperature, hence it is necessary to obtain a slag which is easily fusible. As a reducing agent, iron is almost always used, and this is added either in the form of an iron rod or the crucible itself is made of this metal. The flux used is carbonate of soda. When a clay crucible is used, the method of working is as follows. Weigh up 25 grams of the dry and powdered ore, mix with an equal weight of soda and 2 grams of tartar, place in a crucible, note E. Battersea round, endnote, and then insert a piece of iron rod about ½ an inch in diameter, and of such a length that it will just allow the crucible to be covered. The rod should be pushed down so as to touch the bottom of the crucible, and the mixture should be covered with a sprinkling of borax. Place in a furnace heated to but not above redness, and cover the crucible. In about 20 minutes the charge will be fused. The fusion is complete when bubbles of gas are no longer being evolved, and then, but not till then, the iron is withdrawn, any adhering buttons of lead being washed off by dipping the rod a few times in the slag. Cover the crucible, leave it for a minute or two, and then pour. Detach the slag when cold by hammering. The weight of the button multiplied by 4 gives the percentage. The commoner errors of students in working the process are too high a temperature and too quick a withdrawal. A sample of ore treated in this manner gave on duplicate assay 17.5 and 17.6 grams of lead, equalling 70.0 and 70.4% respectively. By wet assay, the sample gave 73.3%. Using an iron crucible, the results will be 1% or so higher. The crucible must be made of wrought iron, and if it has been previously used, should be cleaned by heating to dull redness and scraping the scale off with a stirrer. Take 30 grams of the ore, mix with 30 grams of soda and 3 grams of tartar. Put the mixture in the crucible and cover with a sprinkling of borax. Heat for about 20 minutes at not too high a temperature, and then scrape down the slag adhering to the side with a stirrer. Leave in the furnace till action has ceased. Before pouring, tap the pot gently and then tilt it so as to make the slag wash over the part of the crucible along which the charge is to be poured. Pour, and when cold, clean and weigh the button of metal. A crucible may be used from 10 to 20 times. These assays are for ores containing the lead chiefly as sulfide. For oxidized ores, charcoal or tartar is employed as the reducing agent. The student may practice on red lead as follows. Take 30 grams of red lead, mix with 10 grams each of borax and soda and about 1.5 gram of powdered charcoal. Place in a small clay crucible with a cover, note C. Battersea round, end note. Fuse at a gentle heat and pour when action ceases. This assay will only take a few minutes. Where lead is present as phosphate, as in the case of pyromorphite, or mixed with phosphates, as sometimes happens, carbonate of soda is a suitable flux, but the phosphate of soda which is formed makes a thick, tenacious slag, which is very apt to be carried out of the pot by the escaping gas. A wide-mouthed clay pot is taken, and a little fluorspar added. For the assay of pyromorphite, the following charge may be used: ore 20 grams, soda 25 grams, tartar 7 grams, and fluorspar 5 grams, and 2 grams of borax as a cover. This will melt down in about 10 minutes, and should be poured as soon as tranquil. Wet assay. In the case of galena, the best method of getting the lead into solution is to treat with hydrochloric acid and zinc. Put 1 gram of the ore in an evaporating dish 4 inches across, and cover with 10 cc of dilute hydrochloric acid. Heat till the evolution of sulphuretted hydrogen becomes sluggish, and then drop in a piece of zinc rod. If the solution effervesces too strongly, dilute it. Continue the heating until the sulphide is seen to be all dissolved. When the lead is all precipitated, pour off the liquid and wash twice with cold water. Peel off the precipitated lead with the help of a glass rod, and then clean the zinc. Cover the lead with 20 cc of water and 5 cc of dilute nitric acid, and heat gently till dissolved. All the lead will be in solution, and when filtered off from the gangue will be ready for a gravimetric determination. For volumetric work, this filtering is unnecessary. The chief objection to this method is that commercial zinc carries considerable quantities of lead. Although this can be determined and allowed for, the correction required is in most cases too large to be satisfactory. The following method is applicable in all cases, but is more troublesome. Treat 1 gram of the ore with 10 cc of dilute nitric acid in an evaporating dish covered with a clock glass, and evaporate till nearly dry. Take up with 50 cc of water and add 10 cc of dilute sulphuric acid. Filter. The residue contains the lead as sulphate, together with the insoluble matter of the ore and globules of sulphur. Warm with a solution of ammonium acetate and filter. The lead will be in the filtrate and is recovered in a state fit for direct gravimetric estimation by the addition of dilute sulphuric acid. If the volumetric method is to be used, the lead sulphate should be dissolved out with a solution of sodium acetate instead of with the ammonium salt solution. Gravimetric determination. The lead is separated and precipitated as sulphate, as already described. The solution must be allowed to stand, and the clear liquid be decanted through a filter. Transfer the precipitate and wash with very dilute sulphuric acid. Note 1 or 2 cc in 100 cc of water. End note. The acid must be completely removed with 1 or 2 washes with cold water, and then with alcohol. The volume of liquid required for washing is small, as the precipitate is dense and easily cleaned, but the washing must be carefully done, since if any acid remains it will on drying char the paper and render the subsequent work troublesome. Dry, transfer to a watch glass, and burn the filter paper, collecting its ash in a weighed porcelain crucible. The filter paper must be freed as much as possible from the lead sulphate before burning, and the ash treated with a drop or 2 of nitric and sulphuric acids. Transfer the lead sulphate to the crucible. Ignite gently, keeping the temperature below redness. Cool and weigh. The precipitate will contain 73.6% of lead oxide or 68.3% of lead. Determination of lead in commercial zinc. Take 10 grams of zinc and treat, without heating, with 60 c.c. of dilute hydrochloric acid. When the zinc is nearly all dissolved, decant off the clear liquid and dissolve the residue in 2 c.c. of dilute nitric acid. Evaporate till most of the acid is removed. Dilute to 20 or 30 c.c. with water and add 10 c.c. of dilute sulfuric acid. Filter off and weigh the lead sulfate. 10 grams treated in this way gave 0.1610 of a gram of lead sulfate, equivalent to 1.10% of lead. Volumetric method. This is based upon the reaction between chromate of potash and soluble lead salts in neutral solutions, whereby an insoluble yellow chromate of lead is produced. Note: K2CrO4 plus Pb open bracket NO3 close bracket twice yields PbCrO4 plus 2KNO3. End note. An excess of the chromate is required to complete the reaction, so that the point at which an indicator shows the presence of undecomposed chromate cannot be satisfactorily taken as the finish. Therefore an excess of the standard chromate must be run in, and such excess determined. Chromate of lead is not precipitated from strong nitric acid solutions, and only incompletely from dilute ones. Acids generally are detrimental to the precipitation and must be neutralized before titrating. If the lead is present as sulfate in sodic acetate solution, it is well to render it distinctly alkaline with ammonia. Lead chromate precipitated in the cold is a lemon yellow light precipitate, very difficult to filter. On heating to 40 degrees centigrade, the colour becomes orange. At 60 degrees centigrade it assumes a deeper hue and becomes flocculent, and at a boiling temperature it still further darkens and settles readily. These changes in colour are not due to any chemical change, as will be seen by testing the filtrate for chromium or lead. This is an advantage to the assay, since it is only at the higher temperature that the precipitate can be easily filtered. The lead is not completely precipitated, but the amount remaining in solution is only 2 or 3 milligrams, which is just sufficient to give a dark coloration with sulphuretted hydrogen. The standard chromate of potash solution is made by dissolving 7.13 grams of bichromate of potash and 2.0 grams of caustic soda in water and diluting to 1 litre, or 9.40 grams of the neutral chromate K2CrO4 may be dissolved and diluted to 1 litre. 100 c.c. will be equivalent to 1.000 gram of lead. Standard lead solution. 16 grams of nitrate of lead, Pb open bracket NO3 close bracket twice, are dissolved in water and diluted to 1 litre. 100 c.c. will contain 1.000 gram of lead. Acetate of soda solution. 250 grams of the crystallized salt, NaAc.3H2O, are dissolved and diluted to 1 litre. Use 40 c.c. for each assay. In the titration, the assay solution should measure 150 to 200 c.c. and should be boiling or nearly so. It is best contained in a pint flask, and the standard chromate solution used with an ordinary burette. Run in the chromate solution in a steady stream until the whole of the lead has been precipitated. The amount required for this may be calculated. For example, 1 gram of an 80% ore would require 80 c.c. A little of the assay may be filtered off, and if it does not show a yellow colour in the filtrate, run in 2 c.c. more of the standard solution, and continue this addition till a colour is shown. After this, run in another cc to ensure an excess. Dilute to 250 c.c. and heat to boiling. Allow to settle for 3 or 4 minutes. Filter off 50 c.c. into a Nessler glass and determine the excess of chromate colorimetrically. The excess found in the 50 c.c. must of course be multiplied by 5 and then be deducted from the quantity of chromate originally run into the assay solution. The quantity to be deducted should not exceed 3 cc. Where a number of determinations are made, the colorimetric estimation is facilitated by using a series of standard vials, similar to those described under the electrolytic copper assay. The determination is rendered sharper and less liable to error by the addition of a few drops of acetic acid to convert the chromate into bichromate. The same chromate solution must be used in this determination as was used in the precipitation. In standardizing the chromate solution, the standard lead nitrate solution is used. A quantity containing about as much lead as the assay is supposed to contain is measured off, rendered alkaline with dilute ammonia, and then neutralized with acetic acid, using a small piece of litmus paper dropped into the solution as indicator. Then dilute, boil, and titrate. When the lead in the assay has been separated as sulfate and dissolved in sodic acetate, less chromate is apparently required, and in this case it will be necessary to precipitate the lead in the standard with an equivalent of sodic sulfate, and redissolve in sodic acetate just as in the assay. In these solutions, although there is considerable chromate in excess, a further addition of 5 or 6 cc of the chromate solution will cause a further precipitate. The following experiments show the effect of variation in the conditions of the assay. Effect of varying temperature. 20 cc of lead nitrate solution and 10 grams of sodium acetate were used. Diluted to 200 cc, heated to the desired temperature, and titrated. The results were: temperature 15 degrees, chromate required 19.8 cc, temperature 30 degrees, chromate required 19.5 cc, temperature 50 degrees, chromate required 19.3 cc, temperature 100 degrees, chromate required 19.2 cc. The first two of these filtered badly, the precipitate coming through the filter. The last was very satisfactory in the working. Effect of varying bulk. Using 20 cc of lead nitrate and 10 grams of sodium acetate as before, diluting to the required bulk, heating to boiling, and titrating. The results were: bulk 100.0 cc, chromate required 19.6 cc, bulk 200.0 cc, chromate required 19.3 cc, bulk 500.0 cc, chromate required 19.4 cc, bulk 1000.0 cc, chromate required 19.4 cc. Effect of varying acetic acid. Since the experiments are carried out in the presence of sodic acetate, acetic acid is the only acid whose effect need be considered. Working as before, but with 200 cc bulk and varying amounts of the acid, the results were: acid present, none, chromate required 19.7 cc, acid present 10.0 cc, chromate required 19.1 cc, acid present 20.0 cc, chromate required 18.5 cc, acid present 40.0 cc, chromate required 17.3 cc. These experiments show that only slight quantities of acid are admissible. Effect of varying sodium acetate. With the same conditions as before, but with varying weights of sodium acetate, the results were: sodium acetate present, none, chromate required 19.7 cc, sodium acetate present 5 grams, chromate required 19.6 cc, sodium acetate present 10 grams, chromate required 19.6 cc, sodium acetate present 25 grams, chromate required 18.8 cc, sodium acetate present 50 grams, chromate required 17.8 cc. These experiments show that excessive quantities of sodium acetate must be avoided. Ammonium acetate interferes to a greater extent, and if both acetic acid and this salt are present, each exerts its disturbing influence. With 10 grams of ammonium acetate, 19.4 cc of the chromate solution were required instead of 19.7 in the absence of this salt. With 10 grams of the acetate and 10 cc of acetic acid, only 18.6 cc were required. Effect of foreign salts. As already stated, sulfates interfere. 20 cc of the lead nitrate solution were taken, precipitated with sulfate of soda, and the precipitate dissolved in 10 grams of sodium acetate, and titrated as before. Duplicate experiments required 18.6 cc and 18.7 cc of the chromate solution. A similar experiment with 40 cc of lead nitrate required 37.4 cc of the chromate. If the sulfate had not been present, the results would have been 19.7 cc and 39.4 cc respectively. Effect of varying lead. In these experiments the conditions were as before, but with varying amounts of lead. Lead nitrate solution present 10.0 cc, chromate solution required 9.4 cc. Lead nitrate solution present 20.0 cc, chromate solution required 19.7 cc. Lead nitrate solution present 50.0 cc, chromate solution required 48.8 cc. Lead nitrate solution present 100.0 cc, chromate solution required 98.2 cc. Determination of lead in galena. Weigh up 1 gram of the powdered and dried ore and boil in an evaporating dish with 10 cc of dilute hydrochloric acid. When the action becomes sluggish, dilute with an equal bulk of water and add a weighed piece of zinc rod, about 1 inch long and 1/4 inch across. Keep up a moderate action by warming till the ore is seen to be completely attacked and the lead precipitated. Decant off the solution, wash once, strip off the lead, wash and weigh the remaining zinc. Dissolve the lead in 5 cc of dilute nitric acid and 5 cc of water with the aid of heat. Dilute and transfer to a pint flask. Add a slight excess of dilute ammonia and render faintly acid with acetic acid. Dilute to 150 cc, heat to boiling and run in the standard chromate in slight excess, noting the amount required, and make up to 250 cc with water. Boil the solution, allow to settle for a minute or so, filter off 50 cc and determine the excess of chromate colorimetrically. As an example, 1 gram of an impure galena was precipitated with 75 cc of standard chromate. Note: 100 cc equals 1.020 of a gram of lead. End note. The excess found in 50 cc was 0.3 cc, which multiplied by 5 gives 1.5 cc as the excess in the whole solution. The remaining 73.5 cc of chromate required by the assay are equivalent to 0.7497 of a gram of lead. The zinc used up weighed 1.5 grams and contained 0.0165 of a gram of lead. Thus we get lead in the assay 0.7497 of a gram, lead from the zinc 0.0165 of a gram. Therefore, lead in the galena 0.7332 of a gram, equivalent to 73.3%. Another sample in which the galena was accompanied with a large quantity of pyrites gave the following results. 3 grams were treated with 30 cc of dilute hydrochloric acid and a rod of zinc. The zinc and lead were carefully transferred to another vessel, the zinc cleaned, and the lead dissolved in 5 cc of dilute nitric acid and 20 cc of water, treated as before. 14.5 cc of the chromate were required, equals 0.1479 of a gram of lead. Lead in 2 grams of zinc equals 0.0220 of a gram of lead. Therefore, lead in 3 grams of the ore equals 0.1259 of a gram of lead, equivalent to 4.20%. The same ore gave, by separation of the lead with sulphuretted hydrogen and conversion into sulfate, 4.16%. With fairly pure ores free from sulfate, the assay may be made more quickly as follows. Dissolve 1 gram of the finely powdered ore by boiling gently with 40 cc of dilute hydrochloric acid for 15 minutes. Cool, add a few drops of permanganate, neutralize with ammonia, add acetic acid and a little sodium acetate. Titrate with standard chromate. Colorimetric process. This is based upon the brown coloration produced in very dilute solutions of lead by the action of a solution of sulphuretted hydrogen. The quantity of lead in the 50 c.c. of the assay solution must not much exceed 0.5 of a milligram, nor be less than 0.01. The sulphuretted hydrogen is used in the form of a solution and is not bubbled through the assay. The principle of working is the same as previously described. Standard lead solution. Each cc of this should contain 0.1 of a milligram of lead. It is made by diluting 10 c.c. of the solution of lead nitrate, described under the volumetric process, to 1 litre. Sulphuretted hydrogen water is made by passing a current of the washed gas into water till the latter is saturated. 5 c.c. of the sulphuretted hydrogen water are put into a Nessler tube, the measured portion of the assay solution added, and the whole diluted with water to the 50 c.c. mark. Into the standard Nessler tube the same amount of the sulphuretted hydrogen water is put and diluted to nearly 50 c.c. The standard lead solution is then run in till the tints are equal. The assay solution must not contain much free acid, and if the conditions will allow it, may with advantage be rendered alkaline with ammonia. The chief cause of disturbance is the precipitation of lead sulphide, forming a black turbid solution instead of a brown clear one. This may be caused by using hot solutions or an excess of acid. Other metals precipitable by sulphuretted hydrogen must be absent, as well as strong oxidizing agents. Effect of varying temperature. The effect of increased temperature is to change the colour from brown to black and to render the estimation difficult. 1 cc at 15 degrees centigrade showed the colour of 0.5 cc's at 60 degrees centigrade. 2 cc's at 15 degrees centigrade showed the colour of 1.5 cc's at 60 degrees centigrade. 3 cc's at 15 degrees centigrade showed the colour of 5.0 cc's at 50 degrees centigrade. Effect of varying time. The colour becomes lighter on standing. 2 cc's on standing 10, 20 and 40 minutes became equal in colour to 1.7 cc's. Effect of acids and ammonia. 2 cc's of the solution with 2 cc's of dilute hydrochloric acid became cloudy and equivalent to about 2.5 cc's, and a similar result was got with 2 cc's of dilute sulfuric acid. With 2 cc's of dilute ammonia, the solution became somewhat darker, or equal to 2.3 cc's, but gave a very clear solution easy to compare. Determination of lead in commercial zinc. Dissolve 0.1 of a gram of the metal in 1 cc of dilute nitric acid. Evaporate till a solid separates out. Dilute to 100 cc's with water and take 20 cc's for assay. A sample treated in this way required 2.4 cc's. This multiplied by 5 gives 12.0 cc's, equivalent to 1.2 milligram of lead, or 1.2%. By gravimetric assay, the sample gave 1.10%. Practical exercises. 1. 30 grams of galena gave on dry assay 21 grams of lead, and this on cupellation gave 15 milligrams of silver. Calculate the results in percents of lead and in ounces of silver to the ton of ore. 2. How many ounces of silver to the ton would be contained in the lead got from this ore if the loss in smelting is equal to that of the assay? 3. Having given you a sample of white lead freed from oil by washing with ether, how would you proceed to determine the percentage of lead in it? End of section 23. Section 24 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 10. Copper, Lead, Thallium, Bismuth, Antimony. Part 6. Thallium. Thallium is a rare metal found in small quantities in some varieties of iron and copper pyrites, and in some lithia micas. It resembles lead in appearance. Its compounds resemble the salts of the alkalis in some respects, and in others those of the heavy metals. It is detected by the green colour which its salts impart to the flame. This, when examined with the spectroscope, shows only one bright green line. It is separated and estimated by dissolving in aqua regia, converting into sulphate by evaporation with sulphuric acid, separating the second group of metals with sulphuretted hydrogen in the acid solution, boiling off the excess of the gas, nearly neutralizing with carbonate of soda, and precipitating the thallium with an excess of potassic iodide. On allowing the liquid to stand for some time, a bright yellow precipitate of thallous iodide separates out. This is collected on a weighed filter, washed with cold water, finishing off with alcohol, dried at 100 degrees centigrade, and weighed. The precipitate is thallous iodide, TlI, and contains 61.6% of thallium. Bismuth. Bismuth is nearly always found in nature in the metallic state, but occasionally it is met with as sulphide in bismuthine, and as carbonate in bismutite. It is also found in some comparatively rare minerals, such as tetradymite, combined with tellurium, and associated with gold. In minute quantities it is widely distributed. It is a common constituent of most copper ores, hence it finds its way into refined copper, which is seldom free from it. It is occasionally met with in silver, in sufficient quantity to interfere with the working qualities of that metal. Bismuth compounds are used in medicine and in the manufacture of alloys. Bismuth possesses many useful properties. It has considerable commercial value and sells at a high price. The metal is brittle, breaks with a highly crystalline fracture, and has a characteristic reddish-yellow colour. It is almost insoluble in hydrochloric, but readily dissolves in nitric acid, and gives, if the acid is in excess, a clear solution. Bismuth salts have a strong tendency to separate out as insoluble basic compounds. This is more especially true of the chloride, which, on diluting with a large volume of water, becomes milky, the whole of the bismuth separating out. The nitrate, carbonate, and hydrate yield the oxide, Bi2O3, on ignition. This oxide closely resembles litharge. It combines with silica, forming fluid slags, and at a red heat is liquid enough to be absorbed by a cupel. In fact, bismuth may take the place of lead in cupellation. The metal itself is easily fusible and may be separated from its ores by liquation. The assay of bismuth by wet methods presents little difficulty and is fairly accurate. The price of the metal is such that only methods which yield good results should be adopted, and since bismuth is volatile at the temperature of the furnace and is found mixed with ores not easy to flux, as also with metals which are not easily separated by the dry method, the dry assay can only be considered as having a qualitative value. Dry assay. By liquation. This is adapted to ores containing the bismuth as metal. Take 20 grams of the powdered ore and place in a crucible with a perforated bottom. Put this crucible into another of about the same size and lute the joint. Lute on a cover, place in the furnace and heat to redness. The bismuth melts readily and drains into the lower crucible, from which, when cold, it is taken and weighed. By fusion. For fairly pure ores, the process is as follows. Take 20 grams of the ore and mix with 20 grams of fusion mixture, 10 grams of salt, and 5 or 10 grams of potassium cyanide. Place in a crucible, cover, and fuse at a moderate temperature for about 15 minutes. Pour. When cold, detach the metal and weigh. For coppery ores in which the metals are present as sulphides, use the fluxes just given with 2 grams of charcoal instead of the cyanide and a little sulphur. For coppery ores in which the metals are present as oxides, mix 20 grams of the ore with 10 grams of fusion mixture, 4 grams of salt, 4 grams of sulphur and 2 grams of charcoal, and fuse. A considerable percentage of bismuth is lost in these assays, it is stated as being nearly 8% of the metal present. Wet methods. Detection. Bismuth is detected by dissolving the substance in nitric or hydrochloric acid and precipitating the diluted solution with sulphuretted hydrogen. The precipitated sulfides, after digesting with soda and washing, are dissolved in nitric acid and the solution boiled with ammonium carbonate. The precipitate is washed and then warmed with dilute sulfuric acid. The solution will contain the bismuth. Add a solution of potassium iodide in excess and boil. A yellow or dark brown solution proves that bismuth is present. Another good test for small quantities of bismuth is to add tartaric acid to the solution to be tested, and then to make it alkaline with potash. Add a few cc's of Schneider's liquid and heat. Note: Schneider's liquid, made by dissolving 12 grams of tartaric acid and 4 grams of stannous chloride in water and adding potash solution till it is alkaline. The solution should remain clear on heating to 60 degrees or 70 degrees centigrade. End note. A brownish black colour is produced by as little as 1 part of bismuth in 200,000 of solution. The test is not applicable in the presence of mercury, copper or manganese. Compounds of bismuth fused with cyanide of potassium in a Berlin crucible readily give a globule of bismuth, which is recognized by its appearance and fracture. Solution and separation. The solution of bismuth compounds presents no difficulty. They are soluble in nitric acid or aqua regia, and provided the solution is sufficiently acid, they remain dissolved. In separating it from other metals, the solution is made up to about 100 cc's and treated with a current of sulphuretted hydrogen. The bismuth comes down in a tolerably strong acid solution. The sulfide is decanted onto a filter and washed. It is next digested with ammonic sulfide, or better, especially when other metals are present, dissolved in nitric acid, and treated with an excess of ammonia and a current of sulphuretted hydrogen. The precipitate is filtered off and evaporated to dryness with nitric acid. It is taken up with a few drops of sulfuric acid and a little water, and warmed and filtered if necessary. The filtrate is nearly neutralized with ammonia, ammonium carbonate added in slight excess, and the liquid heated to boiling and filtered. The bismuth will be contained in the precipitate, with perhaps traces of lead, antimony, tin, or sometimes iron, from incomplete separation or washing. When only traces of a precipitate are got, it must be tested. The bismuth precipitate is readily soluble in dilute nitric acid. Gravimetric determination. The bismuth having been separated and dissolved in nitric acid, note, it must be remembered that arsenate of bismuth is completely insoluble in this acid, end note, is precipitated after dilution by the addition of carbonate of ammonium in slight excess and boiling. The precipitate is filtered off, washed with hot water, dried, ignited and weighed. The ignition should be performed carefully at not above a low red heat. The oxide which is formed has at this temperature a dark yellow or brown colour and becomes yellow on cooling. It is bismuthic oxide, Bi2O3, and contains 89.65% of bismuth. Fusion with potassium cyanide at a temperature just sufficient to melt the salt reduces it to the metal, which falls to the bottom and runs into a globule. The button of metal may be weighed, but it often sticks tenaciously to the bottom of the crucible. The precipitation with ammonic carbonate must not be made in a sulphate or chloride solution, since basic compounds would then be thrown down, and the result on weighing would either be too low because of the volatilization of the chloride, or too high because of the retention of sulfuric acid. Bismuth compounds in a nitric acid solution are readily decomposed by the electric current, but the deposited bismuth is not coherent. It comes down in shaggy tufts which are difficult to wash and easy to oxidize. Volumetric assay. There are two methods which have been proposed. One based on the precipitation as chromate, and the estimation of the chromic acid, and the other on the precipitation as oxalate, and subsequent titration with permanganate of potash. These offer little advantage over the easy gravimetric determination. Colorimetric method. Bismuth iodide dissolves in excess of potassium iodide, forming a yellow-coloured solution, indistinguishable in colour from that given by iodine. The colour, however, is not removed by boiling or by sulphurous acid. Since none of the commoner metals give such a colour, and free iodine is easily separated by boiling, this method is specially suited for small determinations of bismuth. It requires a solution of bismuth, made by dissolving 0.1 gram of bismuth in a drop or so of nitric acid, evaporating with a little sulphuric acid, and diluting with water to 1 litre. 1 cc will contain 0.1 mg of bismuth. And a solution of sulphurous acid, made by diluting 10 cc of the commercial acid to 1 litre with water. The determination is made in the usual way. 50 cc of the prepared solution, which should not carry more than 0.75 mg nor less than 0.01 mg of bismuth, are placed in a Nessler tube, and the colour compared with that observed in a similar tube containing water and potassium iodide on adding the standard solution of bismuth. The assay solution is prepared by separating the bismuth with sulphuretted hydrogen, boiling the precipitate with nitric acid, and evaporating with sulphuric acid. Take up with water, add 10 or 20 cc of solution of potassium iodide, boil off any iodine liberated, dilute, filter, and make up to 100 cc. According to the depth of colour, take 10, 20 or 50 cc and transfer to the Nessler tube. Add a few cc of the solution of sulphurous acid. Into the other Nessler tube, put as much potassium iodide solution as is contained in the assay tube, with sulphurous acid and water to within a few cc of the bulk. Then add the standard bismuth solution till the tints are equal. The student must be careful not to confuse the colour of the bismuth iodide with that of free iodine. If the yellow colour is removed by boiling and returns on standing, it is due altogether to iodine. If it is lessened by the addition of a few drops of the dilute sulphurous acid, it is in part due to it. Hence the necessity of having a little free sulphurous acid in each tube. A strong solution must not be used, since it liberates iodine from potassium iodide. The following experiments illustrate the effect of variation in the conditions of the assay. Effect of varying temperature. At a higher temperature the colour is somewhat lessened. 1 cc at 15 degrees centigrade showed the colour of 0.8 cc at 70 degrees centigrade. 2.5 cc's at 15 degrees centigrade showed the colour of 2.0 cc's at 70 degrees centigrade. 5.0 cc's at 15 degrees centigrade showed the colour of 5.0 cc's at 70 degrees centigrade. Effect of free acid. 2.5 cc's with 5 cc's of nitric acid equaled 2.5 cc's. 5.0 cc's with 5 cc's of sulphuric acid equaled 5.0 cc's. Hydrochloric acid almost completely removes the colour, which however is restored by the addition of a few crystals of potassium iodide. Effect of alkalis. Ammonia, soda or potash destroys the colour, but it is restored on acidifying with nitric or sulphuric acid. Effect of ammonic salts. The following table shows the results after addition of ammonic salts. 1.0 cc's present with 10 grams ammonic nitrate, 0.9 cc's. With 10 grams ammonic sulfate, 1.1 cc. 2.5 cc's present with 10 grams ammonic nitrate, 2.5 cc's. With 10 grams ammonic sulfate, 2.7 cc's. 5.0 cc's present with 10 grams ammonic nitrate, 5.0 cc's. With 10 grams ammonic sulfate, 5.5 cc's. Ammonic chloride, like hydrochloric acid, removes the colour, which may be restored on the addition of more potassium iodide. Nitrates and sulfates do not thus interfere. Effect of foreign salts. Sodic hyposulfite almost completely removes the colour. Copper salts liberate iodine, but when this has been removed by boiling and the cuprous iodide has been filtered off, there is no further interference. Dilute solutions of lead salts give no colour. Practical exercises. 1. A fusible alloy is made up of 8 parts of bismuth, 5 of lead, and 3 of tin. What weight of oxide of bismuth, Bi2O3, would you get on the analysis of 1 gram of it? 2. What weight of bismuth can be got from 2 grams of the subnitrate, BiONO3.H2O? 3. How would you detect and separate arsenic, lead, and copper in a sample of bismuth? Antimony. Antimony occurs in the native state, but is rare. Its common ore is antimonite, the sulfide, Sb2S3. Jamesonite and other sulfides of lead and antimony are frequently met with. Sulfide of antimony is also a constituent of ferrures and of many silver ores. Antimonite occurs generally in fibrous masses, has a lead-like metallic luster, is easily cut with a knife, and melts in the flame of a candle. Antimony itself has a very crystalline fracture, is brittle, and has a bluish-white colour. It is used in the preparation of alloys with lead and tin for the manufacture of type metal. It is readily fusible and imparts hardness and the property of taking a sharp cast to its alloys. It is practically insoluble in hydrochloric acid. On boiling with strong nitric acid, it is converted into antimonic oxide, Sb2O5, which is a powder almost insoluble in this acid or in water, but which may be got into solution with difficulty by the prolonged action of hydrochloric and tartaric acids. Antimonic oxide is converted on ignition into the tetroxide, Sb2O4, with loss of oxygen. Antimony forms 2 series of salts, antimonious and antimonic, and advantage is taken of this in its determination volumetrically. Either sulfide of antimony yields antimonious chloride on boiling with hydrochloric acid, sulphuretted hydrogen being given off, and in the case of antimonic sulfide, sulphur is deposited. Antimonious is converted into antimonic chloride by treatment with permanganate of potash in an acid solution. Antimonic chloride and potassium iodide react, forming antimonious chloride and free iodine. This latter may be got rid of by boiling. Sulfide of antimony is separated from the ore by liquation. This regulus is met with in commerce as crude antimony. Dry assay. An approximate determination of the amount of sulfide of antimony in an ore may be made by fusing and liquating in a luted double crucible in the manner described under bismuth. This is unsatisfactory. The determination of metallic antimony in an ore is made either by fusion with potassium cyanide or by fusion with iron, as in the galena assay. Both methods yield poor results, and where iron is used it must be added in quantity only sufficient for desulfurizing. This amounts to about 40% in pure ores. If the iron is in excess, it alloys with the reduced antimony. If, on the other hand, it is insufficient, the metal will contain sulfur, or sulfide of antimony will be lost in the slag. The following note, for which we are indebted to Mr. Bedford McNeill, ARSM, gives a description of the method adopted in the commercial valuation of a parcel of antimony ore. The antimony smelter, when he wishes to determine the value of any parcel of ore, usually the sulfide, that may be offered for sale, practically has recourse to the smelting operation. That is, a quantity of 200 or 300 weights taken by his sampler having been obtained, he treats it under the immediate supervision of the foreman smelter, as if it formed part of the ore in process of daily reduction at his works. He thus determines by actual trial the output which it may fairly be anticipated will be yielded by the bulk, and upon the result of this trial or assay, and the knowledge gained of the actual behaviour of the ore under treatment, he bases his tender, knowing that should he secure the parcel, he may confidently expect a similar return. Briefly, the process consists of the three ordinary operations of A. Singling, or removing most of the antimony from the ore, B. Doubling, C. Refining, or starring. But in the assay, sufficient information is generally given by the first two of these. A new pot having been taken and made hot in the furnace, 40 or 45 pounds of the ore is weighed in. Note the mineral from the necessities of sampling not exceeding walnut size. End note. 1 to 3 pounds of salt cake is now added to render the separation of the resulting sulphide of iron more easy, as also to assist in the fusion of the gangue. 20 to 25 pounds of tin plate scrap, beaten more or less into ball shape, is weighed, placed on the top of the ore and salt cake, and the whole brought to a state of fusion. The foreman from time to time takes notice of the behaviour of the ore under the working conditions. Ores that manifest a tendency to boil or froth require the admixture of other, more sluggish mineral in order to render their reduction economically practicable. After 1 1/4 to 1 1/2 hours, the time depending mainly on the temperature, the contents of the crucible are usually in a state of tranquil fusion. The pot is now lifted from the fire and its contents transferred to a conical iron mould, the empty pot being immediately put back into the fire and the latter mended, with sufficient coke for another run. The conical mould, note, when dealing with a strange ore, and the possibility of insufficient iron being present to satisfy the sulphur contents, end note, is wiped inside with clay previous to pouring in the molten charge. Otherwise the mould itself will be attacked, and the contents after solidifying will require to be chiselled out piecemeal. A further 40 pounds of the ore is now charged into the crucible with iron as above, but before this second charge is ready to be drawn, an inspection of the first may suggest the addition of either 3 or 5 pounds more iron, or 5 or 10 pounds more ore. It is a good fault rather to aim at an excess of iron as tending to clean the ore from antimony. Any of the latter that, from an insufficiency of iron, may be left in the slag from the first process, being irretrievably lost. Whereas if the iron be in excess, that which is combined with the crude antimony resulting from the first process is easily got rid of by adding 3 to 5 pounds or so of ore in the second process. This latter, as practised for the determination of the value of a parcel of ore, consists in selecting 2 of the best quality singles, resulting from perhaps 4 or 5 trials as above, and running them down with a few pounds of salt cake, or a mixture of salt cake with American potash, and, as is generally necessary, a small addition of ore. Upon the final result, note, confirmed perhaps on another pair of singles, and judging from the total weight or output of the metal as calculated from the ore used in singling, plus any added in the doubling, the crystalline fracture and face of the metal, its colour, etc. End note. The price to be offered for the parcel of ore is fixed. Wet methods. Detection. The antimony, if any, being got into solution by treating the ore with hydrochloric acid or aqua regia, may be detected by evaporating with hydrochloric acid, diluting, and filtering into the cover of a platinum crucible, or better, a platinum dish. A small lump of zinc is then added, and if antimony is present, the dish will in a minute or two be stained black with a deposit of metallic antimony. This stain is removed by nitric, but not by hydrochloric acid. The reaction is delicate and characteristic. Arsenic, under like conditions, is evolved as arseniuretted hydrogen, and tin is deposited as metal on the zinc. Solution. Ores, etc. containing antimony are best opened up by boiling with hydrochloric acid or aqua regia. Treatment with nitric acid should be avoided wherever possible, since it forms antimonic acid, which is subsequently dissolved only with difficulty. Salts of antimony in solution have a tendency to form insoluble basic salts, so that care must be exercised in diluting. Compounds such as antimonite, which are soluble in hydrochloric, should be dissolved at once in that acid. Separation. To the solution add potash in excess and a little free sulphur, and pass a current of sulphuretted hydrogen for some minutes. Allow to digest for an hour or so on a hot plate, filter, and wash the residue. Acidulate the filtrate with hydrochloric acid. The precipitate will contain the antimony, as Sb2S5, and possibly arsenic or tin. The precipitate is transferred to a beaker and boiled with hydrochloric acid. The solution is filtered off and diluted. Add a few crystals of tartaric acid and pass a current of sulphuretted hydrogen for some time. The first flocculent precipitate will become denser and render the filtering more easy. Transfer the precipitate after washing free from chlorides to a Berlin dish and treat cautiously with fuming nitric acid. The action of this acid on the sulphide is very violent. Evaporate and ignite. Transfer to a silver dish and fuse with 4 or 5 times its weight of caustic soda. Cool and extract with a little water. Then add an equal volume of alcohol and allow to stand overnight. Filter, wash with dilute alcohol. The filtrate will contain the tin. The residue contains the antimony as antimonate of soda and is dissolved off the filter with hot dilute hydrochloric, with the help of a little tartaric acid. The filtrate is now ready for the gravimetric determination. Gravimetric assay. Pass a current of sulphuretted hydrogen through the solution containing the antimony, to which a little tartaric acid has been previously added. Pass the gas till the precipitate becomes dense and the antimony is all down. The solution must not be too strongly acid. Filter off the precipitate, wash with hot water, dry in the water oven, transfer to a weighed porcelain dish, and cautiously treat with fuming nitric acid. Continue the action on the water bath till the sulphur and antimony are completely oxidized. Evaporate, ignite, gently at first, then strongly over the blast, cool and weigh. The residue is a white infusible powder and consists of antimony tetroxide, Sb2O4, containing 78.94% of the metal. Determination of antimony as bigallate. What appears to be a very good method has been worked out by M.A. Guyard and is described in Crookes' Select Methods, page 398. The antimony must be in solution as antimonious chloride and must not be accompanied by an excess of hydrochloric acid. To ensure these conditions, the solution is treated with potassium iodide until no more iodine is evolved, and is then evaporated to remove the excess of hydrochloric acid. To the concentrated and nearly neutral solution, a freshly prepared solution of gallic acid is added in slight excess. A bulky white precipitate is formed that settles rapidly. The solution is diluted with hot water and washed by decantation. Then the precipitate is collected on a weighed double filter, washed once or twice with hot water, and dried at 100 degrees centigrade. The dried substance is antimony bigallate and contains 40.85% of antimony. It should be completely soluble in ammonium sulphide. The solution in which the antimony is precipitated need not be quite free from other metals. Volumetric method. This is based on the reduction of antimonic chloride, SbCl5, to antimonious, SbCl3, by the action of potassium iodide in strong hydrochloric acid solution. Footnote: SbCl5 plus 2Ki yields I2 plus SbCl3 plus 2KCl. End footnote. Iodine is at the same time liberated, and the amount of antimony reduced is got at by titrating with sodium hyposulfite, which measures the iodine set free. The standard solution of sodium hyposulfite is made by dissolving 41.32 grams of the salt, Na2S2O3.5H2O, in water and diluting to 1 litre. 100 cc will be equivalent to about 1 gram of antimony. It is standardized with the help of a solution of antimony made as follows. Weigh up 5 grams of powdered antimony, transfer to a flask, and cover with 50 cc of hydrochloric acid. Boil and add nitric acid, 5 or 10 drops at a time, until the metal is dissolved. Allow the action of the nitric acid to cease before adding more. Boil down to a small bulk, add 250 cc of hydrochloric acid, and dilute to nearly 1 litre. Warm until any precipitate which has formed is redissolved. Allow to cool slowly, and run in from a pipette a weak solution of permanganate until a faint brown colour is produced. Dilute to exactly 1 litre. 100 cc contain 0.5 gram of antimony as antimonic chloride. In standardizing, take 50 cc of the antimony solution and transfer to a flask. Add 2 grams of potassium iodide crystals, and when dissolved, after standing a few minutes, run in the solution of hypo from an ordinary burette until the greater part of the iodine has been reduced. Add a few drops of starch solution and continue the addition of the hypo until the muddy green colour changes to a clear brownish yellow. The solution must be shaken after each addition of the hypo. In determining antimony in ore, weigh up 0.5 to 1 gram and dissolve in hydrochloric acid with, if necessary, the help of chlorate of potash. The antimony is separated as sulphide, redissolved in hydrochloric acid, and oxidized with the crystal of chlorate of potash. Chlorine is boiled off, and the solution diluted with an equal bulk of water. To the clear, cold solution, potassium iodide is added, and after a few minutes the liberated iodine is titrated with hypo, as already described. The method only yields satisfactory results when the standard and assay are carried out alike. End of section 24. Section 25 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 11. Iron, Nickel, Cobalt, Zinc, Cadmium. Iron. Iron rusts or oxidizes very readily, and consequently is rarely found in the metallic state in nature. Such native iron as is found being generally of meteoric origin, or embedded in basalt and other igneous rocks. It chiefly occurs as oxide, as in magnetite, hematite, and in the brown iron ores and ochres. Chalybite, which is carbonate of iron, is an ore of great importance. Iron is found combined with sulphur in pyroxene and pyrites, and together with arsenic in mispickel. It is a common constituent of most rocks, imparting to them a green, black, or brown colour, and is present either as an essential part or as an impurity in most substances. The chemistry of iron is somewhat complicated by the existence of 2 oxides, each of which gives rise to a well-marked series of compounds. Those derived from the lower oxide, known as ferrous salts, are generally pale and greenish. Ferric salts are derived from the higher oxide, and are generally red, brown, or yellow. The existence of these 2 well-marked families of salts renders the assay of iron comparatively easy, for the quantity of iron present in a solution can be readily measured by the amount of oxidizing or reducing agent required to convert it from the one state into the other, that is, from ferrous to ferric, or from ferric to ferrous, as the case may be. In the red and brown iron ores and ochres, ferric iron is present. In chalybite, the iron is in the ferrous state, and in magnetite it is present in both forms. Traces of iron in the ferrous state may be found even in the presence of much ferric iron by either of the following tests. 1. Ferricyanide of potassium gives a blue precipitate or green coloration, With ferric salts, a brown colour only is produced. 2. A solution of permanganate of potassium is decolorized by a ferrous salt, but not by a ferric one. Traces of ferric iron can be detected, even in the presence of much ferrous iron, by the following tests. 1. By the brown or yellow colour of the solution, especially when hot. 2. By giving a pink or red coloration with sulfocyanide of potassium. Substances containing oxide of iron yield the whole of the iron as metal when fused at a high temperature with charcoal and suitable fluxes. The metal, however, will contain varying proportions of carbon and other impurities, and its weight can only afford a rough knowledge of the proportion of the metal in the ore. There are 2 or 3 methods of dry assay for iron, but they are not only inexact, but more troublesome than the wet methods, and need not be further considered. Chalybite and the hydrated oxides dissolve very readily in hydrochloric acid. Hematite and magnetite dissolve with rather more difficulty. Iron itself, when soft, is easily soluble in dilute hydrochloric or sulfuric acid. Pyrites, mispickel, etc. are insoluble in hydrochloric acid, but they are readily attacked by nitric acid. Certain minerals, such as chrome iron ore, titaniferous iron ore, and some silicates containing iron, remain in the residue insoluble in acids. Some of these yield their iron when attacked with strong sulfuric acid, or when fused with the acid sulfate of potash. Generally, however, it is better in such stubborn cases to fuse with carbonate of soda, and then attack the melt with hydrochloric acid. When nitric acid or the fusion method has been used, the metal will be in solution in the ferric state, no matter in what condition it existed in the ore. But with dilute hydrochloric or sulfuric acid it will retain its former degree of oxidation. Hydrochloric acid, for example, with chalybite, ferrous carbonate, will give a solution of ferrous chloride. With hematite, ferric oxide, it will yield ferric chloride, and with magnetite, ferrous and ferric oxides, a mixture of ferrous and ferric chlorides. Metallic iron yields solutions of ferrous salts. It is convenient to speak of the iron in a ferrous salt as ferrous iron, and when in the ferric state as ferric iron. Frequently it is required to determine how much of the iron exists in an ore in each condition. In such cases it is necessary to keep off the air while dissolving. The operation should therefore be performed in an atmosphere of carbonic acid. Separation. The separation of the iron from the other substances is as follows. Silica is removed by evaporating the acid solution and taking up with acid, as described under silica. The whole of the iron will be in solution. The metals of groups 1 and 2 are removed by passing sulphuretted hydrogen, and at the same time the iron will be reduced to the ferrous state. The solution should be filtered into a 16-ounce flask, boiled to get rid of the gas, and treated, whilst boiling, with a few drops of nitric acid, in order to convert the whole of the iron into the ferric state. When this condition is arrived at, an additional drop of nitric acid causes no dark coloration. The boiling must be continued to remove nitrous fumes. Next, add caustic soda solution until the colour of the solution changes from yellow to red. The solution must be free from a precipitate. If the soda be incautiously added, a permanent precipitate will be formed, in which case it must be redissolved with hydrochloric acid, and soda again, but more cautiously, added. After cooling, a solution of sodium acetate is added until the colour of the solution is no longer darkened. The solution, diluted to 2/3 of the flaskful with water, is heated to boiling. Long continued boiling must be avoided. The precipitate is filtered quickly through a large filter and washed with hot water containing a little acetate of soda. The precipitate will contain all the iron and may also contain alumina, chromium, titanium, as well as phosphoric acid and perhaps arsenic acids. Footnote: When chromium is present, some of the iron may escape precipitation, but it can be recovered from the solution by means of ammonic sulfide. End footnote. Dissolve the precipitate off the filter with dilute sulfuric acid, avoiding excess. Add tartaric acid and then ammonia in excess. Pass sulphuretted hydrogen, warm, and allow the precipitate to settle. Filter and wash with water containing a little ammonic sulfide. Gravimetric method. Dissolve the precipitate in dilute hydrochloric acid. Peroxidize with a few drops of nitric acid and boil. Dilute to about 200 cc. Add ammonia with constant stirring till the liquid smells of it, and heat to boiling. Wash as much as possible by decantation with hot water. Transfer to the filter and wash till the filtrate gives no indication of soluble salts coming through. The filtrate must be colourless and clear. The wet precipitate is very bulky, of a dark brown colour and readily soluble in dilute acids, but insoluble in ammonia and dilute alkalis. When thrown down from a solution containing other metals, it is very apt to carry portions of these with it, even when they are by themselves very soluble in ammoniacal solutions. It must be dried and ignited, the filter paper being burnt separately and its ash added. When further ignition ceases to cause a loss of weight, the residue is ferric oxide, Fe2O3, which contains 70% of iron. The weight of iron therefore can be calculated by multiplying the weight of oxide obtained by 0.7. The presence of ammonic chloride causes loss of iron during the ignition, and organic matter causes an apparent loss by reducing the iron to a lower state of oxidation. When the iron in the solution much exceeds 0.2 gram, the volumetric determination is generally adopted, as the bulkiness of the precipitate of ferric hydrate makes the gravimetric method very inconvenient. Volumetric methods. As already explained, these are based on the measurement of the volume of a reagent required to bring the whole of the iron from the ferrous to the ferric state, oxidation, or from the ferric to the ferrous, reduction. Ferrous compounds are converted into ferric by the action of an oxidizing agent in the presence of an acid. Either permanganate or bichromate of potash is generally used for this purpose. Footnote 1. 10 FeSO4 plus 2 KMnO4 plus 8 H2SO4 yields 5 Fe2 bracket SO4 close bracket 3 times plus 2 MnSO4 plus K2SO4 plus 8 H2O. 2. 6 FeCl2 plus K2Cr2O7 plus 14 HCl yields 3 Fe2Cl6 plus Cr2Cl6 plus 2 KCl plus 7 H2O. End footnote. Ferric compounds are reduced to ferrous by the action of 1. Stannous chloride, 2. Sulphuretted hydrogen, 3. Sodium sulfite, or 4. Zinc. Footnote. Fe2Cl6 plus SnCl2 yields 2 FeCl2 plus SnCl4. 2 Fe2Cl6 plus SH2 yields 2 FeCl2 plus 2 HCl plus S. 3 Fe2Cl6 plus Na2SO3 plus H2O yields 2 FeCl2 plus Na2SO4 plus 2 HCl. 4 Fe2Cl6 plus Zn yields 2 FeCl2 plus ZnCl2. End footnote. The processes then may be divided into two kinds, one based on oxidation and the other on reduction. In each case, the titration must be preceded by an exact preparation of the solution to be assayed, in order that the iron may be in the right state of oxidation. Permanganate and bichromate methods. These consist of 3 operations. 1. Solution of the ore. 2. Reduction of the iron to the ferrous state. And 3. Titration. Solution. The only points to be noticed concerning the first operation, in addition to those already mentioned, is that nitric acid must be absent. If nitric acid has been used, evaporate to dryness, of course without previous dilution. Add hydrochloric or sulfuric acid and boil for 5 or 10 minutes. Dilute with water to about 100 cc and warm until solution is complete. The reduction is performed by either of the following methods. 1. With stannous chloride. Fill a burette with a solution of stannous chloride. Footnote: 20 grams of stannous chloride and 20 cc of dilute hydrochloric acid are diluted to 1 litre. End footnote. And cautiously run the liquid into the hot assay solution, in which the iron is present as chloride, until the colour is discharged. A large excess of the stannous chloride must be avoided. Then add 5 cc of a 2.5% solution of mercuric chloride. This will cause a white precipitate, or a grey one if too large an excess of the stannous chloride has been added. Boil till the solution clears, cool, dilute, and titrate. 2. With sulphuretted hydrogen. Cool the solution and pass through it a current of washed sulphuretted hydrogen till the liquid smells strongly of the gas after withdrawal and shaking. A white precipitate of sulphur will be formed. This will not interfere with the subsequent titration, provided it is precipitated in the cold. If, however, the precipitate is coloured, showing the presence of the second group metals, or if the precipitation has been carried out in a hot solution, it should be filtered off. Boil the solution until the sulphuretted hydrogen is driven off. This may be tested by holding a strip of filter paper dipped in lead acetate solution in the steam issuing from the flask. The presence of sulphuretted hydrogen should be looked for, rather than its absence. It is well to continue the boiling for a few minutes after the gas has been driven off. Cool and titrate. 3. With sodium sulphite. Add ammonia, a few drops at a time, until the precipitate first formed redissolves with difficulty. If a permanent precipitate is formed, redissolve with a few drops of acid. To the warm solution add from 2 to 3 grams of sodium sulphite crystals. The solution will become strongly coloured, but the colour will fade away on standing for a few minutes in a warm place. When the colour is quite removed, add 20 cc of dilute sulphuric acid and boil until the steam is quite free from the odour of sulphurous acid. Cool and titrate. 4. With zinc. Add about 10 grams of granulated zinc. If the hydrogen comes off violently, add water. If, on the other hand, the action is very slow, add sufficient dilute sulphuric acid to keep up a brisk effervescence. The reduction is hastened by warming, and is complete when the solution is quite colourless and a drop of the liquid tested with sulfocyanate of potassium gives no reaction for ferric iron. Filter through glass wool or quick filtering paper. The zinc should be still giving off gas rapidly, indicating a freely acid solution. If not, acid must be added. Wash with water rendered acid. Cool and titrate. With regard to the relative advantages of the different methods, they may be roughly summed up as follows. The stannous chloride method has the advantage of immediately reducing the ferric iron, whether in hot or cold solution, and under varied conditions in regard to acidity, but has the disadvantage of similarly reducing salts of copper and antimony, which in a subsequent titration count as iron. Moreover, there is no convenient method of eliminating any large excess of the reagents that may have been used, and consequently it either leaves too much to the judgment of the operator, or entails as much care as a titration. Students generally get good results by this method. The sulphuretted hydrogen method also has the advantage of quick reduction under varying conditions, and the further one of adding nothing objectionable to the solution. In fact, it removes certain impurities. The disadvantages are the necessity for boiling off the excess of the gas, and of filtering off the precipitated sulphur, although this last is not necessary if precipitated cold. The tendency with students is to get high results. The sodium sulphite method has the advantages of being clean and neat, and of requiring no nitration. On the other hand, it requires practice in obtaining the best conditions for complete reduction, and, as with sulphuretted hydrogen, there is the necessity for boiling off the gas, while there is no simple and delicate test for the residual sulphurous acid. In addition, if an excess of sodium sulphite has been used and enough acid not subsequently added, the excess will count as iron. Students generally get low results by this method. The advantages of the zinc method are that it is easily worked and that the excess of zinc is readily removed by simply filtering. The disadvantages are the slowness with which the last portions of ferric iron are reduced. Footnote: the maximum reducing effect of zinc is obtained by exposing as large a surface as possible of the metal in a hot concentrated solution containing but little free acid. Note Thorpe. End note. End footnote. The danger of loss by effervescence, the precipitation of basic salts and perhaps of iron, and the loading of the solution with salts of zinc, which, in the titration with bichromate, have a prejudicial effect. The tendency in the hands of students is to get variable results, sometimes low and sometimes high. Generally speaking, the sulphuretted hydrogen and sodium sulphite methods are to be preferred. Carefully worked, each method will yield good results. The titration may be done with a standard solution of 1 permanganate of potash or 2 bichromate of potash. 1. With permanganate of potash. Prepare a standard solution by dissolving 2.82 grams of the salt and diluting to 1 litre. The strength of this should be 100 cc's, equaling 0.5 gram of iron, but it varies slightly and should be determined and afterwards checked every 2 or 3 weeks by weighing up 0.2 gram of iron wire, dissolving in 10 cc's of dilute sulphuric acid and diluting to about 100 cc's and titrating. The standard solution must be put in a burette with a glass stopcock, as it attacks india rubber. The assay should be contained in a pint flask and be cooled before titrating. The standard solution must be run in until a pinkish tinge permeates the whole solution. This must be taken as the finishing point. When certain interfering bodies are present, this colour quickly fades, but the fading must be ignored. With pure solutions, the colour is fairly permanent, and a single drop of the potassium permanganate solution is sufficient to determine the finishing point. 2. With bichromate of potash. Prepare a standard solution by dissolving 4.39 grams of the powdered and dried salt in water and diluting to 1 litre. This solution is permanent. Its strength is determined by dissolving 0.2 gram of iron wire in 10 cc's of dilute sulphuric acid, diluting to about 1/4 litre and titrating. Also, prepare a test solution by dissolving 0.1 gram of ferricyanide of potassium in 100 cc's of water. This solution does not keep well and must be freshly prepared. An ordinary burette is used. The assay is best contained in a glazed earthenware dish and may be titrated hot or cold. To determine the finishing point, place a series of drops of the ferricyanide solution on a dry, white glazed plate. The drops should be of about the same size and be placed in lines at fairly equal distances. The bichromate is run in a steady stream, the assay solution being continuously stirred until the reaction is sensibly slackened. Then bring a drop of the assay with the stirrer in contact with one of the test drops on the plate. The standard solution can be safely run in 1 cc at a time, so long as the test drop shows signs of a precipitate. When only a coloration is produced, run in cautiously a few drops at a time, so long as 2 drops of the assay gives with the test a colour which is even faintly greener than 2 drops of the assay solution placed alongside. The finishing point is decided and practically permanent, although it demands a little practice to recognise it. The titration with permanganate of potassium has the advantage of a more distinct finishing point and easier mode of working. Its application, however, is somewhat limited by the disturbing effects of hydrochloric acid. The bichromate method has the advantage of a standard solution which does not alter in strength, and the further one of being but little affected by altering conditions of assay. Hydrochloric acid has practically no effect on it. Both methods give accurate results and are good examples of volumetric methods. The following results illustrate the extent to which the methods may be relied on, and the influence which the various conditions of experiment have on the assay. Solutions of ferrous sulphate and of ferrous chloride were made, containing 0.5 gram of iron in each 100 c.c., corresponding to the standard solutions of permanganate and bichromate of potassium. These last were prepared in the way already described. The solution of ferrous sulphate was made by dissolving 5.01 grams of iron wire in 100 c.c. of dilute sulphuric acid and diluting to 1 litre. A similar solution may be made by dissolving 24.82 grams of pure ferrous sulphate crystals in water, adding 100 c.c. of dilute sulphuric acid and diluting to 1 litre. Rate of oxidation by exposure to air. This is an important consideration, and if the rate were at all rapid, would have a serious influence on the manner of working, since exclusion of air in the various operations would be troublesome. 20 c.c. of the solution of ferrous sulphate were taken in each experiment, acidified with 10 c.c. of dilute sulphuric acid, and diluted to 100 c.c. The solution was exposed cold in an open beaker for varying lengths of time, and titrated with permanganate of potassium. Time exposed 1 hour, c.c. required 19.2. Time exposed 1 day, c.c. required 19.1. Time exposed 2 days, c.c. required 19.0. Time exposed 3 days, c.c. required 19.0. These results show that the atmospheric oxidation in cold solution is unimportant. With boiling solutions the results are somewhat different. A solution which at the outset required 20 c.c. of permanganate of potassium, after boiling for an hour in an open beaker without any precautions to prevent oxidation, water being added from time to time to replace that lost by evaporation, required 19.2 c.c. If the solution be evaporated to dryness, the oxidizing power of concentrated sulphuric acid comes into play, so that very little ferrous iron will be left. A solution evaporated in this way required only 2.2 c.c. of permanganate of potassium. Effect of varying temperature. In these experiments the bulk was in each case 100 c.c. and 10 c.c. of dilute sulphuric acid were present. The permanganate required by 1 c.c. of ferrous sulphate was at 15 degrees 1.0 c.c. and at 70 degrees 1.1 c.c. 10 c.c. of ferrous sulphate was at 15 degrees centigrade 9.7 c.c. and at 70 degrees 9.8 c.c. 100 c.c. of ferrous sulphate was at 15 degrees 97.7 c.c. and at 70 degrees 96.8 c.c. The lower result with the 100 c.c. may be due to oxidation from exposure. Effect of varying bulk. The following experiments show that considerable variations in bulk have no practical effect. In each case 20 c.c. of ferrous sulphate solution and 10 c.c. of dilute acid were used. Bulk of assay 30.0 c.c. Permanganate required 20.0 c.c. Bulk of assay 100 c.c. Permanganate required 20.0 c.c. Bulk of assay 500 c.c. Permanganate required 20.2 c.c. Bulk of assay 1000 c.c. Permanganate required 20.5 c.c. Effect of free sulphuric acid. Free acid is necessary for these assays. If there is an insufficiency, the assay solution, instead of immediately decolorizing the permanganate, assumes a brown colour. The addition of 10 c.c. of dilute sulphuric acid suffices to meet requirements and keep the assay clear throughout. The following experiments show that a considerable excess of acid may be used without in the least affecting the results. In each case 20 c.c. of ferrous sulphate were used. Reader's note: 19.3 c.c. of permanganate were required. For all volumes of dilute sulphuric acid tested, 1.0 c.c., 5.0 c.c., 10.0 c.c., 20.0 c.c., 50.0 c.c. and 100.0 c.c. End reader's note. Effect of foreign salts. When the assay has been reduced with zinc, varying quantities of salts of this metal pass into solution, the amount depending on the quantity of acid and iron present. Salts of sodium or ammonium may similarly be introduced. It is essential to know by experiment that these salts do not exert any effect on the titration. The following series of experiments show that as much as 50 grams of zinc sulfate may be present without interfering. Zinc sulfate present 0 grams, permanganate required 19.3 cc's. Zinc sulfate present 1 gram, permanganate required 19.3 cc's. Zinc sulfate present 10 grams, permanganate required 19.3 cc's. Zinc sulfate present 50 grams, permanganate required 19.3 cc's. Magnesium, sodium and ammonium salts are equally without effect. Ammonic sulfate present 0 grams, permanganate required 19.3 cc's. Ammonic sulfate present 1 gram, permanganate required 19.2 cc's. Ammonic sulfate present 10 grams, permanganate required 19.3 cc's. Sodic sulfate present 0 grams, permanganate required 19.3 cc's. Sodic sulfate present 1 gram, permanganate required 19.3 cc's. Sodic sulfate present 10 grams, permanganate required 19.3 cc's. Magnesic sulfate present 0 grams, permanganate required 19.3 cc's. Magnesic sulfate present 1 gram, permanganate required 19.3 cc's. Magnesic sulfate present 10 grams, permanganate required 19.3 cc's. Effect of varying amounts of iron. It is important to know within what limits the quantity of iron in an assay may safely vary from that used in standardizing. In the following experiments, the conditions as to bulk, acidity and mode of working were the same as before. Ferrous sulfate solution taken 1 cc, permanganate required 1.0 cc's. Ferrous sulfate taken 10 cc's, permanganate required 9.7 cc's. Ferrous sulfate solution taken 20 cc's, permanganate required 19.6 cc's. Ferrous sulfate solution taken 50 cc's, permanganate required 48.9 cc's. Ferrous sulfate solution taken 100 cc's, permanganate required 97.7 cc's. The ferrous sulfate solution is here a little weaker than that of the permanganate of potassium, but the results show that the permanganate required is proportional to the iron present. Titrations in hydrochloric solutions. These are less satisfactory than those in sulfuric solutions, since an excess of hydrochloric acid decomposes permanganate of potassium, evolving chlorine, and since the finishing point is indicated not by the persistence of the pink colour of the permanganate, but by a brown coloration, probably due to perchloride of manganese. Nevertheless, if the solution contains only from 5 to 10% of free hydrochloric acid, note specific gravity 1.16, end note, the results are the same as those obtained in a sulfuric acid solution. Equal weights, 0.1 gram, of the same iron wire required exactly the same quantity of the permanganate of potassium solution, 20 cc's, whether the iron was dissolved in dilute sulfuric or dilute hydrochloric acid. The following series of experiments are on the same plan as those given above with sulfuric acid solutions. A solution of ferrous chloride was made by dissolving 5.01 grams of iron wire in 50 cc's of dilute hydrochloric acid and diluting to 1 litre. The dilute hydrochloric acid was made by mixing equal volumes of the acid, note specific gravity 1.16, end note, and water. Rate of atmospheric oxidation. 20 cc's of the ferrous chloride solution were acidified with 10 cc's of the dilute hydrochloric acid and diluted to 100 cc's. The solution was exposed cold in open beakers. Time exposed, none. Permanganate required 19.6 cc's. Time exposed 1 hour. Permanganate required 19.6 cc's. Time exposed 1 day. Permanganate required 19.5 cc's. Time exposed 2 days. Permanganate required 19.4 cc's. time exposed 3 days, permanganate required 19.5 cc's. Similar solutions boiled required before boiling 20 cc's, after boiling for 1 hour, replacing the water as it evaporated, 19.3 cc's, and after evaporation to a paste and redissolving, 17.0 cc's. Effect of varying temperature. Solutions similar to the last were titrated and gave the following results. Temperature 15 degrees, permanganate required 19.8 cc's. Temperature 30 degrees, permanganate required 19.6 cc's. Temperature 50 degrees, permanganate required 19.5 cc's. Temperature 70 degrees, permanganate required 19.4 cc's. Effect of varying bulk. As before, 20 cc's of the iron solution and 10 cc's of the dilute acid were diluted to the required volumes and titrated. Bulk 30 cc's, permanganate required 20.4 cc's. Bulk 100 cc's, permanganate required 20.3 cc's. Bulk 500 cc's, permanganate required 20.8 cc's. Bulk 1000 cc's, permanganate required 21.5 cc's. The variation due to difference in bulk here, although only equal to an excess of 0.7 mg of iron for each 100 cc's of dilution, are about 3 times as great as those observed in a sulfuric acid solution. The end of section 25. Section 26 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 11. Iron, Nickel, Cobalt, Zinc, Cadmium. Part 2. Iron continued. Effect of free hydrochloric acid. In these experiments, 20 cc's of the ferrous chloride solution were used, with varying quantities of acid, the bulk of the assay in each case being 100 cc's. Dilute acid present 5 cc's, permanganate required 20.2 cc's. Dilute acid present 10 cc's, permanganate required 20.2 cc's. Dilute acid present 50 cc's, permanganate required 20.5 cc's. Dilute acid present 100 cc's, permanganate required 21.0 cc's. The last had a very indistinct finishing point, the brown coloration being very evanescent. The effect of the acid is modified by the presence of alkaline and other sulfates, but not by sulfuric acid. Repeating the last experiment, we got, without further addition, 21.0 cc's, with 100 cc's of dilute sulfuric acid, 22.0 cc's, with 10 grams ammonic sulfate, 20.5 cc's, with 10 grams sodic sulfate, 20.0 cc's, with 10 grams magnesium sulfate, 20.4 cc's, with 10 grams manganese sulfate, 20.2 cc's. The results with these salts in counteracting the interference of the acid, however, were not a complete success, since the end reactions were all indistinct, with the exception perhaps of that with the manganese sulfate. Effect of varying amounts of iron. In these experiments the bulk of the assay was 100 cc's, and 10 cc's of acid were present. Ferrous chloride used 1 cc, permanganate required 1.1 cc's. Ferrous chloride used 10 cc's, permanganate required 10.3 cc's. Ferrous chloride used 20 cc's, permanganate required 20.3 cc's. Ferrous chloride used 50 cc's, permanganate required 50.4 cc's. Ferrous chloride used 100 cc's, permanganate required 100.1 cc's. In making himself familiar with the permanganate of potassium titration, the student should practice by working out a series of experiments similar to the above, varying his conditions one at a time, so as to be certain of the cause of any variation in his results. He may then proceed to experiment on the various methods of reduction. A solution of ferric chloride is made by dissolving 5.01 grams of iron wire in 50 c.c. of hydrochloric acid. Note specific gravity 1.16. End note. And running from a burette nitric acid diluted with an equal volume of water into the boiling iron solution until the liquid changes from a black to a reddish yellow. About 4.5 c.c. of the nitric acid will be required, and the finishing point is marked by a brisk effervescence. The solution of iron should be contained in an evaporating dish and boiled briskly with constant stirring. There should be no excess of nitric acid. Boil down to about half its bulk, then cool and dilute to 1 litre with water. 20 c.c. of this solution diluted to 100 c.c. with water and acidified with 10 c.c. of dilute hydrochloric acid should not decolorize any of the permanganate of potassium solution. This shows the absence of ferrous salts. And 20 c.c. of the same solution, boiled with 20 c.c. of the ferrous sulfate solution, should not decrease the quantity of permanganate required for the titration of the ferrous sulfate added. In a series of experiments on the various methods of reduction, the following results were got. The modes of working were those already described. 1. With stannous chloride. 20 c.c. of the ferric chloride solution required after reduction with stannous chloride 20 c.c. of permanganate. 50 c.c. of a solution of ferrous chloride, which required on titration 49.8 c.c. of permanganate, required for retitration after subsequent reduction with stannous chloride 50 c.c. of the permanganate solution. With sulphuretted hydrogen. 2 experiments with this gas, using in each 20 c.c. of the ferric chloride solution and 10 c.c. of hydrochloric acid, required after reduction 20.2 c.c. and 20.1 c.c. of permanganate. Repeating the experiments by passing the gas through a nearly boiling solution, but in other respects working in the same way, 21.3 c.c. and 21.6 c.c. of the permanganate were required. The sulphur was not filtered off in any of these. In another experiment in which 50 c.c. of the ferrous sulfate solution were titrated with permanganate, 48 c.c. of the latter were required. The titrated solution was next reduced with sulphuretted hydrogen, brought to the same bulk as before, and again titrated. 47.9 c.c. of the permanganate of potassium solution were required. 3. With sodium sulfite. 20 c.c. of the ferric chloride solution reduced with sodium sulfite required 19.9 c.c. of permanganate. In one experiment, 50 c.c. of the ferrous sulfate solution were titrated with permanganate. 49.3 c.c. of the last mentioned solution were required. The titrated solution was reduced with sodium sulfite and again titrated. It required 49.2 c.c. of the permanganate of potassium solution. 4. With zinc. 20 c.c. of the ferric chloride solution, reduced with zinc and titrated, required 20.8 c.c. of permanganate. 50 c.c. of a solution of ferrous sulfate, which required 49.7 c.c. of permanganate, required for retitration after reduction with zinc 49.7 c.c. The student should next practice the titration with bichromate, which is more especially valuable in the estimation of hydrochloric acid solutions. The following experiments are on the same plan as those already given. In each experiment, except when otherwise stated, there were present 20 c.c. of the ferrous chloride solution and 10 c.c. of dilute hydrochloric acid, and the bulk was 300 c.c. Effect of varying temperature. The quantities of the bichromate of potassium solution required were as follows. Temperature 15 degrees, bichromate required 20.2 c.c. Temperature 30 degrees, bichromate required 20.3 c.c. Temperature 70 degrees, bichromate required 20.3 c.c. Temperature 100 degrees, bichromate required 20.4 c.c. Effect of varying bulk. Bulk 50 c.c., bichromate required 20.4 c.c. Bulk 100 c.c., bichromate required 20.4 c.c. Bulk 200 c.c., bichromate required 20.4 c.c. Bulk 500 cc's, bichromate required 20.5 cc's. Bulk 1000 cc's, bichromate required 20.8 cc's. Effect of varying acid. In these, variable quantities of dilute hydrochloric acid were used. Acid present 10 cc's, bichromate required 20.3 cc's. Acid present 50 cc's, bichromate required 20.3 cc's. Acid present 100 cc's, bichromate required 20.2 cc's. Effect of foreign salts. The effect of the addition of 10 grams of crystallized zinc sulfate was to decrease the quantity of bichromate required from 20.3 cc's to 20.1 cc's, but the colour produced with the test drop was very slight at 18.5 cc's, and with incautious work the finishing point might have been taken anywhere between these extremes. Zinc should not be used as a reducing agent preliminary to a bichromate titration. 10 grams of ammonic sulfate had the effect of rendering the finishing point faint for about 0.5 cc's before the titration was finished, but there was no doubt about the finishing point when allowed to stand for a minute. The student should note that a titration is not completed if a colour is developed on standing for 5 or 10 minutes. 10 grams of sodic sulfate had no effect. 20.3 cc's were required. Effect of varying iron. The results are proportional, as will be seen from the following details. Ferrous chloride present 1.0 cc's, bichromate required 1.0 cc's. Ferrous chloride present 10.0 cc's, bichromate required 10.2 cc's. Ferrous chloride present 20.0 cc's, bichromate required 20.3 cc's. Ferrous chloride present 50.0 cc's, bichromate required 51.0 cc's. Ferrous chloride present 100.0 cc's, bichromate required 102.3 cc's. The students may now apply these titrations to actual assays of minerals. The following examples will illustrate the mode of working and of calculating the results. Determination of iron in chalybite. Weigh up 1 gram of the dry powdered ore and dissolve in 10 cc's of dilute sulfuric acid and an equal volume of water with the aid of heat. Avoid evaporating to dryness. Dilute and titrate. The result will give the percentage of iron existing in the ore in the ferrous state. Some ferric iron may be present. If it is wished to determine this also, add, in dissolving another portion, 10 cc's of dilute hydrochloric acid to the sulfuric acid already ordered, and reduce the resulting solution before titrating. By dissolving and titrating without previous reduction, one has a measure of the ferrous iron present. By dissolving, reducing, and then titrating, one can measure the total iron, and as the iron exists in only two conditions, the total iron, less the ferrous iron, is the measure of the ferric iron. Determination of iron in brown or red ores or magnetite. Weigh up 0.5 gram of the ore, powdered and dried at 100 degrees centigrade, and dissolve in from 10 to 20 cc's of strong hydrochloric acid, boiling until all is dissolved or until no coloured particles are left. Dilute, reduce, and titrate. Determination of iron in pyrites. Weigh up 1 gram of the dry powdered ore and place in a beaker. Cover with 10 cc's of strong sulfuric acid, mix well by shaking, and place on the hot plate without further handling for an hour or so until the action has ceased. Allow to cool, and dilute to 100 cc's. Warm until solution is complete. Reduce and titrate. Determination of iron in substances insoluble in acids. Weigh up 1 gram of the ore, mix with 5 or 6 grams of carbonate of soda and 0.5 gram of nitre by rubbing in a small mortar, and transfer to a platinum crucible. Clean out the mortar by rubbing up another gram or so of soda, and add this to the contents of the crucible as a cover. Fuse till tranquil. Cool. Extract with water. If the ore carries much silica, evaporate to dryness with hydrochloric acid to separate it. redissolve in hydrochloric acid and separate the iron by precipitating with ammonia and filtering. If only a small quantity of silica is present, the aqueous extract of the melt must be filtered, and the insoluble residue washed and dissolved in dilute hydrochloric acid. Reduce and titrate. A convenient method of at once separating iron from a solution and reducing it is to add ammonia, pass sulphuretted hydrogen through it, filter, and dissolve the precipitate in dilute sulphuric acid. The solution, when boiled free from sulphuretted hydrogen, is ready for titrating. Stannous chloride process. The colour imparted to hot hydrochloric acid solutions by a trace of ferric compound is so strong, and the reducing action of stannous chloride is so rapid, that a method of titration is based upon the quantity of a standard solution of stannous chloride required to completely decolorise a solution containing ferric iron. This method is more especially adapted for the assay of liquors containing much ferric iron, and of those oxidised ores which are completely soluble in hydrochloric acid. It must be remembered, however, that it only measures the ferric iron present, and when, as is generally the case, the total iron is wanted, it is well to calcine the weighed portion of ore previous to solution, in order to get the whole of the iron into the higher state of oxidation, since many ores which are generally supposed to contain only ferric iron carry a considerable percentage of ferrous. The stannous chloride solution is made by dissolving 20 grams of the commercial salt, SnCl2.2H2O, in 100 cc of water with the help of 20 cc of dilute hydrochloric acid, and diluting to a litre. The solution may be slightly opalescent, but should show no signs of a precipitate. The strength of this is about equivalent to 1 gram of iron for each 100 cc of the solution, but it is apt to lessen on standing, taking up oxygen from the air, forming stannic chloride. A larger proportion of hydrochloric acid than is ordered above would remove the opalescence, but at the same time increase this tendency to atmospheric oxidation, as the following experiments show. The stannous chloride solution, 20 cc, was mixed with varying amounts of strong hydrochloric acid. Note: specific gravity 1.16, end note, diluted to 100 cc, and exposed in open beakers for varying lengths of time, and the residual stannous chloride measured by titration with permanganate. The quantities required were as follows: 50% acid, time exposed 1 hour, 33.2 cc, time exposed 1 day, 5.0 cc, time exposed 2 days, 3.0 cc, 10% acid, time exposed 1 hour, 34.4 cc, time exposed 1 day, 24.0 cc, time exposed 2 days, 14.5 cc, 1% acid, time exposed 1 hour, 34.5 cc, time exposed 1 day, 27.6 cc, time exposed 2 days, 21.3 cc. These indicate very clearly the increased susceptibility to oxidation in strongly acid solutions. A standard solution of ferric chloride is prepared in the same manner as that described under the experiments on the methods of reduction, but it should be of twice the strength, so that 100 cc may contain 1 gram of iron. This solution is used for standardizing the stannous chloride when required, and must be carefully prepared and tested for the presence of nitric acid. The titration is more limited in its application than either of the oxidizing processes because of the restrictions as to bulk, quality, and quantity of free acid present, and other conditions of the solution to be assayed. The following experiments show the conditions necessary for a successful titration. Effect of varying temperature. 20 cc of ferric chloride solution with 20 cc of strong hydrochloric acid, diluted to 50 cc, gave the following results when titrated. Temperature 15 degrees, stannous chloride required 22.8 cc. Temperature 30 degrees, stannous chloride required 22.0 cc. temperature 70 degrees, stannous chloride required 22.1 cc's. Temperature 100 degrees, stannous chloride required 22.0 cc's. The finishing point, however, is more distinct the hotter the solution, so that it is best in all cases to run the standard into the boiling solution. Effect of varying bulk. Solutions containing the same quantity of iron and acid as the last, but diluted to various bulks and titrated while boiling, gave the following results. Bulk 30 cc's, stannous chloride required 21.5 cc's. Bulk 100 cc's, stannous chloride required 21.7 cc's. Bulk 500 cc's, stannous chloride required 24.3 cc's. Effect of varying quantities of hydrochloric acid. In these experiments, the bulk before titration was 50 cc's, except in the last, in which it was 70 cc's. With less than 5 cc's of strong hydrochloric acid, the finishing point is indistinct and prolonged. Strong hydrochloric acid present 5 cc's. Stannous chloride required 21.1 cc's. Strong hydrochloric acid present 10 cc's. Stannous chloride required 21.1 cc's. Strong hydrochloric acid present 20 cc's. Stannous chloride required 21.2 cc's. Strong hydrochloric acid present 30 cc's. Stannous chloride required 21.8 cc's. Strong hydrochloric acid present 50 cc's. Stannous chloride required 22.2 cc's. Effect of free sulfuric acid. In these experiments, 20 cc's of hydrochloric acid were present, and the bulk was 50 cc's. Strong sulfuric acid present, none. Stannous chloride required, 21.6 cc's. Strong sulfuric acid present, 3 cc's. Stannous chloride required, 22.3 cc's. Strong sulfuric acid present, 5 cc's. Stannous chloride required, 22.9 cc's. Strong sulfuric acid present, 10 cc's. Stannous chloride required, 23.1 cc's. This interference of strong sulfuric acid may be completely counteracted by somewhat modifying the mode of working. Another experiment, like the last of this series, required 21.6 cc's. Effect of foreign salts. Experiments in which 10 grams of various salts were added showed them to be without effect. The results were as follows. Stannous chloride required 21.6 cc's when no salt was present, AmCl or Am2SO4, MgCl2, FeCl2 or Al2Cl6. Salt present CaCl2, stannous chloride required 21.8 cc's. Effect of varying iron. Titrating a solution with 20 cc's of hydrochloric acid, measuring 50 cc's and kept boiling, the quantity of stannous chloride solution required is practically proportional to the iron present. Ferric chloride added 1 cc, stannous chloride required 1.1 cc's. Ferric chloride added 10 cc's, stannous chloride required 10.5 cc's. Ferric chloride added 20 cc's, stannous chloride required 20.6 cc's. Ferric chloride added 50 cc's, stannous chloride required 51.4 cc's. Ferric chloride added 100 cc's, stannous chloride required 102.6 cc's. The student, having practiced some of the above experiments, may proceed to the assay of an iron ore. Determination of iron in brown iron ore. Weigh up 1 gram of the dried and powdered ore, calcine in the cover of a platinum crucible, and dissolve up in an evaporating dish, note about 5 inches in diameter, end note, with 20 cc's of strong hydrochloric acid. When solution is complete, dilute to 50 cc's after replacing any acid that may have been evaporated. Boil and run in the stannous chloride solution until the colour is faintly yellow. Boil again and continue the addition of the stannous chloride solution, stirring continuously, until the solution appears colourless. Note the quantity of the stannous chloride solution required. Suppose this to be 59 cc's. Take 60 cc of the standard ferric chloride solution, add 20 cc of hydrochloric acid, boil, and titrate in the same way as before. Suppose this to require 61 cc. Then, as 61 is equivalent to 60 of the iron solution, 59 is equivalent to 58.13. Footnote: 61 to 60 is equivalent to 59 to 58.13. The iron in the ore is then the same in amount as that in 58.13 cc of the ferric chloride solution, and since 100 cc of the latter contain 1 gram of iron, 58.13 cc of the same contains 0.5813 gram of iron. And further, if 1 gram of ore carries this amount of iron, 100 grams of ore will obviously give 58.13 grams of iron. End footnote. This gives the percentage. It is not necessary to standardise the stannous chloride solution in this way with each sample assayed. The ratio 61 to 60 would serve for a whole batch of samples, but the standardising should be repeated at least once each day. Colorimetric method. This method is valuable for the determination of small quantities of iron present as impurities in other metals or ores. It is based on the red coloration developed by the action of potassic sulfocyanate on acid solutions of ferric salts. Standard ferric chloride solution. Take 1 cc of the ferric chloride solution used for standardising the stannous chloride solution. Add 2 cc of dilute hydrochloric acid and dilute to 1 litre with water. 1 cc equals 0.01 milligram. Solution of potassic sulfocyanate. Dissolve 60 grams of the salt in water and dilute to a litre. It should be colourless. Use 10 cc for each test. The quantity of the substance to be weighed for the assay should not contain more than 1 milligram of iron. Consequently, if the ore contains more than 0.1% of that metal, less than 1 gram of it must be taken. The method is as follows. Weigh up 1 gram of the substance and dissolve in a suitable acid. Dilute and add permanganate of potash solution until tinted. Boil for some time and dilute to 100 cc. Take a couple of Nestler tubes holding over 100 cc but marked at 50 cc. Label them 1 and 2, and into each put 10 cc of the potassic sulfocyanate solution and 2 cc of dilute hydrochloric acid. The solutions should be colourless. To one, add 10 cc of the assay solution and dilute to the 50 cc mark. To the other, add water, but only to within 5 or 10 cc of this mark. Now run in the standard ferric chloride solution from a small burette, 1 cc at a time, stirring after each addition, till the colour is nearly equal to that of the assay, number 1. At this stage, bring the solution to the same level by diluting, and make a further addition of the standard ferric chloride solution till the colours correspond. The amount of iron will be the same in each tube. That in the standard may be known by reading off the volume from the burette and multiplying by 0.01 milligram. If the 10 cc of the assay solution gave a colour requiring more than 5 or 6 cc of the standard ferric chloride solution, repeat the determination, taking a smaller proportion. The effect of varying conditions on the assay will be seen from the following experiments. Effect of varying temperature. The effect of increase of temperature is to lessen the colour. In fact, by boiling, the colour can be entirely removed. All assays are best carried out in the cold. 1 cc at 15 degrees would only show the colour of 0.75 cc at 45 degrees. 2 cc at 15 degrees would only show the colour of 1.75 cc at 45 degrees. 5 cc at 15 degrees would only show the colour of 4.0 cc at 45 degrees. Effect of time. The effect of increase of time is to increase the colour, as will be seen from the following experiments. 2 cc on standing 10 minutes became equal to 2.25 cc. 2 cc's on standing 20 minutes became equal to 2.75 cc's. 2 cc's on standing 40 minutes became equal to 3.00 cc's. Effect of free acid. If no acid at all be present, the sulfocyanate of potassium solution removes the colour it first produces, so that a certain amount of acid is necessary to develop the colour. The use of a large excess has a tendency to increase the colour produced. 5 cc's nitric acid, note specific gravity 1.4, end note, read 3.7 cc's instead of 2 cc's with the dilute acid. 5 cc's sulfuric acid, note specific gravity 1.32, end note, read 2.2 cc's instead of 2 cc's with the dilute acid. 5 cc's hydrochloric acid, note specific gravity 1.16, end note, read 2.5 cc's instead of 2 cc's with the dilute acid. Effect of foreign metals. Lead, mercury, cadmium, bismuth, arsenic, tin, antimony, nickel, cobalt, manganese, aluminium, zinc, strontium, barium, calcium, magnesium, sodium or potassium, when separately present in quantities of from 100 to 200 times the weight of iron present, do not interfere, if they have previously been brought to their highest oxidized condition by boiling with nitric acid or by treating with permanganate. Arsenic and phosphoric acids interfere unless an excess of free hydrochloric or other acid is present. Oxalic acid, but not tartaric acid, in minute quantities destroys the colour. Nitrous acid strikes a red colour with the sulfocyanate of potassium. Consequently, when nitric acid has been used in excess, high results may be obtained. Copper and some other metals interfere, so that, in most cases, it is advisable to concentrate the iron before estimating it. A blank experiment should always be made with the reagents used, in order to determine the iron, if any, introduced during the solution, etc., of the substance assayed. Determination of iron in metallic copper. This may be most conveniently done during the estimation of the arsenic. The small quantity of white flocculent precipitate which may be observed in the acetic acid solution before titrating contains the whole of the iron as ferric arsenate. It should be filtered off, dissolved in 10 cc's of dilute hydrochloric acid, and diluted to 100 cc's. 10 cc's of this may be taken for the estimation. For example, 10 grams of copper were taken and the iron estimated. 3.0 cc's of standard ferric chloride solution were used, equivalent to 0.03 milligrams of iron. This multiplied by 10, because only 1/10 of the sample was taken, gives 0.3 milligram as the iron in 10 grams of copper. This equals 0.003%. In a series of experiments with this method, working on 10-gram lots of copper, to which known quantities of iron had been added, the following were the results: iron present 0.015%, iron found 0.015%, iron present 0.070%, iron found 0.061%, iron present 0.100%, iron found 0.087%, iron present 0.495%, iron found 0.522%. When no arsenic is present in the copper, the iron can be separated by fractionally precipitating with sodic carbonate, dissolving in ammonia, and filtering off the ferric hydrate. Coppers generally carry more iron the less arsenic they contain. Determination of iron in metallic zinc. Dissolve 1 gram of zinc in 10 cc's of dilute hydrochloric acid, adding a drop or two of nitric acid towards the end to effect complete solution. Boil, dilute, and tint with the permanganate of potassium solution. Boil till colourless and dilute to 100 cc's. Take 10 cc's for the determination. Make a blank experiment by boiling 10 cc's of dilute hydrochloric acid with a drop or two of nitric acid. Add a similar quantity of the permanganate of potassium solution, boiling, etc., as before. The quantity of iron in zinc varies from less than 0.005 to more than 2.0%. When 1 gram is taken and worked as above, each cc of ferric chloride solution required indicates 0.01% of iron. Determination of iron in metallic tin. Cover 1 gram of tin with 5 cc of hydrochloric acid. Add 1 cc of nitric acid and evaporate to dryness. Take up with 2 cc of dilute hydrochloric acid. Add 10 cc of the potassic sulfocyanate solution and make up to 50 cc. Probably the colour developed will be brown instead of red owing to the presence of copper. In this case, add to the standard as much copper as the assay is known to contain. Note, which must have previously been determined. See copper. End note. The titration is then carried out in the usual way. Or the iron may be separated from the copper in the tin by the following process. Dissolve 5 grams of metal in 30 cc of hydrochloric acid and 5 cc of nitric acid, and evaporate to dryness. Take up with 5 cc of dilute hydrochloric acid, add 10 grams of potash dissolved in 30 cc of water, and warm till the tin is dissolved. Pass sulphuretted hydrogen, boil, cool, and filter. The iron and copper will be in the precipitate. They are separated in the ordinary manner. Practical exercises. 1. Calculate from the following determinations the percentages of ferrous, ferric, and total iron in the sample of ore used. 1 gram of ore dissolved and titrated required 26.7 cc of bichromate of potassium solution. 1 gram of ore dissolved, reduced, and titrated required 43.5 cc of bichromate of potassium solution. Standard equals 1.014. 2. 1 gram of an ore contained 0.307 gram of ferrous iron and 0.655 gram of total iron. The iron existing as oxide, what are the percentages of ferrous oxide, FeO, and ferric oxide, Fe2O3, in the ore? 3. 1 gram of brown iron ore dissolved in hydrochloric acid required 59.2 cc of stannous chloride. Standard equals 0.930. Another gram dissolved in acid and titrated with permanganate required 8.2 cc. Standard equals 0.4951. Calculate the percentages of ferrous, ferric, and total iron. 4. Another gram of the same ore, roasted, dissolved, and titrated with stannous chloride, required 63.5 cc. To what extent does this result confirm the others? 5. 2 grams of a metal were dissolved and diluted to 100 cc. 5 cc were taken for a colorimetric determination and required 4.5 cc of the standard ferric chloride solution. What is the percentage of iron in the metal? End of section 26. Section 27 of a textbook of assaying for the use of those connected with mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 11. Iron, Nickel, Cobalt, Zinc, Cadmium. Part 2. Nickel. Nickel and cobalt are closely related in their chemical properties, and may best be considered together. Nickel is the commoner of the two, and is met with in commerce alloyed with copper and zinc as German silver, as also in the coinage of the United States and on the continent. It is used for plating polished iron and steel goods, forming a coating little liable to rust and taking a good polish. The ores of nickel are not very common. Kupfernickel and chloanthite are arsenides of nickel, with generally more or less iron and cobalt. Numiite and garnierite are hydrated silicates of nickel and magnesia. The chief sources of nickel are these silicates, which are found in large quantity in New Caledonia, and a pyrites found in Norway, containing 3 or 4% of the metal. In smaller quantities it is more widely distributed, being frequently met with in copper ores. Consequently, commercial copper is rarely free from it. Nickel is readily soluble in moderately concentrated nitric acid. Its salts are mostly green and soluble in excess of ammonia, forming blue solutions. In these respects it resembles copper. The acid solutions, however, are not precipitated by sulphuretted hydrogen, although in alkaline solutions a black sulfide is formed which is insoluble in dilute hydrochloric acid. If the sulfide is formed in a solution containing much free ammonia, the precipitation is incomplete, some sulfide remaining in the solution and colouring it dark brown. These reactions serve to distinguish and separate nickel from other metals, except cobalt. If the separated sulfide be heated in a borax bead, the colour obtained will be a sherry brown in the outer flame and grey or colourless in the inner flame if nickel only is present. In the presence of cobalt, these colours are masked by the intense and characteristic blue yielded in both flames by that metal. Dry assay. The dry assay of nickel, cobalt being at the same time determined, is based on the formation of a spicer which will carry the cobalt, nickel, copper and some of the iron of the ore in combination with arsenic. Spicer of this kind, fused and exposed at a red heat to air, first loses arsenide of iron by oxidation. It is only when the iron has been oxidized that the arsenide of cobalt begins to be attacked, and when the removal of the cobalt is complete, the nickel commences to pass into the slag, the copper being left till last. The changes are rendered evident by fusion in contact with borax. The process is as follows. Weigh up 5 grams of the ore and calcine thoroughly on a roasting dish in the muffle. Rub up with some anthracite and re-roast. Mix intimately with from 3 to 5 grams of metallic arsenic and heat in a small covered clay crucible at dull redness in a muffle until no more fumes of arsenic come off. Note about 15 minutes. End note. Take out the crucible and inject a mixture of 20 grams of carbonate of soda, 5 grams of flour and 2 grams of fused borax. Place in the wind furnace and raise the temperature gradually until the charge is in a state of tranquil fusion. Pour. When cold, detach the button of spicer and weigh. Weigh out carefully a portion of about 1 gram of it. Place a shallow clay dish in the muffle and heat it to bright redness. Then add about 1.5 gram of borax glass wrapped in a piece of tissue paper. When this has fused, drop the piece of spicer into it. Close the muffle until the spicer has melted, which should be almost at once. The arsenide of iron will oxidize first, and when this has ceased, the surface of the button brightens. Remove it from the muffle and quench in water as soon as the button has solidified. The borax should be coloured slightly blue. Weigh. The loss is the arsenide of iron. Repeat the operation with the weighed button on another dish, using rather less borax. Continue the scorification until a film, green when cold, floating on the surface of the button, shows that the nickel is beginning to oxidize. Cool, separate, and weigh the button as before. The loss is the arsenide of cobalt. If copper is absent, the spicer is now arsenide of nickel. The weight of nickel corresponding to the arsenide got is calculated by multiplying by 0.607, and similarly the weight of the cobalt is ascertained by multiplying the loss in the last scorification by 0.615. Footnote: these compounds are Ni2As and CO2As. End footnote. It must be remembered that the nickel and cobalt so obtained are derived from a fraction only of the spicer yielded by the ore taken, so that the results must be multiplied by the weight of the whole of the speise and divided by the weight of the fragment used in the determination. As an example, suppose 5 grams of ore gave 3.3 grams of speise, and 1.1 gram of this gave 0.8 gram of nickel arsenide. Then 0.8 times 0.607 equals 0.4856 gram of nickel. 0.4856 times 3.3 divided by 1.1 equals 1.456 gram of nickel, and this being obtained from 5 grams of ore is equivalent to 29.12%. When copper is also present, weigh up accurately about 0.5 gram of gold and place it on the scorifier with the button of nickel and copper arsenide, using borax as before. Scorify until the button shows the bluish-green colour of a fused gold-copper alloy. Then cool and weigh the button of copper and gold. The increase in weight of the gold button gives the copper as metal. The weight of the copper multiplied by 1.395 is the weight of the copper arsenide, Cu3As, present. The difference will be the nickel arsenide. The student should enter the weighings in his book as follows: ore taken, grams; speise got, grams; speise taken, grams; arsenides of cobalt, nickel and copper, grams; arsenides of nickel and copper, grams; gold added, grams; gold and copper got, grams; showing cobalt %, nickel %, copper %. Wet methods. Solution and separation. 2 or 3 grams of a rich ore, or 5 to 10 grams if poor, are taken for the assay. If much arsenic is present, as is usually the case, the ore must be calcined before attacking with acids. Transfer to a flask and boil, first with hydrochloric acid until the oxides are dissolved, and then with the help of nitric acid until nothing metalliferous is left. Dilute, nearly neutralize with soda, and separate the iron as basic acetate, as described in page 233. Footnote: with large quantities of iron, the ferric precipitate should be redissolved and reprecipitated. The filtrate must be added to the original filtrate. End footnote. Reader's note, page 233 describes separation of iron. End reader's note. Through the filtrate pass sulphuretted hydrogen till saturated. Allow to settle, best overnight. Filter and wash. Transfer the precipitate to a beaker and dissolve in nitric acid. Dilute with water, pass sulphuretted hydrogen, and filter off the precipitate, if any. Boil off the gas, add ammonia until a precipitate is formed, and then acidify somewhat strongly with acetic acid. Pass sulphuretted hydrogen in a slow stream until any white precipitate of zinc sulfide there may be begins to darken. Filter. To the filtrate add ammonia and pass sulphuretted hydrogen. The precipitate will contain the nickel and cobalt as sulfides. Where small quantities of nickel and cobalt are present and an approximate determination is sufficient, they can be concentrated as follows. Remove the copper, etc. by passing sulphuretted hydrogen through the acid solution and filtering. Add ammonia to the filtrate and again pass sulphuretted hydrogen. Then heat nearly to boiling and filter. Dissolve the precipitate off the filter with dilute hydrochloric acid. The residue will contain nearly all the nickel and cobalt as sulfides. Separation of nickel and cobalt. Dissolve the sulfides separated as above in nitric acid. Render alkaline with a solution of potash, then acidify with acetic acid. Add a concentrated solution of nitrite of potash. The liquid after this addition must have an acid reaction. Allow to stand for 24 hours in a warm place. Filter off the yellow precipitate of nitrite of potash and cobalt, and wash with a 10% solution of acetate of potash. The cobalt is determined in the precipitate in the way described under cobalt. The nickel is separated from the solution by boiling with sodic hydrate, filtering, and dissolving the precipitate in nitric acid. The solution will contain the nickel. Gravimetric determination. The solution, which contains the nickel free from other metals, is heated and a solution of sodic hydrate added in slight excess. The precipitate is filtered off, washed with boiling water, dried, ignited at a red heat, and weighed when cold. The ignited substance is nickel oxide, NiO, and contains 78.67% of nickel. The oxide is a green powder, readily and completely soluble in hydrochloric acid, and without action on litmus paper. It is very easily reduced by ignition in hydrogen to metallic nickel. Nickel is also determined by electrolysis, as follows. The nitric acid solution is rendered strongly ammoniacal and placed under the electrolytic apparatus used for the copper assay. 3 cells, however, must be used, coupled up for intensity, that is, with the zinc of one connected with the copper of the next. Note figure 56, end note. Reader's note, which shows 3 Daniell cells connected in series, end reader's note. The electrolysis is allowed to go on overnight, and in the morning the nickel will be deposited as a bright and coherent film. A portion of the solution is drawn off with a pipette. If it smells of ammonia, has no blue colour, and gives no precipitate with ammonic sulfide, the separation is complete. Wash the cylinder containing the deposited metal, first with water and then with alcohol, as in the copper assay. Dry in the water oven and weigh. The increase in weight is metallic nickel. As an example, there was taken 1 gram of a nickel alloy used for coinage. It was dissolved in 10 cc of nitric acid and diluted to 100 cc with water. The copper was then precipitated by electrolysis. It weighed 0.734 gram. The solution after electrolysis was treated with sulphuretted hydrogen, and the remaining copper was thrown down as sulfide and estimated colorimetrically. This amounted to 3.5 milligrams. The filtrate was evaporated, treated with ammonia, warmed and filtered. The ferric hydrate was dissolved in dilute acid and reprecipitated, dried, ignited and weighed. Its weight was 0.0310 gram. The 2 filtrates were mixed and reduced in bulk to about 50 cc. A considerable excess of ammonia was added, and the nickel precipitated by electrolysis. It weighed 0.2434 gram. These quantities are equivalent to copper 73.75%, nickel 24.34%, iron 2.17%, total 100.26%. Volumetric determination. An alkaline solution of potassium cyanide, to which a little potassium iodide has been added, can be assayed for its strength in cyanide by titrating with a standard solution of silver nitrate. Nickel interferes with this assay, doing the work of its equivalent of silver, and the quantity of nickel present can be calculated from the amount of its interference in the titration. A volumetric assay for nickel is based on this. It has the disadvantage of all indirect titrations, in that it requires 2 standard solutions. On the other hand, it gives good results even under unfavourable conditions, and is applicable in the presence of much zinc. Small quantities of cobalt will count as so much nickel, but larger quantities make the assay unworkable. Some of the other metals, lead for example, have no appreciable effect, but practically the solution demands a preliminary treatment which would result in their removal. Nevertheless, it is a very satisfactory method, and makes the determination of nickel quick and comparatively easy in most cases. The standard solution of silver nitrate is made by dissolving 14.48 grams of recrystallized silver nitrate in distilled water and diluting to 1 litre. 100 cc of this solution are equivalent to 0.25 gram of nickel. Footnote: 4KCy plus NiSO4 yields K2NiCy4 plus K2SO4. 2KCy plus AgNO3 yields KAgCy2 plus KNO3. Therefore, 2AgNO3 yields Ni. End footnote. The standard solution of potassium cyanide should be made so as to be exactly equal to the silver nitrate solution. This can be done as follows. Weigh up 12 grams of good potassium cyanide, note 95%, end note, dissolve in water, add 50 cc of a 10% solution of sodium hydrate, and dilute to 1 litre. Fill one burette with this and another with the solution of silver nitrate. Run 50 cc of the cyanide into a flask. Add a few drops of potassium iodide solution and titrate with the standard silver nitrate until there is a distinct, permanent, yellowish turbidity. The titration is more fully described under cyanide, page 165. The cyanide solution will be found rather stronger than the silver nitrate. Dilute it so as to get the two solutions of equal value. For example, 51.3 cc of silver nitrate may have been required. Then add 1.3 cc of water to each 50 cc of the cyanide solution remaining. If the full 950 cc are available, then add to them 24.7 cc of water. After mixing, take another 50 cc and titrate with the silver nitrate. The two solutions should now be exactly equal. The cyanide solution, being strongly alkaline with soda, keeps very well, but its strength should be checked from time to time by titrating with silver nitrate. Should there be any slight inequality in the strengths of the two solutions, it is easily allowed for in the calculations. The titration. The solution, containing not much more than 0.1 of a gram of nickel and free from the interfering metals, must be cooled. It is next neutralized and then made strongly alkaline with a solution of soda, NaHO. An excess of 20 or 30 cc suffices. This will produce a precipitate. The cyanide solution is now run in from a burette until the solution clears, after which an excess of about 20 cc is added. It is well to use some round number of cc to simplify the calculation. Add a few drops of potassium iodide solution and run in the standard solution of silver nitrate from a burette. This should be done a little at a time, though somewhat rapidly and with constant shaking, till a permanent yellow precipitate appears. If the addition of the cyanide did not result in a perfectly clear solution, this is because something besides nickel is present. The residue may be filtered off, though with a little practice the finishing point may be detected with certainty in the presence of a small precipitate. If the student has the slightest doubt about a finish, he should run in another 5 cc of the cyanide, and again finish with silver nitrate. The second result will be the same as the first. For example, if 40 cc of cyanide and 30 cc of silver nitrate were required at the first titration, then the 45 cc of cyanide in the second titration will require 35 cc of silver nitrate. The difference between the quantities of the two solutions used in each case will be 10 cc. It is this difference in the readings of the two burettes which measures the quantity of nickel present. Each cc of the difference is equal to 0.0025 gram of nickel. But if the cyanide solution is not exactly equal in strength to the silver nitrate, the quantity of cyanide used should be calculated to its equivalent in silver nitrate before making the subtraction. The following experimental results indicate the accuracy of the assay and the effect upon it of varying conditions. A solution containing 1 gram of nickel sulfate, NiSO4.6H2O, in 100 cc was used. By a separate assay, the sulfate was found to contain 22.25% of nickel. For the sake of simplicity, the results of the experiments are stated in weights of nickel in grams. Effect of varying excess of cyanide solution. In each experiment there was 20 cc of the nickel solution, equal to 0.0445 gram of nickel. There were also 10 cc of soda solution, 3 or 4 drops of potassium iodide, and sufficient water to bring the bulk to 100 cc before titrating. Cyanide in excess, 4 cc. Nickel found, 0.0434. Cyanide in excess, 6 cc. Nickel found, 0.0436. Cyanide in excess, 8 cc. Nickel found, 0.0440. Cyanide in excess, 12 cc. Nickel found, 0.0442. Cyanide in excess, 25 cc. Nickel found, 0.0444. Although the difference between the highest and lowest of these results is only 1 milligram, their meaning is quite obvious. The excess of cyanide should not be less than 20 cc. Effect of varying the quantity of soda. There were 2 series of experiments, one with 2 cc of nickel solution, note equals 0.0044 gram of nickel, end note, the other with 20 cc. The solutions were as before, except that the quantity of soda was varied. Soda added 5 cc, nickel found, first series 0.0037, second series 0.0444. Soda added 15 cc, nickel found, first series 0.0042, second series 0.0444. Soda added 30 cc, nickel found, first series 0.0045, second series 0.0442. These show that the presence of much soda, though it has only a small effect, is beneficial rather than otherwise. Ammonia has a bad effect if present in anything like the same quantities. Effect of varying the nickel. In experiments with 10, 20 and 40 cc of the nickel solution, the results were nickel present 0.0222, nickel found 0.0220, nickel present 0.0445, nickel found 0.0442, nickel present 0.0890, nickel found 0.0884. Effect of zinc. In these experiments, 20 cc of nickel solution, note equals 0.0445 gram of nickel, end note, 10 cc of soda, 6 drops of potassium iodide and water to 100 cc were used. The excess of cyanide was purposely kept at from 10 to 15 cc, which is hardly sufficient. Zinc added 0, nickel found 0.0442. Zinc added 0.25 gram, nickel found 0.0440. Zinc added 0.5 gram, nickel found 0.0407. On increasing the excess of cyanide to over 20 cc and doubling the quantity of soda, the experiment with 0.5 of a gram of zinc gave 0.441 of a gram of nickel. Hence the titration is satisfactory in the presence of zinc, provided that not fewer than 20 or 30 cc of soda are used, and that the excess of cyanide is such that not fewer than 20 or 30 cc of silver nitrate are required in the titration. Moreover, these precautions should be taken whether zinc is present or not. Effect of other metals. If metals of the first and second groups are present, they should be removed by passing sulphuretted hydrogen and filtering. If iron is present, it must be removed, since ferrous salts use up much cyanide, forming ferrocyanides, and ferric salts yield ferric hydrate, which obscures the end reaction. Hence the sulphuretted hydrogen must be boiled off, and the iron removed as basic ferric acetate by the method described on page 233. Reader's note at the beginning of the section on iron, under separation, end reader's note. If the precipitate is bulky, it should be dissolved in a little dilute acid, neutralized, and again precipitated as basic acetate. The nickel will be in the 2 filtrates. In the absence of manganese and cobalt, the titration may be made without further separation. Manganese does not directly interfere, but the precipitated hydrate, which rapidly darkens through atmospheric oxidation, obscures the end reaction. It may be removed by passing sulphuretted hydrogen through the filtrate from the acetate separation. Sulphides of nickel, cobalt and zinc will be precipitated, whilst manganese remains in solution. The addition of more sodium acetate may assist the precipitation. The precipitate must be filtered off and dissolved in nitric acid. The solution should be evaporated to dryness. The filtrate may retain a little nickel. If so, add ammonia till alkaline, then acidify with acetic acid and again filter. Any small precipitate obtained here should be added to that first obtained. It is only when cobalt is present that any further separation is required. Cobalt hydrate takes up oxygen from the air, and on adding potassium cyanide, some may refuse to dissolve, and the solution itself acquires a brown colour which becomes deeper on standing. At this stage the cobalt is easily separated. The solution containing the nickel and cobalt, with no great excess of acid, is made alkaline by adding 20 c.c. of soda, exactly as in preparing for a titration. So too the solution of cyanide is added so as to have an excess of 20 or 30 c.c. The solution may have a brown colour, but if it is not quite clear, it must be filtered. Then warm, boiling is not needed, and add from 50 to 100 c.c. of bromine water. This throws down all the nickel as black peroxide in a condition easy to filter. Filter it off and wash with water. The precipitate can be dissolved off the filter with the greatest ease by a little warm sulphurous acid. The filtrate and washings, boiled till free from sulphurous acid, yield the nickel as sulphate in a clean condition. Determination of nickel in nickel sulphate crystals. Take 0.5 gram of the salt, dissolve in 50 c.c. of water, and add 25 c.c. of solution of soda. Run in from a burette, say 60 c.c. cyanide. Add a few drops of potassium iodide and titrate back with silver nitrate. Suppose 15.5 c.c. of the latter is required, then 15.5 c.c. subtracted from 60 c.c. leaves 44.5 c.c. And since 100 c.c. equals 0.25 gram of nickel, 44.5 c.c. will equal 0.11125 gram of nickel. This in 0.5 gram of the salt equals 22.25%. Determination of nickel in German silver. Weigh up 0.5 gram of the alloy and dissolve in a dish with 5 or 10 c.c. of dilute nitric acid. Add 5 c.c. of dilute sulphuric acid and evaporate till all the nitric acid is removed. Cool, take up with 50 c.c. of water, and when dissolved, pass sulphuretted hydrogen through the solution. Filter off the precipitate and wash with water containing sulphuretted hydrogen and dilute sulphuric acid. Boil down the filtrate and washings to get rid of the excess of the gas. Add some nitric acid and continue the boiling. Cool, neutralize the excess of acid with soda, add 1 gram of sodium acetate and boil. Filter off the precipitate, which contains the iron. The filtrate, cooled and rendered alkaline with soda, is ready for the titration. Cobalt occurs less abundantly than nickel. Its chief ores are smeltite and cobaltite, which are arsenides of cobalt with more or less iron, nickel and copper. It also occurs as arseniate in erythrine and as oxide in asbolan or earthy cobalt, which is essentially a wad carrying cobalt. It is mainly used in the manufacture of smalts for imparting a blue colour to glass and enamels. The oxide of cobalt forms coloured compounds with many other metallic oxides. With oxide of zinc it forms Rinman's green, with alumina a blue, with magnesia a pink. This property is taken advantage of in the detection of substances before the blowpipe. The compounds of cobalt, in most of their properties, closely resemble those of nickel, and the remarks as to solution and separation given for the latter metal apply here. Solutions of cobalt are pink, while those of nickel are green. The detection of cobalt, even in very small quantity, is rendered easy by the strong blue colour which it gives to the borax bead, both in the oxidizing and in the reducing flame. It is concentrated from the ore in the same way as nickel, and should be separated from that metal by means of potassic nitrite, in the way described. The dry assay of cobalt has been given under nickel. Gravimetric method. The yellow precipitate from the potassium nitrite, after being washed with the acetate of potash, is washed with alcohol, dried, transferred to a weighed porcelain crucible, and cautiously ignited with an excess of strong sulphuric acid. The heat must not be sufficient to decompose the sulphate of cobalt, which decomposition is indicated by a blackening of the substance at the edges. The salt bears a low red heat without breaking up. If blackening has occurred, moisten with sulphuric acid and ignite again. Cool and weigh. The substance is a mixture of the sulphates of cobalt and potash. Note 2COSO4 plus 3K2SO4, end note, and contains 14.17% of cobalt. Cobalt is also gravimetrically determined, like nickel, by electrolysis or by precipitation with sodic hydrate. In the latter case, the ignited oxide will be somewhat uncertain in composition, owing to its containing an excess of oxygen. Consequently, it is better to reduce it by igniting at a red heat in a current of hydrogen, and to weigh it as metallic cobalt. Practical exercises. 1. In the dry assay of an ore containing cobalt, nickel, and copper, the following results were obtained. Calculate the percentages. Ore taken 5 grams, speise formed 0.99 gram, speise taken 0.99 gram. Arsenides of cobalt, nickel, and copper got 0.75 gram. Arsenide of nickel and copper got 0.54 gram. Gold added 0.5 gram. Gold and copper got 0.61 gram. 2. Calculate the percentage composition of the following compounds: CO2As, Ni2As, and Cu2As. 3. A sample of mispickel contains 7% cobalt. What weight of the mixed sulphates of potash and cobalt will be obtained in a gravimetric determination on 1 gram of the ore? 4. 0.3157 gram of metal was deposited by the electrolysis of a nickel and cobalt solution. On dissolving in nitric acid and determining the cobalt, 0.2563 gram of potassium and cobalt sulphates were got. Find the weight of cobalt and nickel present in the deposit. 5. What should be the percentage composition of pure cobaltite, its formula being COASS? End of section 27. Section 28 of A Textbook of Assaying for the Use of Those Connected with Mines by C. and J. J. Beringer. This LibriVox recording is in the public domain. Recording by Peter Yearsley. Chapter 11. Iron, Nickel, Cobalt, Zinc, Cadmium. Zinc. Zinc occurs in nature most commonly as sulfide, blende. It also occurs as carbonate, calamine, and silicate, smithsonite. Each of these is sufficiently abundant to be a source of the metal. The metal is known in commerce as spelter when in ingots, and as sheet zinc when rolled. It is chiefly used in the form of alloys with copper, which are known as brasses. It is also used in the form of a thin film to protect iron goods from rusting, galvanized iron. Ores of zinc, more especially blende, are met with in most lead, copper, gold, and silver mines, in larger or small quantities scattered through the lodes. Those ores which generally come under the notice of the assayer are fairly rich in zinc, but alloys and metallurgical products contain it in very varying proportions. Zinc itself is readily soluble in dilute acids. Any residue which is left after boiling with dilute hydrochloric or sulphuric acid consists simply of the impurities of the metal. This is generally lead. All zinc compounds are either soluble in, or are decomposed by, boiling with acids, zinc going into solution. Zinc forms only one series of salts, and these are colourless. Their chief characteristic is solubility in an alkaline solution, from which sulphuretted hydrogen produces a white precipitate of zinc sulfide. Zinc is detected by dissolving the substance in hydrochloric or nitric acid, boiling and adding sodic hydrate in excess, filtering, and adding ammonic sulfide to the filtrate. The precipitate contains the zinc, which can be dissolved out by boiling with dilute sulphuric acid, and detected by the formation of a white precipitate on the addition of potassic ferrocyanide. The dry assay of zinc can only be made indirectly and is unsatisfactory. Zinc is volatile, and at the temperature of its reduction is a gas. It is impracticable to condense the vapour so as to weigh the metal. Consequently, its amount is determined by loss. The following method gives approximate results. Take 10 grams of the dried and powdered ore and roast, first at a low temperature and afterwards at a higher one, with the help of carbonate of ammonia to decompose the sulphates formed. Cool and weigh. The metals will be present as oxides. Mix with 2 grams of powdered charcoal and charge into a black lead crucible, heated to whiteness. Cover loosely and leave in the furnace for about 1/4 hour. Uncover and calcine the residue, cool and weigh. The loss in weight multiplied by 8.03 gives the percentage of zinc in the ore. Wet methods. Solution and separation may be effected as follows. Treat 1 or 3 grams of the substance with 10 or 30 c.c. of hydrochloric acid or aqua regia. Evaporate to dryness. Take up with 10 c.c. of hydrochloric acid and dilute to 100 c.c. Heat nearly to boiling. Saturate with sulphuretted hydrogen. Filter and wash with water acidulated with hydrochloric acid. Boil off the sulphuretted hydrogen and peroxidize with a few drops of nitric acid. Cool. Add caustic soda till nearly but not quite neutralized, and separate the iron as basic acetate by the method described under iron. To the filtrate add ammonia till alkaline and pass sulphuretted hydrogen. Allow to settle and decant onto a filter. Dissolve off the precipitate from the filter with hot dilute hydrochloric acid. The solution will contain the zinc, together with any manganese the ore contained, and, perhaps, traces of nickel and cobalt. If the zinc is to be determined volumetrically, and manganese is present, this latter is separated with carbonate of ammonia, as described further on. But if a gravimetric method is used, and only small quantities of manganese are present, it is better to proceed as if it were absent, and to subsequently determine its amount, which should be deducted. Gravimetric determination. The solution containing the zinc is contained in an evaporating dish and freed from sulphuretted hydrogen by boiling, and, if necessary, from an excess of acid by evaporation. The evaporating dish must be a large one. Cautiously add sodium carbonate to the hot, moderately dilute solution until the liquid is distinctly alkaline, and boil. Allow the precipitate to settle, decant onto a filter, and wash with hot water. Dry, transfer to a porcelain crucible, note, cleaning the paper as much as possible, end note. Add the ash, ignite, and weigh. The substance weighed is oxide of zinc, which contains 80.26% of the metal. It is a white powder, becoming yellow when heated. It must not show an alkaline reaction when moistened. If it contains manganese, this metal will be present as sesquioxide, Mn2O3. Its amount can be determined by dissolving in dilute acid and boiling with an excess of sodic hydrate. The oxide of manganese will be precipitated and can be ignited and weighed. Its weight multiplied by 1.035 must be deducted from the weight of oxide of zinc previously obtained. The results yielded by the gravimetric determination are likely to be high, since the basic carbonate of zinc frequently carries down with it more or less soda, which is difficult to wash off. Volumetric determination. This method is based on the facts that zinc salts in an acid solution decompose potassium ferrocyanide, forming a white insoluble zinc compound, and that an excess of the ferrocyanide can be detected by the brown coloration it strikes with uranium acetate. The method resembles in its working the bichromate iron assay. The standard solution of potassium ferrocyanide is run into a hot hydrochloric acid solution of the zinc until a drop of the latter brought in contact with a drop of the indicator, uranium acetate, on a white plate strikes a brown colour. The quantity of zinc in the solution must be approximately known. Run in a little less of the ferrocyanide than is expected will be necessary. Test a drop or two of the assay and then run in 1 or 2 cc at a time until the brown colour is obtained. Add 5 cc of a standard zinc solution, equivalent in strength to the standard ferrocyanide, retitrate, and finish off cautiously. Of course, 5 cc must be deducted from the reading on the burette. The precipitate of zinc ferrocyanide formed in the assay solution is white, but if traces of iron are present, it becomes bluish. If the quantity of ferrocyanide required is known within a few cc's, the finishing point is exactly determined in the first titration, without any addition of the standard zinc solution. Unfortunately, this titration serves simply to replace the gravimetric determination, and does not, as many volumetric processes do, lessen the necessity for a complete separation of any other metals which are present. Most metals give precipitates with ferrocyanide of potassium in acid solutions. If the conditions are held to, the titration is a fairly good one, and differences in the results of an assay will be due to error in the separation. Ferric hydrate, precipitated in a fairly strong solution of zinc, will carry with it perceptible quantities of that metal. Similarly, large quantities of copper, precipitated as sulfide by means of sulphuretted hydrogen, will carry zinc with it, except under certain nicely drawn conditions. When much copper is present, it is best separated in a nitric acid solution by electrolysis. The titration of the zinc takes less time and, with ordinary working, is more trustworthy than the gravimetric method. The standard ferrocyanide solution is made by dissolving 43.2 grams of potassium ferrocyanide. Note K4FeCy6.3H2O in water and diluting to a litre. 100 cc's are equal to 1 gram of zinc. The standard zinc solution is made by dissolving 10 grams of pure zinc in 50 cc's of hydrochloric acid and 100 or 200 cc's of water and diluting to 1 litre, or by dissolving 44.15 grams of zinc sulphate, note ZnSO4.7H2O, in water with 30 cc's of hydrochloric acid and diluting to 1 litre. 100 cc's will contain 1 gram of zinc. The uranium acetate solution is made by dissolving 0.2 gram of the salt in 100 cc's of water. To standardize the ferrocyanide, measure off 50 cc's of the standard zinc solution into a 10-ounce beaker, dilute to 100 cc's and heat to about 50 degrees centigrade, not to boiling. Run in 47 or 48 cc's of the ferrocyanide solution from an ordinary burette, and finish off cautiously. 50 divided by the quantity of ferrocyanide solution required gives the standard. In assaying ores, etc., take such quantity as shall contain from 0.1 to 1 gram of zinc. Separate the zinc as sulphide, as already directed. Dissolve the sulphide off the filter with hot dilute hydrochloric acid, which is best done by a stream from a wash bottle. Evaporate the filtrate to a paste. Add 5 cc's of dilute hydrochloric acid. Dilute to 100 cc's or 150 cc's. Heat to about 50 degrees centigrade and titrate. Manganese, if present, counts as so much zinc and must be specially separated, since it is not removed by the method already given. The following method will effect its removal. To the hydrochloric acid solution of the zinc and manganese, add sodium acetate in large excess, and pass sulphuretted hydrogen freely. Allow to settle. Filter off the zinc sulphide, and wash with sulphuretted hydrogen water. The precipitate freed from manganese is then dissolved in hydrochloric acid and titrated. The following experiments show the effect of variation in the conditions of the assay. Effect of varying temperature. Using 20 c.c. of the standard zinc solution, 5 c.c. of dilute hydrochloric acid, and diluting to 100 c.c. Temperature 15 degrees centigrade. Ferrocyanide required 20.6 c.c. Temperature 30 degrees centigrade. Ferrocyanide required 20.3 c.c. Temperature 70 degrees centigrade. Ferrocyanide required 20.3 c.c. Temperature 100 degrees centigrade. Ferrocyanide required 20.3 c.c. The solution can be heated to boiling before titrating without interfering with the result, but it is more convenient to work with the solution at about 50 degrees centigrade. Cold solutions must not be used. Effect of varying bulk. These were all titrated at about 50 degrees centigrade, and were like the last, but with varying bulk. Bulk 25.0 c.c. Ferrocyanide required 20.2 c.c. Bulk 50.0 c.c. Ferrocyanide required 20.4 c.c. Bulk 100.0 c.c. Ferrocyanide required 20.3 c.c. Bulk 200.0 c.c. Ferrocyanide required 20.4 c.c. Any ordinary variation in bulk has no effect. Effect of varying hydrochloric acid. With 100 c.c. bulk and varying dilute hydrochloric acid, the results were acid added 0.0 c.c. Ferrocyanide required 24.4 c.c. Acid added 1.0 c.c. Ferrocyanide required 20.2 c.c. Acid added 5.0 c.c. Ferrocyanide required 20.3 c.c. Acid added 10.0 c.c. Ferrocyanide required 20.3 c.c. Acid added 20.0 c.c. Ferrocyanide required 20.7 c.c. Effect of foreign salts. The experiments were carried out under the same conditions as the others. 5 grams each of the following salts were added. Salt added: ammonic chloride. Ferrocyanide required 20.3 c.c. Salt added ammonic sulfate. Ferrocyanide required 20.5 c.c. Salt added sodium chloride. Ferrocyanide required 20.6 c.c. Salt added sodium sulfate. Ferrocyanide required 20.4 c.c. Salt added potassium nitrate. Ferrocyanide required 20.2 c.c. Salt added magnesium sulfate. Ferrocyanide required 20.4 c.c. Salt added nil. Ferrocyanide required 20.4 c.c. In a series of experiments in which foreign metals were present to the extent of 0.050 gram in each, with 20 c.c. of zinc solution and 5 c.c. of dilute hydrochloric acid, those in which copper sulfate, ferrous sulfate, and ferric chloride were used gave, as might be expected, so strongly coloured precipitates that the end reaction could not be recognized. The other results were: with nothing added, ferrocyanide required 20.3 c.c. With 0.050 gram lead as chloride, ferrocyanide required 20.9 c.c. With 0.050 gram manganese as sulfate, ferrocyanide required 25.5 c.c. With 0.050 gram cadmium as sulfate, ferrocyanide required 23.5 c.c. With 0.050 gram nickel as sulfate, ferrocyanide required 26.2 c.c. Effect of varying zinc. These were titrated under the usual conditions and gave the following results. Zinc added 1.0 c.c. Ferrocyanide required 1.1 c.c. Zinc added 10.0 c.c. Ferrocyanide required 10.2 c.c. Zinc added 20.0 c.c. Ferrocyanide required 20.3 c.c. Zinc added 50.0 c.c. Ferrocyanide required 50.6 c.c. Zinc added 100.0 c.c. Ferrocyanide required 101.0 c.c. Determination of zinc in a sample of brass. Take the solution from which the copper has been separated by electrolysis and pass sulphuretted hydrogen until the remaining traces of copper and the lead are precipitated. Filter, boil the solution free from sulphuretted hydrogen, put in a piece of litmus paper and add sodic hydrate solution in slight excess. Add 10 c.c. of dilute hydrochloric acid, which should render the solution acid and clear. Warm and titrate. A sample of 0.5 gram of brass treated in this manner required 16.4 c.c. of ferrocyanide. Note standard 100 c.c. equals 0.9909 zinc. End note. Which equals 0.1625 gram of zinc, or 32.5%. Determination of zinc in blend. Dissolve 1 gram of the dried and powdered sample in 25 c.c. of nitric acid, with the help of 2 or 3 grams of potassium chlorate dissolved in the acid. Evaporate to complete dryness, taking care to avoid spurting. Add 7 grams of powdered ammonium chloride, 15 c.c. of strong ammonia, and 25 c.c. of boiling water. Boil for 1 minute and see that the residue is all softened. Filter through a small filter and wash thoroughly with small quantities of a hot 1% solution of ammonium chloride. Add 25 c.c. of hydrochloric acid to the filtrate. Place in the solution some clean lead foil, say 10 or 20 square inches. Boil gently until the solution has been colourless for 3 or 4 minutes. Filter, wash with a little hot water, and titrate with standard ferrocyanide. Determination of zinc in silver precipitate. This precipitate contains lead sulphate, silver, copper, iron, zinc, lime, etc. Weigh up 5 grams of the sample and extract with 30 c.c. of dilute sulphuric acid with the aid of heat. Separate the copper with sulphuretted hydrogen. Peroxidize the iron with a drop or two of nitric acid and separate as acetate. Render the filtrate ammoniacal, pass sulphuretted hydrogen, warm and filter. Dissolve the precipitated zinc sulphide in dilute hydrochloric acid. Evaporate, dilute and titrate. Silver precipitates carry about 2.5% of zinc. Gasometric method. Metallic zinc is readily soluble in dilute hydrochloric or sulphuric acid, hydrogen being at the same time evolved. Footnote: Zn plus H2SO4 yields H2 plus ZnSO4. End footnote. The volume of the hydrogen evolved is obviously a measure of the amount of zinc present in the metallic state. The speed with which the reaction goes on, even in the cold, and the insolubility of hydrogen renders this method of assay a convenient one. It is especially applicable to the determination of the proportion of zinc in zinc dust. The apparatus described in the chapter on gasometric method is used. The method of working is as follows. Fill the 2 burettes with cold water to a little above the 0 mark. Place in the bottle about 0.25 gram of the substance to be determined, and in the inner phial or test tube 5 c.c. of dilute sulphuric acid. Cork the apparatus tightly and allow to stand for a few minutes. Then bring the water to the same level in the 2 burettes by running out through the clip at the bottom. Read off the level of the liquid in the graduated burette. Turn the bottle over sufficiently to spill the acid over the zinc, and then run water out of the apparatus so as to keep the liquid in the 2 burettes at the same level, taking care not to run it out more quickly than the hydrogen is being generated. When the volume of gas ceases to increase, read off the level of the liquid, deduct the reading which was started with. The difference gives the volume of hydrogen evolved. At the same time, read off the volume of air in the volume corrector, which must be fixed alongside the gas burettes. Make the correction. For example, a piece of zinc weighing 0.2835 gram was found to give 99.9 c.c. of gas at a time when the corrector read 104 c.c. Footnote: these 104 c.c. are equivalent to 100 c.c. of dry air at 0 degrees centigrade and 760 millimeters. End footnote. Then the corrected volume is 104 to 100 is equivalent to 99.9 to X. X equals 96.0 cc's. 100 cc's of hydrogen at 0 degrees centigrade and 760 millimeters is equivalent to 0.2912 gram of zinc. Therefore, the quantity of zinc found is 100 to 96, equivalent to 0.2912 to X. X equals 0.2795 gram of zinc. This being contained in 0.2835 gram of metal is equivalent to 98.5%. As an example of a determination in which reducing the volume of liberated hydrogen to 0 degrees centigrade and 760 millimeters is avoided, the following may be taken. 0.2315 gram of pure zinc gave 82.1 cc's of gas, and the volume of air in the corrector was 103.6 cc's. 0.2835 gram of the assay gave 99.9 cc's of gas, and the volume of air in the corrector was 104.0 cc's. 104 to 103.6 is equivalent to 99.9 to X. X equals 99.5 cc's. This is the volume of gas got in the assay if measured under the same conditions as the standard. 82.1 to 99.5 is equivalent to 0.2315 to X. X equals 0.2806. Then 0.2835 to 0.2806 is equivalent to 100 to X. X equals 98.9%. As these assays can be made quickly, it is well for the sake of greater accuracy to make them in duplicate, and to take the mean of the readings. One set of standardizings will do for any number of assays. The student must carefully avoid unnecessary handling of the bottle in which the zinc is dissolved. Colorimetric method. Zinc salts being colourless, there is no colorimetric determination. Examination of commercial zinc. Take 20 grams of zinc and dissolve them in dilute nitric acid. Boil, allow to settle, filter, wash, dry, ignite the precipitate, if any, and weigh as oxide of tin. Examine this for arsenic. Lead. Add ammonia and carbonate of ammonia to the liquid and boil. Filter off the precipitate, wash with hot water. Digest the precipitate with dilute sulfuric acid. Filter, wash and weigh the sulfate of lead. Iron. To the filtrate from the sulfate of lead, add ammonia and pass sulphuretted hydrogen. Digest and filter. Save the filtrate. Dissolve the precipitate in hydrochloric acid, oxidize with nitric acid and precipitate with ammonia. Wash, ignite, and weigh as ferric oxide. Calculate to iron. Arsenic. To the filtrate from the sulfide of iron, add hydrochloric acid in slight excess. Filter off and wash the precipitate. Rinse it back into the beaker, dissolve in nitric acid. Filter from the sulfur and add ammonia in excess and magnesia mixture. Filter off the ammonic magnesic arsenate and wash with dilute ammonia. Dry, ignite with nitric acid and weigh as magnesic pyrarsenate. Calculate to arsenic and add to that found with the tin. Copper. To the filtrate from the ammonia and ammonic carbonate, add sulfuric acid in small excess and pass sulphuretted hydrogen. Allow to settle, filter and wash. Rinse the precipitate into a beaker, boil with dilute sulfuric acid and filter. Save the filtrate. Dry, burn the paper with the precipitate, treat with a drop or two of nitric acid, ignite, and weigh as copper oxide. Calculate to copper. Cadmium. To the filtrate from the sulfide of copper, add ammonia so as to nearly neutralize the excess of acid, and pass sulphuretted hydrogen. Collect and weigh the precipitate as cadmium sulfide, as described under cadmium. Practical exercises. 1. What weight of hydrogen will be evolved in dissolving 1 gram of zinc in dilute sulfuric acid? 2. How many cc's would this quantity of hydrogen measure at 0 degrees centigrade and 760 millimeters? Note, 1 litre weighs 0.0896 gram. End note. 3. 0.23 gram of zinc are found to give 77.9 cc's of hydrogen. In another experiment under the same conditions, 80.2 cc's are got. What weight of zinc was used for the second experiment? 4. A sample of blend is found to contain 55% of zinc. What percentage of zinc sulfide did the sample contain? 5. How much metallic lead would be precipitated from a solution of lead acetate by 1 gram of zinc? Cadmium. Cadmium occurs in nature as cadmium sulfide in greenockite, CdS, which is very rare. It is widely diffused in calamine, blende, and other zinc ores, forming in some cases as much as 2 or 3% of the ore. Oxide of cadmium forms the brown blaze of the zinc smelters. Sulfide of cadmium is used as a pigment, cadmium yellow, and the metal and some of its salts are useful reagents. The salts of cadmium closely resemble those of zinc. The hydrate, however, is insoluble in excess of potash, and the sulfide is insoluble in dilute acids. It forms only one series of salts. Cadmium is detected by giving with sulphuretted hydrogen in solutions, not too strongly acid, a yellow precipitate, which is insoluble in solutions of the alkalis, alkaline sulfides, or cyanide of potassium. Solution and separation. Substances containing cadmium are soluble in acids. The solution is evaporated to dryness to render any silica that may be present insoluble, and taken up with 10 cc's of dilute hydrochloric acid. Dilute to 100 cc's and pass sulphuretted hydrogen. Filter, digest the precipitate with soda, wash, and boil with dilute sulphuric acid. Filter. The filtrate contains the cadmium and possibly a small quantity of zinc, from which it is best separated by reprecipitating with sulphuretted hydrogen. Gravimetric determination. The solution containing the cadmium, freed from the other metals, is precipitated with sulphuretted hydrogen in a moderately acid solution. The precipitate is collected on a weighed filter and washed, first with an acid solution of sulphuretted hydrogen and afterwards with water. It is dried at 100 degrees centigrade and weighed. If free sulphur is suspected to be present, extract with bisulfide of carbon and again weigh. The residue is cadmium sulfide, which contains 77.78% of cadmium. It is a yellow powder, insoluble in solutions of the alkalis, alkaline sulfides, or cyanide of potassium. It dissolves readily in acid. It cannot be ignited in a current of hydrogen without loss. Volumetric method. The solution containing the cadmium is concentrated by evaporation and mixed with an excess of oxalic acid and alcohol. The precipitate is filtered, washed with alcohol, dissolved in hot hydrochloric acid, and titrated with permanganate of potassium. The end of section 28.